Okay, so we should be live. What I'm just going to do, I'm just going to wait until the until I see the video appear on YouTube. Apologies if you're already watching. Just don't trust this. Weirdly, it says live in 18 minutes here. It should have started by now.
Yeah, I'm seeing it.
You seeing it?
Yeah.
All right, well, without further ado. Okay, so welcome everybody. Thanks to all of those who are watching along, and thanks to all of those who have made a donation already. This is a maths marathon, 24 exams in 24 hours. To raise money for Refuge, a charity who helps victims of domestic violence, particularly women and children, as they are more likely to be victims of domestic violence than anybody else. If you've not yet donated, no problem. You can click the link in the description and donate there. And joining me on the first, the first 9 hours or so is my good friend James Gill, who is a statistician working with the NHS.
Yeah, that's right. Hello, everyone.
Okay, so on the menu today, so plenty of GCSE papers, plenty of A-level papers. We're going to be doing another journey from Key Stage 1 all the way up to a degree level. For those who don't know, Key Stage 1 is what we call in this country, in the UK, the exams that you do when you are in year 2. So that's you're about 6-7 years old when you take those. So easy, but with a surprising amount of mathematical sophistication that I love to talk about. And we're going to go all the way up through school into college and do a degree level paper. And I'm going to talk through how the mathematics develops over that time. What else have we got? I think that's about it. That about covers it. We've also got some international GCSE papers. They are exactly what it sounds like. The GCSE is the exam taken by 16 to 17 year olds, by 15 to 16 year olds in the UK. The international GCSE are for students wanting a GCSE qualification who live outside of the UK, but it's the equivalent level of qualification, and plenty of A-level papers, and yeah. Anything to add, James, before we get started?
Nope, just really excited to see you do some maths.
Right,
Looking
okay.
forward to it.
I wish I was. I mentioned this to you earlier. I had a terrible night's sleep last night, and I did this last year, and it went fine. But the amount of prep that I've done this year has been minimal, to say the least. So let's just get on with it. Let's just see how it goes. So let's start with a degree level paper. A GCSE level paper. To begin with, I've got one here. Okay, so I remember last year I was incredibly nervous until I got the first paper out of the way. So let's stop my hand from shaking with one of these. Should be fairly easy. It's non-calculator, which is always my preferred paper. The questions tend to be a bit more interesting. I think when you can rely on the calculator, there's two types of calculator question, isn't there? There's the kind of calculator question where you need the calculator, so it's like some trigonometric question or something. And then there's the kind of question where it's a non-calculator question, but they just made the numbers really faffy, which is not my kind of thing. So I'm just going to update the list here. So this is GCSE. Okay, I'm going to put a little countdown up here. So this is exam 1 of 24. There we go, look at that. Okay, so, ready? Let's do it.
Here we go.
All right, first paper. Okay, there are only blue, red, and yellow cubes in a box. The number of red boxes is the same as the number of yellow cubes, so these are equal in probability. There are 12 blue cubes in the box. Work out the total number of cubes in the box. So it must be 60, right? This is a 0.2 chance that they get taken. All right, easy start. So Dion needs 50 grams of sugar to make 15 biscuits. She needs, you know what? Already, I hate these questions, and they love them now. Ratio is just like a topic in and of itself. You know, it's just every question has to involve ratio. Anyway, so 50 grams of sugar to make 15. Right, maybe this isn't as bad as I thought. So that's 150 grams of flour, 2 times as much butter. So the amount of flour is 150 grams. Oh, to make 60 biscuits. So 4 of that, which is 600. 3 marks for that. That seems a bit too easy. Fine. Dion has to buy all the sugar she needs to make 60 biscuits in to make 60 bigots. 250 gram packs. So she needs 400 grams. So that means she needs 2 packs. Fine. Highest common factor of 72 and 90 must be 12, right? Oh no, not 12. That's not 18 then. So 18 definitely goes into both of them. Can we get any higher than that? We'd have to times by 4. No, 18. All right.
Yeah.
Oh, geez, plans and elevations. Well, we're looking at a cylinder, aren't we? Viewers will be pleased to know that I've sharpened my pencils this year. So let's do a cylinder like that. Okay, it's a centimeter grid. So it's 4 centimeters by 6 centimeters. Got it? These feel like the old spec questions, if I'm being honest. Shape A can be transformed by reflection in the x-axis followed by that. So after we reflect in the x-axis, we are going to be there. So 1, 2, 3, 4, 5, 6 by 1. And the negative, because we're going in the negative direction. Okay.
Yeah.
I'm just going to try and keep all these papers in the right order. Just mix them up here. Okay. Black pens, red pens, green pens. Wow, how to annoy your customers with the number sold. Okay, work out the number of green. Okay, all right. Okay, so that's 14 black pens to 15 red pens to 24 green pens. I think this is how we'll do it. So this adds up to 54. So we need 4 of those to make 512. So 24 times 4, 96 green pens. 2 rectangles. I tend to like these questions actually. QR is 10. So the perimeter of this one is 26. The area of this one is 45. So we know that. And we know that BC is equal to PQ. So this one's 4.5. So that's 9, isn't it? So the other 2 sides must add up to 17. They're equal, so 8.5. Happy with that?
Yep.
An estimate, so we're going to do 60 times 100 and then rooted, which is root 6,000.
Oh, God.
Wow, yeah. What does it want me to do there? Because
64, I think.
yeah, I mean, it's between. Yeah, it must be around the 80 mark. So let's go with 80. That is 148 corrected to 3 significant figures. Work out the value of that. Okay, so that's 0.23 is 2.3 times 10 to the minus 1. So to the 6 is 148 times 10 to the minus 6. So 148, we're going to go 1, 2, 3, 4, 5, I think it's there. 1, 2, 3, 4, 5, 6. Oh, but we only want it to 3. Oh yeah, that's 3 significant figures. Work out the value of 5 to the minus 2, 1 on 25. Okay, work out that. So we're going to convert them out into improper fractions and times. So that's 56 on 10, which as a mixed number is 5 and 3/5 in its simplest form. All right. A bit of graphs now. The graphs with these equations have been drawn. Yeesh, look at that. Using the graphs, find estimates to the solutions of the simultaneous equations. This is amazing how easy this is. This is 2019. You know what I mean? So the old spec GCSE, this, yeah, this, oh, I've just read your comment about that roots question. Yeah, totally agree with that. That's probably a decent shout. I'm happy with 80.
Yeah.
Part of this is what the actual exam wants from you. You know, it's you know, like estimate. There's no good meaning of the word estimate. However, in GCSE, it has a specific meaning of round everything to one significant figure before you do the calculation. And that is not how any grown-up would estimate. But because they have to write mark schemes and they can't just leave it all fluffy, they have to have this like very specific meaning for it. You know what I mean? So it's almost sometimes just like trying to get your head around what the question's actually asking of you. Anyway, so I mean they have a solution where they cross, right? So 2.25, let's say, and y is minus 1.3.
Yeah.
Now, we've not been screwed over by the question here, have we? They really are the same.
Yeah, it's bizarre.
So sometimes
Very
they can, sometimes they can maybe if you maybe change that, and it actually wants you to do something with it, you know.
Yeah.
But no. Oh jeez, please tell me they're already in order. A bus recorded the ages. 23 people on coach A. Well, this stands out as the middle number, doesn't it? I like how they've actually arranged arranged those so that the middle number is there. That's actually quite nice. And then the upper quartile, we're going to go for 66.5. And we'll go 53 for the lower quartile. Richard says that people on coach A are younger. Is Richard correct? I would say yes. Lower median age. Usually it's a 2-mark question, and it asks you about the median, and it asks you about the consistency of the results. So you have to compare the interquartile ranges. But I'm fairly okay with that. I mean they're all lower actually. There's no there's actually no ambiguity there at all.
Well, except for the fact that it's not that everybody on coach A is younger. It's just on average.
Oh yeah, yes, on average. Yeah, that's a good point. Such a statistician, aren't you? You know.
Yeah. Well, I mean, believe me, people make a mess of this stuff every day.
Oh
so.
no, I can. Hang on a minute. Richard says that the people on coach A vary more than in age than the people on coach B. All right, so that is exactly the follow-up question that I just said. So what is the interquartile range there? 13.5, and the interquartile range here is 23. So the coach B varies more. He says that coach A vary more. No, they don't vary more. Higher IQ are on coach B. Agreed? Anything more to add?
Nah.
On that question? Okay, the volume of sphere Q is 50% more than the volume of sphere P. The volume of sphere R is 50% more than that. Ooh, interesting. So, Q is 1.5P, and R is 1.5Q, so 1.5 squared P, that's 2.25P. What does it want? A fraction. So P is R on 2.25. Now let's just sort that out. Easiest way I can see of doing it is that, then divide by 5. Oh geez, that's 45, is it? And then by 5 again. Oh yeah, we could have divided by 25. That's actually a lot easier. And then 4/9. 4/9. I wonder if that makes sense in the context of the question. 4/9 just doesn't feel right to me. No, it is, because it's 3 halves times 3 halves, which is 9 quarters, and then you invert it because it's P in terms of R. I've lost the R though, so it's 4/9 of R, isn't it? Yeah?
Yeah.
What I like about that question is that it's got nothing to do with spheres. This is just you can take any congruent solid and it would hold. I reckon a lot of people would jump in there with 4/3 pi r cubed and start messing around with that.
Yeah.
Given that n can be any integer, prove that n squared minus n is never an odd number.
Great question.
Yeah, I
Love these ones.
I love the proof questions on the GCSE. I'm so glad that that's something that's more prevalent now. I'm not going to do it by induction. I think that's a bit high powered.
Yeah.
So if n is, I'm going to do it by cases. If n is odd, then n minus 1 is even. Therefore, the product is even. And I suppose if we wanted to make that implicit, so we could say n minus 1 equals 2k. Therefore, n minus 1 equals 2kn, which is definitely even. If n is even, n minus 1 is odd. Actually doesn't matter because n now equals 2r for r an integer. And so n times n minus 1 is equal to 2r n minus 1, which is even because it's a multiple of 2. Obviously, induction is not something that's done at GCSE. I don't think there's another way of really doing that.
No.
And why does it specify n is bigger than 1? Because n, when n is 1, we get 0, don't we?
Yeah.
Which is an even number, so why is that a problem? It isn't a problem. Fine, whatever. Give the exact value of tan 30 to... you know, for all the things that I have memorized, this is not one of them. 30...
Really?
No, it just isn't. They've never stuck. So, which one is this? Don't tell me. So, it's the 2, 1, root 3, isn't it? So, tan 30... is 1 on root 3, and sine 60 is root 3 on 2, so it's a half. Yeah?
I think so.
Do you have those memorized?
Yeah, a lot of the first year Cambridge exams needed this stuff. So
Yeah, I think there was a time I knew them more fluently, but yeah. Just something that's never really stuck. Okay. The classic ice cream cone question. So the total volume is k pi. Work out the value of k. All right, fine. So the volume of the cone is it's a third pi r squared h. So it's a third of what the cylinder would be, is how I think of it. So a third pi times 3 squared times 10, and that's going to all boil down to 30 pi. And then the volume of the hemisphere, let's not forget it's a hemisphere, is 4/3 pi times 3 cubed, all over 2. Ugly way of writing it, but fine. So that we get some cancel. So that's 9. That's as well. So 18 pi. So therefore, k is equal to 48. That'll do. Combinations, love these. So each dial can be set to one of the numbers 1, 2, 3, 4, 5. The 3-digit number 553 is one way the dials can be set. Sure. Work out the number of different 3-digit numbers that can be set for the combination. Well, that's just 5 cubed, 125. How many possible 3-digit numbers have 3 different digits? 5. Oh, 3 different digits. Well, there's... Ooh, okay, alright, fine. 5 factorial then? But only the first 3, so 5 times 4 times 3? Feels right. Feels right, doesn't it? Yeah. There's 5 choices, then 4 choices, and then 3. And because we're looking at combinations and not permutations, we're not over counting here. So
No.
I think that's fine with 60. Yeah. It's 5 factorial onto the order of the alternating group of order 5 of on 5 objects.
Oh ho ho.
That's why I recognize 60. Okay, given that, you see what I mean about ratio? They love it.
Yeah.
I teach my students this trick, which is a get out of jail free card on all ratio questions. Is you just write it like that and you're done. So it's 2x squared minus 3x minus 5 is equal to 1. Equal to 0 once you take it all over. So right, wants me to factorize this then, I guess. Hopefully it'll factorize. We've got primes, which makes it easy. So we need minus 5 plus 1. Pretty sure that works. Yep. So x is 5 halves and x is minus 1. Nice.
Sweet.
Okay. So 3 root 3. And, 1 on root 3 to the power of 7. Well, I'm going to check that actually. That is definitely root 4, root 3, which is 2 root 3 years. Yeah, that's fine. So 1 on root 3 to the power of 6 is the same as 1 on 3 cubed, which is 1 on 27. So if we times it again, we just get 1 on 27 root 3, and it wants me to rationalize it, so I will. Root 3 on 81 then. Happy with that. That was an interesting question.
Is it? Yes, root 3 on 81, sorry.
Okay. Completing the square then. X minus 3 all squared minus 9 plus 1, which is x minus 3 all squared minus 8. So A is 3 and B is 8. And the reason I'm labouring over that is it is subtract B there, not plus B. So it is 8, not minus 8. Hence write down the coordinates of the turning point. So it turns at 3 minus 8. God, I'm completely amazed at how there's not been a single, maybe that spheres question might, and that power 7 question, you know, there's been nothing really in here. Okay, so, right, this looks a bit more meaty, but again, usually these questions, you can just, you know, use your common sense. So Fine, given that H... Okay, so the whole system has a common... Fine, let's just do it. I thought there might be a clever way, but I don't think there is. And then therefore P is equal to L root T, let's say. And then we're just given all the information, so we can just substitute in. So H is 10 when P is 6, so K is 60. And P is 6 when T is 144, so that's 12, so that's over 12, that's L is 1/2. Okay, and we want H in terms of T. So H is equal to 60 over half root T. In other words, 120 over root T. Yeah?
Mm-hmm.
And that makes sense because root 144 is 12. 120 divided by 12 is 10 when H is 10. So a little check there. Okay, the functions are as such. So f inverse of x is x plus 1 over 3. Given that, okay, so let's work out these composites. So f of x squared plus 4 is equal to 3x squared plus 4 subtract 1. Gf of x, and we'll throw the 2 in there as well, why not? That's 2g of 3x minus 1. This is the more awkward case because we are now going to have to square that. So it's 3x minus 1 all squared. Man, my nerves, honestly. 9x squared minus 6x plus 1 plus 4 on the end. That's 18x squared. Subtract 12x plus 2 is plus 6. Let's expand this one out as well. So 3x squared plus 12 minus 1 is plus 11. Okay, given that these are equal to each other, we've got 18x squared minus 12x plus 6 is equal to 3x squared plus 1. Take that, we get 15x squared minus 12x plus 5. Ooh, plus 5. All right. So we've made an error somewhere. Oh, 11. Sorry. Yeah, subtract 5. I knew that was gonna when I did that. So as required, as we like to say. Okay.
Isn't it supposed to be subtract 1?
Oh. Yes.
I'm not seeing it. Gosh.
Yes, it is. Okay, happy with that. It's 3. Got it. So it is actually 2 of this entire thing. So it's... you know what?
Yeah.
I even had that moment where I got my brackets muddled up here. And
Yeah.
in my head I was like, that'll be fine. I'll fix that. So this is actually plus... so when we expand out that whole thing, plus 2 plus 8. So that is actually 10, which when we subtract is minus 1.
Yeah.
I'm sure everybody viewing spotted that mistake as well. So thanks for pointing that out. Okay, there are only R red counters and G green counters in a bag. A counter is taken at random from the bag. The probability that the counter is green is 3/7. The counter is put back in the bag. 2 more red counters and 3 more green counters are put in the bag. Oh, wow. A counter is taken at random from the bag. The probability that the counter is green is 6/13. Wow. Okay, so what do we know? We know that G over R plus G is 3/7. That's the probability of choosing a green token. Then we know that the probability of the counter being green when we have R plus 2, but there's plus 3 here, plus G plus 3 is equal to 6/13. I think that's how I'm going to do it. That should work. So 7G is equal to 3R plus 3G. In other words, 4G is equal to 3R. This is a simultaneous equations question in disguise. 13G plus 39 is equal, let's make that 5. So it's 30 plus 6R plus 6G. Okay, and let's tidy up. We get 9. We get 7G minus 6R plus 9 equals 0. Let's do 8G is equal to 6R, so therefore 7G minus 8G plus 9 is equal to 0. This smells like G equals 9. Let's just sort that out. Minus G plus 9 is equal to, G is equal to 9. And therefore, 4 times 9 is equal to 3R, which means R is equal to 12. R is 12, G is 9. Great question. Now that's what I'm looking for. And we're done. So, all in all, fairly straightforward there. That's quite surprising actually, because I trump up the GCSE quite often and say like just how difficult it is. And if you're a GCSE student, sure, some of those questions in there are going to be quite challenging, but there's usually a few more questions in there where I'm like, wow, they expect 16-year-olds to do that, Whereas in that one, I don't know, there wasn't that many moments where I was like, what are we doing here? Okay, so one down. Any other comments on that paper, James?
No. Well, apart from where are my circle theorems, but that's my only thought on that. And just to say as well, thanks very much to your dad for his donation. Good to see you.
Amazing. Yeah, make sure you point those out, because when I'm working on these papers, I'm not checking the screen there. So the old man, as I call him, thanks very much for joining, and thanks very much for your donation. Really, really appreciate it. Thank you. And look at that little event counter there. Okay, so I feel nice and warmed up now. I might do another GCSE paper. Let's see if we get anything more interesting in this one. So this is as above, but paper 2, which is calculator. What my students certainly prefer, but what I don't. Yeah, let's just power forward with another one of these.
My calculator at the ready. It's a Casio MX8B.
It is a Casio FX991ES actually. Oh, your calculator.
Yeah.
Right. Okay. So
you win.
You're gonna be checking along here. Well, I like this calculator. This has been with me since I did my GCSEs, I think. Oh no, since I did my A levels actually. Since I did my AS levels. Yeah, very good calculator. The newest calculator that we've got, so the ones that the students use now, they are really good, but they're so high powered now that we keep having to train students to how to underpower it. So like This iteration of calculator, this generation is the one that brought in the like it gives you the answer as a fraction, or it gives you the answer as a simplified surd and stuff like that. So you know, if the question is simplify root 80, you can just put it in. But if you just do that, then you get 0 marks because you've not shown any of your working. And then the next generation of calculator do even more than that. And it's actually becoming a bit of a problem for me as a teacher, because we keep having to, you know, to tell them you can't just use the calculator. And I'm like, I think the calculators have got too powerful for what they're actually needed for in an exam setting. Anyway, we've got an inequality here. So we've got 3n is bigger than 6. In other words, n is bigger than 2. So on the number line, show that. Wow, they never ask this. So -2 and solid blob at 4, because we want to include 4. Oh, I've not read the question properly. It's x plus 3. So it's -5 is less than x is less than or equal to 1. So let's do blob there and circle there and ignore those. Stupid. Right, okay. So
thank you, Jacob, for your donation.
Jacob, what a guy. He was one of my the people in my PhD group. Thanks very much for your donation, Jacob. Really, really appreciate it. And it would be nice to catch up soon, actually. I actually got no idea what... he must have finished his PhD by now, but... okay, so y is 2x minus 3. Okay, oh, it's an awkward scaling, isn't it? So it's actually going to be there. Because it's got a gradient of 2. So for every 1 we go along, we go 2 up. Yeah, I'm happy with that. Oh, and it only wants from -2 to 4. Close enough. It's fine. Hannah is planning a day trip for 195 students. She asks a sample of 30 students where they want to go. Okay, so she's asked 30, which... calculator time is that amount. So it's 0.15 of the theme park, so that's going to be 15. State any assumption you made. The sample generalizes to the whole population. Something like that. Come on, James, you're the stats aficionado.
So the sample is representative. It's the language I prefer.
Ah, shut up. All right. A container is in the shape of a cuboid. It's 2/3 full. A cup holds that. What is the greatest number of cups that can be completely filled with water from a container? Okay, so the volume is 30 by 6 by 19. And then we need to times it by 2/3. So that is in fact 20 times 6 by 19, which is 380 times 6. Why am I doing this when I've got a calculator sat next to me? So that is 2,280. And that divided by 275 is 8 and change. So 8 is the answer. Right-angled triangle. Calculate the length of AB. Okay. So give it a name. This is sine 38 is equal to, so 16 sine 38. Let me check them in degrees here. So yeah, degrees. X is 9.85 to 2 dp. Makes sense. It looks like it could be about 9. Sally used her calculator to work out the value of a number y. Complete the error interval for y. Ooh, that's interesting. That's an error interval that's based around truncation rather than rounding, isn't it? this would catch out a lot of students. So it could be that. It could be... okay, so anything less than 8.4, because as soon as you go below 8.4, it's 8.3 something. Yeah, happy with that. Interesting question. 360 is shared between 4 people conveniently named alphabetically. The ratio of the amount Abby gets to the ratio Ben gets is 2 to 7. Okay, and they each get 1.5 of Abby. So it's actually 2 to 7 to 3 to 3, really, isn't it? Work out the amount of money that Ben gets. Well, when you add these up, they add up to 15. 360 divided by 15. What's that? That's gonna be... wow, my brain is just so slow. 24, is it? 360 divided by... I'm trying not to use the calculator where I can because I need to just warm up a little bit. 24. So the amount of money that Ben gets will be 24 times 7, which is 168.
Yeah.
Yes, 168. 5.62 times 1, 2, 3, 10 to the minus 3. As an ordinary number, 1, 4, 5, 2, 1, 2, 3. It's just that. Fine. On a calculator paper as well. You could just type that into the calculator.
Yeah, you just got to check from Catherine on question 3. Actually, I just noticed it in the comments.
Oh. Oh dear. Oh dear.
Yeah, sorry. I know it's going backwards. Question 3 she wants to look at.
Okay. How many of the 195 students?
Yeah, I think she's right, actually.
So the sample is...
The sample's 30. 10 of them want to go to the theme park. Yeah.
Yes. Yes, of course. Oh yeah, massive. Yeah.
Thank you, Catherine.
Thanks so much. Yeah, honestly, that is a huge blunder. So it's a third of the people want to go to the theme park. So it's a third of 195, which is 65. All right. That is an embarrassment. Let's move on. Forget that ever happened. The circumference of circle B is 90% of the circumference of circle A. The ratio of the areas. Okay, now we're getting into it now. So, how best to set this out? So let's do RB 2 pi times the radius of B is 0.9 times 2 pi times the radius of A. Okay. Which means RB is just that. Which means the square will be that. So the ratio of the area of circle A, it'll be that, won't it? Or maybe the other way around. So area of A, area of B. I always confuse these. It's going to be 1 to 0.81. Yeah, because you need, for every one of these, the area of B is bigger, so you need more of them to equal the 1 of A. So I'm happy with that. Yeah. Square E has sides of length E. Square F has sides of length F. the area of square E is 44% greater than the area of square F. Work out the ratio E to F. Oh, so messy. So area of E is E squared, and that is equal to 1.44, which is nice because that's going to be a nice square, isn't it? Times F squared. So E is equal to, is this 1.2? Doesn't always behave the way you expect it to. Yeah, 1.2 F. So I'm going to do my trick again here to make sure I get them in the right order. E on F is 1.2 on 1. So E to F is 1.2 to 1.
Yeah.
Tree diagram. This, I tell you, until I was in my second year of university, tree diagrams were basically the only way I could ever understand probability. I just didn't get it at all. And I basically, every distribution that we did, I always still pictured it in terms of a tree diagram. Obviously your intuition on these sorts of things is better than mine, but it's just something I really struggled with.
Oh no, it's difficult. No, I think probability in general, the intuition is very hard, and I have to say I'm not sure my intuition of probability is actually that great.
Right. Okay.
But it is generally pretty difficult.
Yeah, but there's plenty of concepts in maths that I think are counterintuitive that kind of just come so naturally, whereas this I always, it just never never kind of folded nicely into my brain as nicely as other things. Work out the probability that her train will be late on at least one of the days. So we need 0.15 times, well actually we want everything apart from not late. So let's do that. Which is 0.2775. Yeah. That's right, isn't it? Cumulative frequency. Ugh, so boring. 35, 55.
Thank you, Ollie, for your donation, by the way.
Ollie, thanks so much. And thanks so much for tuning in. Really appreciate it. I love that I still say tuning in as if that is like in any way. I mean, I think tuning in was not even in my generation of TV. You know what I mean?
Yeah.
Question 2 is going to ask me to draw this, no doubt. Here we are. I'll try and show the table and the graph here. So we have got 0, 0. We've got 25. We've got 40, 35. We've got 60, 55. 80, 70. 178 and 120, 80. And as smoothly as we can get it, a nice S-curve. Use your graph to find an estimate for the percentage of these office workers who take more than 90 minutes to get to work. So let's be grown-ups and use rulers. So 90 minutes is there. So whoop, and we will go. I'll tell you something about this. Is I never used to want to draw these lines on the graph. I would just do it by eye, and my teacher would tell me again and again and again, Alex, you must draw the lines, otherwise the examiner doesn't know that you've used the graph. And I used to say, well, isn't it obvious that I've used the graph because it's just right there, you know? And he was right, because in the mark scheme it says if you don't see the lines, you don't get the marks. And now I am the teacher saying, please, I'm begging you, draw the lines. But you just don't want to do it. So that's on 74, isn't it? So the number of people is going to be 6, out of 80. So what's that as a percentage? 3/40. So it's going to be 7.5%. Let's check that. Yes, 7.5. Even as a statistician, that kind of question must bore you.
Yeah, I mean, to be honest, if I ever do need to do anything like that, I use the computer, right?
Yeah, exactly. Histograms, Okay, work out the perimeter of the sector, given that the area is 40. Okay, I can do that. So it's in degrees, so we've got to convert that out. So theta on 360 times pi 7 squared is equal to 40. So theta is equal to 40 times 360 divided by 49 pi. And then we will use that. So the perimeter is going to be 14 plus the arc here, which will be 14 plus theta on 360 times 2 pi lots of 7. So that's the question. Just need to put it in a calculator now. So 360 over 49 pi is that. So 14 plus theta over 360 times 2 pi times 7 is that. To 3 significant figures. 25. Does that make sense? Yeah, I mean, that's 7 and 7, that's 14. So we're saying that that's about 11. That looks like it's about 11, doesn't it? Sure. Why not?
Yeah.
Why not 11? Why not?
Why not? Yeah.
Okay, this looks like a meaty question. Bit of the old algebra. What is this? Further maths. Honestly, that paper last year killed me. So we are doing x plus 5 times x minus 1 over 3x. Okay, let's see if this factorizes first. Oof. Yeah, minus 2 plus 5, x minus 2, x plus 5. I'm glad I did that because we've got some cancellation here. So this is now 6, x minus 2 over x minus 2 plus x minus 1. So this is 6x plus x minus 12 minus 1 all over x minus 2, which is 7x minus 13 over x minus 2. All right.
On.
Good bit of algebra.
Yep.
Can't beat it. So a car moves from rest. I should hope so. The graph gives information about the speed, v meters per second, of the car t seconds after it starts to move. Calculate an estimate of the gradient of the graph at t equals 15. So, in the dark ages before calculus, this is how we would do it. And we have something. Let's go for that. Okay, where's my pen? So we've got, let's go from here. And we'll go all the way up to, can we see another nice coordinate? Yeah, let's just do the full thing. So it's changing y over changing x. Y increases from 6 to 25. That's not 6, 5, 6, 7 to 25. So it's 18. And x increases from 0 to, I'm going to do that one there. So 21, 22, 23, 24. 18 on 24. So that's 0.75, isn't it? Describe what happens. Describe what your answer to. That's the acceleration. An acceleration of 0.75 meters per second squared, I guess. Yeah?
Yep. Agreed.
Fine. Work out an estimate for the distance the car travels the first 20 seconds of its journey. Use 4 strips of equal width. You know what this reminds me of? This reminds me of the Trapezium Rule, which I can't stand it. So I'm begging those papers over there that the Trapezium Rule does not come up, because it is so boring. If you thought cumulative frequency was boring, you ain't seen nothing yet. So it wants us to use 4 strips of equal. Wow, this really is like a Trapezium Rule question. So here, here, and here. Does it want me to use trapezia?
I was wondering that.
I mean,
How many marks?
3. Let's just do it. All right. Don't fight it. Let's just. I mean, they do fit quite nicely as trapezia, don't they? This last one you could probably bodge as a rectangle, and this one obviously is going to be a triangle. This does feel like a lot of work for 3 marks. Can't see another way of doing it. You know what? Let's actually use the trapezium rule. So this is what is it? Height divided by 2 over the extreme values. So at 20 we've got 20 plus 2 of all the others. So it's 4 plus 12 plus, apologize that you can't really see the graph right now, about 16, 17, 18, I think. Yeah. And the height of each strip is 5, isn't it? So it's 5 over 2, 20 plus 2 of 34. So this 5, 10 plus 2 of 17. Oh, I mean, the easier way would have been to divide there. So 5 times 10 plus 8 for 44, which is 220. So 220 meters. Now, can we believe that after 20 seconds, it's gone that far? So after 20 seconds, it's doing 20 meters per second. Yeah, I think I can believe that, because that means...
Yeah. Show us the graph.
Yeah, I just like to always double check that my answer makes sense.
Yeah, I agree.
Yeah.
The way I often think about these ones is that at 10 seconds, it's like on average, it's going about 10 meters a second. So it's doing about 20 seconds at about 10 meters a second. So it feels okay.
Yeah.
How I think about these ones.
Yeah, I think that's right. 20 meters per second is actually quite fast, isn't it? So.
Yeah.
Okay, make M the subject of this. So, this is going to be M. What will it be? F minus 3 equals 4 minus F. So M is equal to 4 minus F over F minus 3. I think I'm happy enough with that. I'm not going to bother. Go on. I'm not trusting my algebra at the moment. So 4. Yeah, I'm glad that I checked this. That's 4 plus F is Fm minus 3m. So that's m F minus 3. Yeah. So when you whip it down, it's gonna. Yeah, it is that. Okay. Glad that I checked.
Yeah.
I'm usually better at that sort of thing. Okay. A point A has those coordinates. Find the equation of the straight line that is perpendicular to R and passes through A. So y is equal to 4/3 x plus 7/3. So the gradient of the perpendicular line will be that, and it passes through this. So y is equal to minus 3/4 of x. Okay, 9/4 plus 9/4 minus 5. So when we times by 4, we'll get 9 to minus 11 over 4. Yeah.
Yeah.
And does that make sense? So 3 minus 5 is about there. We are saying it passes through, what's 11 divided by 4? That's about 2.75, isn't it? So it's going to pass through here, and it's got a relatively shallow... I can believe that. I can believe it. There are some small cubes, and there are some large cubes in a bag. Have you ever seen a bag more interesting than this? The cubes are red, or the cubes are yellow. Okay. The ratio of the number of small cubes to the number of large cubes is 4 to 7. Explain why the least possible number of cubes in the bag is 88. Okay, well that equals 11, that equals 8. And the lowest common multiple of 11 and 8 is 88. So total must be 88k for some natural k. All the small cubes are yellow. Wow. M. Night Shyamalan wrote this question. What a twist. Work out the least possible number of large yellow cubes in the bag. Okay. So, I suppose least possible number of large yellow, that will come when there is actually 88 in the bag, isn't there? So that means we're looking at the ratio 33 to 55 for the number of red to yellow. And for this, we're looking at 32 to 56 for the small to large. Is it that all yellows are small, or all smalls are yellow? All smalls are yellow. So that means there's 32 of the 55 yellow cubes are the small ones, because these are all yellow, which means 23 must be the number of large yellow cubes. And that makes sense, because now we've got 33 large reds, which is the 33 reds, because there can't be any small reds. I don't know if that was the right way of doing that, but oh, here we go. Here are your circle theorems. It's my favorite as well.
Well, I always used to slag it off when I was a teacher. I was like, this is the most useless thing. It doesn't lead to anything. It's not useful for anything, but it is just a good piece of heritage, really.
Yeah, it is. And, you're speaking to a pure mathematician, so as soon as you tell me that it's not useful for anything, I don't care, My PhD was in group theory, which I'm pretty sure will have an application somewhere, but I've told you this story, but when I asked my supervisor, like, where do you think the first big use for this will be? And his answer was, well, actually, the results that we're using here are used in the theory of groups. So I'm like, okay, so it's just a self-propagating subject. Okay, anyway, let's stop messing about. What do we want? We want the angle ADE. So we want that one. Well, this must be 70. This must be 70. Cyclic quadrilateral. This must be 110. which means this one must be 35, which means that is 105, which means that is 75. I think I'm happy with that.
Yep. Cyclic quadrilateral, yeah.
Cyclic
Absolutely.
quadrilateral. Yeah, I mean, there's a little check. We could do that. That's 35, which means that is 75. And by the alternate angle theorem, we should have that this angle here is equal to. It's going to go. Oh no, we can't actually use that there because there isn't. Well, we should be able to. Oh no, it's not a tangent. What on earth am I talking about?
Yes.
Yeah. So, well, that is 75. I just recognised that was the same, and I thought, is that a coincidence? It won't be a coincidence because it's in a circle, so there's lots going on in it. But that at least should be equal when we add it to that to 180. So 70 plus 75 plus 30. Yeah. Okay. So we're pretty happy with that. I do love circle theorems. Absolutely love them.
Don't forget your degree sign on your 75.
Thank you for that. Right. So the base is a square, even though it doesn't look like it. Angle ABE and angle CBE are right angles. Okay. EAB is 35. M is the point on DA such that DA to MA is 2 to 3. Okay, so that is breaking it up into a 10 and a... Oh no. So... Sorry, it's breaking it here, isn't it? Breaking it up into a 6 and a 9. Calculate the size of the angle between EM and the base of the prism. So, we are looking for this angle here. Let's give it a name. We'll call it theta. Right, okay, finally got to the root of this question. Okay, so what we want is a bit of Pythagoras to work out MB. So MB is equal to the square root of 15 squared plus 9 squared. Don't think that's nice. Equals 3 root 34. So that's there. So the triangle I'm actually really interested in is this one, which is MBE. We've just worked out 3 root 34. Now we can use this triangle here. So we know, let's call that x. We know that tan 35 is equal to, so x is 15 tan 35. That's about 10.5. So we've got 10.5. And now we know that tan theta is equal to 10.5 over 3 root 34. So arctan of that over 3 root 34 equals 30.98, which to one decimal place is 31 degrees. Even remember the degree sign this time. And that makes sense because the further you pull that point there, the more acute that angle is going to get. So I expect it to be similar to, but slightly less than 35 degrees. So I'm happy with that. Okay. Final question. Led through the paper there. So, a vectors question. Here we go. express Fe in terms of A and or B. Right, okay. Usually it gives you all this information on the diagram, so that's annoying. DE all the way down is vector B, and FC we're given is A minus B. Right. I think what it's trying to say is that this is like an isosceles trapezium. If that's minus B, perhaps. Yeah, because if you go minus B, yeah, it must be the same length there. That might be useful, I don't know. So FE, well, FE is simply that plus that plus that. So that is just 2A. X is the midpoint of D. Sorry, M is the midpoint of D, fine. X is the point on Fm such that Fx to Xm is n to 1. And we know that CXE is a straight line. Yeesh. Right, okay, so the way I approach these questions is never the way that you are quote-unquote meant to do it. So we know CXE is a straight line, so therefore CX must be some scalar amount of CE. And we know CE to be A plus B. Now, what else do we know? We know that Fx must be some scalar amount of Fm. And we know Fm, it's A minus B plus A plus half of B. That's mu 2A minus half B. Now, what's the point? The point is, what we want to do, we've got that, and we've got that. So if I do Cx, another way to get from F to X is to go A minus B plus mu of A plus B. So I'm basically doing that and then plus Cx. And the point is, we've got Fx in two different ways here. So we can do A minus B plus lambda of A plus B is equal to mu of 2A minus half of B, and see what happens. So we've got how much A have we got over here? We've got 1 plus lambda of it. And how much B have we got? We've got minus 1 plus lambda of it. How much A have we got here? We've got 2 mu of it. And how much B have we got? We've got minus a half of mu of it. Okay, so this is telling us that 1 plus lambda is equal to 2 mu, and it is telling us that minus 1 plus lambda is equal to minus 1/2 of mu. Okay. So lambda is minus 1/2 of mu plus 1. So that is 2 times everything through by 2. I get 4 minus mu is equal to 4 mu. Mu is equal to 4/5. Yep. And now, since 1 plus lambda is equal to 8/5 now. We know that lambda is equal to 3/5. Okay, now, fine. What was the point in all of that? Well, the point was we have a ratio n to 1 here, and we've just worked out that mu, we could have stopped here, I guess. So we know that if we take this length here and scale it down by 4/5, then we land on x. So in other words, n is 4, because there's 5 total parts. You take 4 of them, so n is 4. Whew.
Blimey, Riley.
What would
I
you
always hate. I don't know what I would have done, to be honest. I mean, but is that really what the kid? Is that what the kids are supposed to do? I mean, that is.
So, I've actually I've got to admit to this. When I look at the mark schemes for questions like this, I don't know what they're on about, because they omit a lot of steps, and they I don't know, they're just written in a way that, like, there's obviously some method to this that I just don't know. But I mean, this makes sense, right? You know, you're basically you all the information that you've got is that x lies on those two lines. So the only way to get x is to use the fact that it lies on those two lines, because these are just vectors in the abstract. So you know, to get x rooted in place, you need to attack it from those two lines. Yeah, you know, it's this is always the approach that I take, and I don't think it is the quote unquote the proper way, but you know, it works, so it's fine.
It works, yeah.
I mean, it's not easy. That question, that's a good question, because that's like that's your differentiator, isn't it? You know, that's your grade 9 versus your grade 8.
Yeah.
But okay, so an hour and 20 minutes in and 2 papers done. That's not bad.
Good stuff. And I'm chatting a lot, so sorry about that.
No,
but
no, not at all.
I'll just say we have with us Emily Haythorne-Thwaite. Good northern name.
She's changed that name recently, actually, but I don't know.
Oh, okay.
I don't know if it's actually gone through. Yeah. Hi, Emily. Thanks for joining us. Love your comment there. What is the point? I ask myself that question all the time. Fortunately, I'm a pure mathematician, and I don't care what the point is. Maths is all good, regardless of the point. Okay, so I'll tell you what we'll do. Let's start. We'll go back to our key stage 1, and we're gonna go for a full run through from key stage 1 all the way up to degree level, and see how the maths evolves. I will be back in just a minute. So yeah, just keep the video warm for me. I'll be back in a second.
All right, see you later on. All right, folks. You know the drill. Like, comment, and subscribe. Keep those donations coming in for Refuge, please, as well. Yeah, so I think Alex has just said we are going to do, after this, we're going to go all the way through. We're going to do an accelerated tour through the British mathematical educational system, because we're going to do a little Key Stage 1 paper, which is Year 2's. So that is your... actually, how old are they? 7-year-olds, 8-year-olds? And then we're gonna do Key Stage 3, which is Key Stage 3 paper, which is your 11-year-olds. Key Stage 3 paper, which is Year 9's. So I guess they're 14 or something. And then we'll do a couple more GCSEs, and then we're gonna do some A-level papers. And I think we are going to finish off with one first-year degree level paper. And I believe that this year we're going to tackle a sets, numbers, and functions paper. So that is kind of the start of pure maths in the undergraduate context. So, and I imagine by the time we get to that point, it'll be, I should think 6 or 7 o'clock, something like that. So yeah, that's the plan for the rest of today. Still thinking about those ratio questions, you know, because I think that's, these papers, it's interesting how they've changed over the last 10 years. So I think, certainly they were getting wordier and wordier and wordier, and that seems to have gone away again. We're not getting those really long word problems that we were getting in 2015, and I think that's a good thing, because they were really just testing reading comprehension more than anything. But what we seem to have instead now is all these questions about ratio. Um, I don't really know why. I do know they're quite fiddly. It's interesting. I mean, it almost goes back to like the Piaget days. So for those people who are connoisseurs of educational theory, there's a guy called Piaget, and he was a big cheese in educational theory. I think in the sort of 50s, 60s, 70s. And his idea was that there were sort of particular kind of concepts that you could only, the way the brain develops, there's particular concepts that you can only grasp once you reach a certain age. And so, for example, he kind of thought that, before kind of primary school age, children's brains are not developed enough to kind of understand area. And ratio is one of these other things. I think that's one of his differentiators between sort of primary aged and secondary aged children, was ratio. But it's quite an old-fashioned theory now, so it's kind of interesting to see this come around again. I mean, one of the things when you look back at what he did, very often he was really studying one or two children and coming up with these ideas, which obviously is not how we do it these days. We want our big randomized controlled trials with a big sample size. But anyway, it's interesting. But yeah. Ollie, I'm interested to know whether that's how you would have done that vectors question if you're still watching. Because I don't know how I would have done that. Probably a quite similar way to how Alex did it, forming up the simultaneous equations like that. But that seems quite challenging, just to say, okay, I'm going to form up some simultaneous equations and here we go. But I can't really think of a clever way of doing it. And I should say as well, for those people who are going to be following us as we get further into the 24 hours, we're doing it a little bit differently this year. We're going to cut the video into 3 parts. So we will be hopping over to a different link after about 8 hours.
Hello.
And hello. I was just explaining to people that we are going to cut the video at 8 hours so that because YouTube can't save videos that are more than 8 hours. So
Yeah,
there will be
it's actually more than 12 hours, but I don't want to take any chances.
any risks. Yeah.
Plus,
So I'm just saying, just explain to people if they come back later on, they will potentially have to click a different link, but it will be there it's in the link, it's in the description of this video, and we also have it on the Tiltify page, I'm sure.
Yeah, I'm going to edit the Tiltify page so that it goes to the part 2. But yeah, thanks for reminding me about that because yeah, it's a bit awkward, isn't it? Like, I don't know, I feel like 24-hour streams are quite a common thing now, that I think they should just up the limit of, it's not like they're running out of server space, is it?
No, it's not like they're running out of server space.
So,
Hard drives are cheap. So I can see a couple of people have just joined us, so welcome. Do give us some encouragement in the chat. We're just about to go through the whole British school system from Key Stage 1, 7, 8-year-olds, all the way up to... Are we going to finish this one with a degree paper?
yeah, we're going to go up to degree level.
We're going to go all the way up to degree. So this is a really good bit. So, say hi, give us a wave, and here we go, I guess.
Here we go. I'll just update the paper there. So where are we? So this is a SATS paper. We've got what's the delay like, by the way, the latency? Is it working all right?
Yeah, it's like about 5 seconds, I think.
All right, that's fine. So yeah, because I appreciated when I was going through that last one, I was thinking James probably can't even see the question that I'm on yet. when I was like talking through one of the questions.
Yeah.
Okay, so key stage 1, that is what we call the first 3 years of compulsory education in the UK. Actually, the first year it isn't actually compulsory, is it, reception? But let's not count that. So year 2. So children of age 6 to 7 will be sitting this paper. This is one of 3 papers around mathematics. This is a reasoning paper. Now, a confession to make, I actually won't be able to answer the first few questions here. Not because they are too challenging, but because they're actually, you actually listened to the questions and answer them. They're kind of an audio questions, and I don't have access to that audio. So, for example, these practice questions, I guess that's 7. But questions like this, for example, I don't know what the question is, so unfortunately we're going to have to just skip a few of them. And I think we'll start with this one here, with question 6. So this is the start of the journey through mathematics that a child will embark upon. We're gonna see mostly arithmetic in here. We might see some shapes, like names of shapes. We might see some just generally this kind of contextual stuff where it's not so much mathematics. It's just a bit of the kind of I don't even know what you would call it. What we would call common sense, even though that's a term I really dislike. A lot of what we call common sense had to be trained at some stage, and it doesn't always come as naturally to everybody. So and I also think a lot what we'll see here is just around vocabulary. Do people know what least full and most full actually mean? There's a lot of like vocabulary in here that we kind of take for granted that a 6-year-old might not. So it should be interesting. I remember I did this last year, and I was floored by some of the questions that came up in the Key Stage 1 and Key Stage 2. So, and famously got one of them wrong. So we'll see how that goes. Okay, well, here's your Piaget question, isn't it? This.
Yeah.
You love this stuff, don't you?
Yeah.
So D, then C, then A. Nice measuring cylinders there. Oh, and that was the question. Okay, so Abdul has 9 shells. Amy has 3 more. So even now, it's just attacking your conceptual of 3 more. And I still meet students who are caught out by even things like, obviously not in a context as straightforward as this, but the idea of, she doesn't have 3, she has 3 more. Just that language, it can still be difficult. Okay, so £1 is more, £2 is less, £10 is less, 50p is more.
Ew, it's an interesting question.
What, just like knowledge of British coins?
Yeah.
Yeah, well, especially in the world of contactless payment, it should show 4 credit cards and ask which one has the highest credit limit or something. On these cards, the word should match the number, but that one doesn't. Fine. Ben makes a tally chart of his toys. So he's got 3 dinosaurs, it's one of these. He's got 2 dice. He's got 6 footballs. It must be that one. Okay. If any of you out there have children, I don't, and I've only spent very limited time in primary school because I'm a secondary school teacher. But just think about what your child was like when they were 6, or if you have a child that's near that age, what do you think they would be able to do? How to interpret questions like this. What I find fascinating is just the speed of acquisition. Kids go from in a quite a short space of time, not talking at all, to making noises, to speaking words, in a matter of, a blink of an eye, really, in the course of a lifetime. And then we're now asking them to answer questions like this, where they're having to use the language that they've just got their heads around and then apply it in this mathematical way. I think it's quite hard. I don't know. Okay, square has sides of equal length. I agree with that. It does not have curved sides. It does have lines of symmetry. Again, that vocab, line of symmetry. I remember when I was in year 2, it's always hard for me to comment on stuff like that because I was always good at maths, but like I don't know. I do remember.
I think they're looking for them to look at the ones that are wrong, honestly.
Probably, yeah. That's another approach that you can take.
But you have to be quite canny to do that. I mean, that's...
Yeah, exactly, yeah. Write 2 numbers to make the calculation correct. I would love to write 19 plus 0 here as a mathematician. That's the mathematician's answer, isn't it? But
yes.
But I'm gonna not do that. Toy cars, half of them, and has 4 left. Must have started with 8. Okay. Now, I'm spending so much more time on these coins questions than I did last time because I'm not making another error, but I'm pretty sure it's 93. So again, more coins. Write the number in the box. Okay, 45 out of 50. Well, 55. I'd say 58 for that one. Which shape has exactly 5 faces? So that's, again, that's not obvious, is it? And there's always debate among maths teachers as to whether a curved surface constitutes a face, which I would say, no. But, I don't know. Kemi and Ben share these pencils equally. Okay, well, there's 10, 20, 30, 50, 70. So I would have expected that to be an even multiple of 10, that total. So let me add them up again. 30, 40, 50. Yeah, it is 70. So they get 35 each. Well, I suppose what this question really, one person gets that, 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 one person gets that. So actually, you're only having to do 20 plus 10 plus 5, rather than 70 divided by 2. So, what we call the burden of knowledge. Once you reach a certain stage of your understanding, it's sometimes hard to dial back and appreciate how less capable or younger people might approach the question. 6 bags of apples. So that's just a times tables question. We want them to start acquiring their times tables at that stage, I guess. 21 counters all together. 14 in one hand, 7 in the other hand. So again, that is a times tables question because they're all multiples of 7. So the big thing for me in this stage is it's times tables and what we call number bonds. So
I think that's a number bonds question. I don't think they're looking for times tables there. I think that's a number bonds question.
It's the fact that it's that's probably true. So for those who don't know, a number bond, so usually you think about your number bond to 10. If I say 4 to you, you can say 6, and you know that what we call the complement, that is the number that you have to add to 4 to get to 10. And if I say 8, you know instinctively that 2 is what you need to add to make 10. And these are memorized, they're like firmly embedded in your long-term memory, and proficiency with those kind of bonds just improves, broadly speaking, your arithmetic. Okay, we have a triangle, we have a pentagon, and we have an octagon. The Pentagon in America, the big building, originally supposed to be an octagon, but the contractor kept cutting corners. Okay, maybe only I find that funny. So
Oh, no, I'm laughing.
three.
I think Discord was like suppressing my laughter there, but I was laughing.
Okay, yeah. So Discord doesn't pick up on the pity laugh, does it not? Three different fruits for £1. So those ones. Tick. Why am I drawing circles? What a strange thing to do. This turtle is rotated clockwise. That is a quarter turn. So I like this question. This is obviously the fact that clockwise is there is irrelevant. You know that even if you didn't know your clock directions, you could work out that that's a quarter turn. But what this is really getting at is angles. So the big mistake when learning or when teaching angles is to talk about the size of angles, and it leads to all these sorts of misconceptions like this. If I do two angles here, which angle is bigger? They like to say that one, whereas actually, if you draw it precisely, they are both the same angle. And it's because angle is a measure of turn rather than anything else. And I think this is just kind of planting the seeds that we are doing a quarter turn here, and then the next step is to introduce that a right angle is a quarter turn, because angles they can be surprisingly hard to a lot of students, and I think if they're not taught in the right way from the start, it can lead to a lot of the difficulties that they have. So it's how much you are turning. So I think that's what that question is really trying to get there.
But it's interesting because at that age, then they won't be that secure with the fractions. So it's almost I think it's almost like a piece of isolated vocabulary, quarter turn and half turn.
Yeah, well, I think they might not be secure on fractions in the kind of it means 1 divided by 4, that sort of sense. But I think, yeah, there's that colloquial. They probably know what half of a cake is or a quarter of a cake.
Yeah.
So it's like that. And yes, they are the same thing, but you know.
Yeah.
Now.
And in the old days, you'd have quarter past 12 and all that kind of thing. But
Yeah, exactly. Yeah.
Sorry.
So now I really, really like this question. So this is an associativity question. This is saying that the order in which numbers are added does not matter with addition. This is a kind of disguising the rules of additive arithmetic in this question. So we compare these up like that, I guess. I love that kind of stuff. More of this, please. One length of a swimming pool is 10 meters. Abdul swims the length of the pool 4 times. Now, again, this is a great question. I love stuff like this. So it's getting you to think about, what does adding mean? What does multiplication mean?
Great question.
Maybe the distractors could be better, but I like this kind of stuff. There needs to be more of that. Okay, some shading. So here are fractions. So I'm gonna not do anything fancy here. I'm just gonna shade like that. 3/4. That'll do.
Thank you, Lynn, for your donation. Much appreciated. Hope you're enjoying the maths.
Thanks very much. Always appreciated. Thanks so much. And a third here. A variety of different answers there, of course. But let's not go crazy. Okay, so Again, it's more arithmetic, but it's arithmetic wrapped up in words. In the trade, we call these worded questions because the arithmetic that we have to do here is not particularly hard. I suppose there's a few different ways you could do it. You could do 40 subtract 17 and then subtract 10, or in the other order, or you could add them and then subtract as a whole. Go on, let's show our working. Let's do it the way a child might be expected to do it. So something like that, or they might do 40 take 17 is that, and then 23 take away 10, which they might just know is 13. Okay, here are some signs. Well, clearly that's bigger, and they are the same. See, again, I like questions like this. This again, this is basically a repeat of the question that we had before. Interestingly, that it's only 1 mark, so I don't know whether I'm doing too much work here. We know it's 47, but I guess what else might it be trying to ask? It's the difference between the numbers, isn't it? And kind of trying to drill down on that subtraction is the same as finding the difference. Oh, here you go. Here's your old-fashioned, as you put it, your old-fashioned time. It's not old-fashioned now, is it? That one. End of test. All right. Well, that wasn't too bad. That wasn't too bad. Did you spot
Really
any,
nice.
spot any arithmetic mistakes there?
Nope.
Right. So that means either they were all right or that we're both wrong. So fine. Key stage 2 then. So 4 years later, let's see the difference. What should happen 4 years after these questions? What are we expecting to see here? More times tables. I think there's going to be a huge emphasis on times tables. This is my prediction. I think there's going to be just a lot of like what's 3 times 7 and that kind of thing, and it's going to be wrapped up in words. We'll get some formal methods. We'll get some formal addition, formal subtraction, formal 4 operations as a whole. We might get a bit of directed number, but only in the context of temperature. We might get some more shape names, area, perimeter, that sort of thing. That's what I'm expecting to see. Again, it's all arithmetic. Even area and perimeter, it's all arithmetic. Just wrapped up in all sorts of different contexts. We might, much to my dismay, we might see some very early algebra here.
Oh no, that's not right.
No, it really isn't. But we'll see. We will see. I'll explain more about why I am disappointed by that when I get to it.
Overlay.
Say it again. Sorry.
Are you updating the overlay? I don't know whether you're going to do it.
Oh
Okay.
yes. Thank you.
Yeah.
Thank you. You said
No
a
worries.
word that I knew the meaning of, but my brain wouldn't find the definition of overlay. Yeah, let's keep that going. So, key stage 2, and what is this? I did a random number generator to figure out which exams to pull from here. So this was the 2019 paper. Yeah, thanks for reminding me about that. You're going to have to keep reminding me about that.
Yeah, no worries.
So again, so exactly what I said, times tables, just wrapped up in some context.
Bloody Sudoku, that.
Yeah, pretty much. Yeah, and this kind of place value reasoning. So place value, I'm sure you all remember from school, it's the notion that the position of the numbers has a bearing on how big it is, which it took civilization quite a long time to really, pin down what we actually want from our number system. And it's ingenious, really, and we take it for granted so much. But it's so just by changing where that 9 is, we change its value. So we're recognizing it's in the thousands column. So 1,000 left. We need 1 less 1,000, so it's only 8 thousands. I've probably talked for far too much about that question, so let's move on. Okay, biggest of those looks like that one, and then clearly that one, and then so this one is the third biggest, and then that one. So up to a million, I think, is usually the key stage 2. We got a million and something, so I think we're getting into the millions. In year 7, the job is usually then to extend it to the billions, but a lot of kids already know about billions. I've noticed, you know, they're quite happy with that. Reflects the shape in the mirror line. Use a ruler. Don't tell me what to do. I don't want to use a ruler. So let's just do that. Now, if I had to pick one thing that I still struggle to teach, it is stuff like this. The kind of thing where if you're good at it, you never need to be taught it. You know what I mean? Like, same with rotations. If you've got that kind of spatial reasoning, which I've noticed is often completely divorced from your mathematical ability.
Yes.
You know, there's kids who their maths is amazing, but their spatial reasoning is quite pants, and vice versa. You know, and it's quite extraordinary. Really. We think of them to be quite intertwined, but I just don't think they are. I am just purely lucky in the fact that I'm quite adept at both. You know, and I think it's, I don't know, important to be grateful for that, because, you know, I could have had a life where I just didn't wasn't able to do that as well. Okay, so sequences. So we're not looking at nth term here, we're just looking at pattern spotting, so that's fine.
3, 2, 5.
Oh, 3, 3, 5, yeah.
3, 3, 5, yeah.
There we go. There's the there's the mistake. Write the missing number to make this division correct. Okay, and again, it's another place value thing. You know, 3/10, a tenth of a tenth is 100th. So 3/10 divide by 10, we get 3/100. Jack pours some dark paint, mysterious dark paint, into a container. What color is that? Dark. What a strange thing to say. In liters. Oh, this is a nice little question, isn't it? So each tick is going to be 250. So big tick, that's 500. That'll be 2.5 liters. Okay, so a bit of reasoning there. A bit of, yeah. Okay. So sometimes this is in the context of a what we call a function machine or a number machine. Again, just this kind of sequence generation. You know, when you're doing the grown-up sort of thing, you're doing like nth term and things like that. We'll see plenty of that in the A level, I suspect, the arithmetic and geometric progressions and stuff like that. But for now, it's just getting us into the idea that we can have a list of numbers that have a rule in order to generate the list. So we're going to multiply by 2 and add 3. And then to go the other way, we will subtract 3 and half. So that'll do. Again, it's just times tables city, isn't it? You know? Oh, this looks like a formal methods question. So he chose a number. He multiplied it by 7. He then added, so we need to do 953, subtract 85, and then divide by 7. That's what we need to do there, isn't it? So that's 948, that's 968. Oof, does that divide by, I mean, it must divide by 7. That's 910 plus 58. That isn't divisible by 7. Oh, because it's 868, you idiot. Man, I'm really rusty today, aren't I? So that's 840 plus 28. So when we divide by 7, we get 4 plus 120, so 124. Obviously, it's wanting us to do this sort of way, which is so boring, but we'll do it to check our answer. 124. Okay, a theme park sells tickets online. Okay, each ticket costs £24. There's a £3 charge for buying the tickets. Okay, now this is the kind of algebra question that I don't mind coming up. So this is more of a reasoning around. So we need to be timesing by 24 and adding 3. So it's that one. So the next step in this is it will say form an equation or form an expression to give the total price of the tickets, and you would say let n be the number of tickets, and then it's 24n plus 3. So this is the step before that, where we're just getting them to think about how you would actually do an all-round calculation to calculate something the total like this. Wouldn't you say?
Yeah, absolutely. It's kind of a sad indictment on British life that we now have these questions where it's like, oh, the significance of the service charge, the transaction fee. Anyway, but never mind.
I knew as soon as I started that question, I thought James is going to make some stink around the fact that there's a £3 service charge. Okay, Amina, sometimes Amina, is shopping. She says, I would like to buy 1/4 of a kilogram of cheese. 0.25 kilograms. The cheese costs 1.35. She pays with a £2 coin. And I'll put the pound sign in there because sometimes they specify that you must include the pound sign, or you write it like this. Either or. But not both. So, 7/10 is bigger than 7/100. 23 thousandths is smaller than 23 tenths. Again, good stuff, isn't it? This, I suppose you could reason is that, and I suppose you could reason is, 1, 2, 3. Sorry, I'm going the wrong way there. 0.023, is it? 1, 2, 3. Yeah. So, clearly we've got smaller there and smaller here. Here is the sketch of a triangle. Use an angle measurer. Oh, I actually don't have an angle measurer, unfortunately, so I'm not sure. I might have to skip this question. Here is the sketch. What does it actually want me to do? It wants me to... Oh, it just wants me to draw the same thing again. Okay, so this is going to have to be a bit of a bodge, because I don't have my trusty angle measurer, unfortunately. So let's just do it as best we can here. So we're going to go for a parallel line. Yes, Emily, I know it's a bad excuse. A mathematician should have a angle measurer, but sadly I don't. Let's just go for that. Close enough, right? Okay, now how long is that? That is 75 millimeters, 76. So something like, and if we've done it right, it should drop straight down and give us a right angle. Which, wow, it really doesn't.
Yeah, I think that is not actually 35, right? That would make it too easy.
Ah, that's 6 centimeters. So we're actually scaling up. Whatever. Let's just draw the right angle in there and be done with it.
Yeah. I don't know how I feel now. No protractor, honestly. What kind of example are we setting here?
I know.
You'd be telling me you've forgotten your pen next.
I've got plenty of pens. No, Emily, I don't take my angle measurer on a night out. It's cheeky, isn't it? I do have a compass, so is there a Euclidean construction of 35 degrees that I could have done there? I don't think 35 can be constructed.
No, you would. I think the only thing you could have done is got the calculator out and use some trig. I think that's the best you could have done.
Yeah, but you know what? I'm happy not to do that on a Key Stage 2 question.
Yeah.
I can't believe I don't have a protractor. I never even thought about that. I got all my stuff together.
Listen, I'll get an Amazon Prime, and you'll have it by tomorrow morning.
By tomorrow morning, I'll go back and do this question. Okay, moving on to the nearest 10,000, to the nearest 1,000, to the nearest 100. Oops, 39,500. Fine. Amina, she's back, and she's now asking 60 children to choose their favourite flavour of jelly. What percentage chose orange? 25%. 15 out of the 60. Okay, so how might a child have done that? So 15 out of 60, would they know how to... yeah, I mean, my year 7s, when they first started, I think they knew how to simplify fractions, so they would boil that down to a quarter and recognise that that's 25%. I think that's how they would have done that. Yeah. Okay. Oh, and here we have a bidmass question, so we've got to make sure that that's in there. So 6 plus 4 subtract something is 6, which is 4. Don't make me draw anything. Oh no, it's calculate the area. So the length of each side of the hexagon is 8. They have the same perimeter. Ooh, okay. So the perimeter of the hexagon is 8 times 6. So that is the length of each side of the square. So the area will be that. So that's 2 times 6 all squared, which is 144. Again, a child would just do this in more steps, I guess. So they would do 8 times 6, which is, I don't even know, 48, and then divide it by 4, which is 12, and then, yeah, 144. Circle the prime number. Ooh, now, it's that one, isn't it? But they all, 95 is equal to 5 times 19, is it? Yeah. So that's not prime, and 87 is equal to 3 multiplied by 29, I think. So they are not prime, they are composite numbers. We can find 2 non-trivial integers at times to make them. 89 is prime because it doesn't have any proper factors.
So for this question, do you think if you wrote 95 is a multiple of 5 because it ends in a 5, and 87 is a multiple of 3 because 8 plus 7 is 15, they would give it you?
Yeah, I think they would give it to you even if you didn't write the thing about the digital sum. I think they would do... I think if you just stated that 87 is a multiple of 3, that's fine. This whole question is 1 mark.
1 mark, yeah.
So in this cloud here, they just want any old rubbish, just to indicate that they slightly know what they're doing.
Yeah.
They've not chosen the easiest numbers there, I would say. They could have been really mean and put 91 in there, because that is what I call the most prime looking non-prime below 100. Because it definitely, you look at that and it just screams prime number, but it actually isn't, because it's 7 times 13, which is the product of the 2 biggest primes you can get and still wind up below 100. So that's why it stinks of priminess, but just isn't. Okay, a machine pours 250 millimeters of juice every 4 seconds. Okay, so that's 16 seconds for 1 liter. So that means we want every minute. So that means in 64 seconds, it's doing 4 liters. So that means in 60 seconds, it's doing 3,750. That was a really weird way. I don't know why I did it like that. But obviously, the better way is how many 4 seconds are in 60 seconds. So it's 15, and then you can do 15 times 250. I think my way is easier. I don't know. Take the fractions that are equal to 20%. Now we definitely need more questions like this, because there are so many misconceptions already firmly embedded by the end of primary school around this. This here is the big no-no that a lot of them might want to say. especially in the context of an exam. Adam has this rectangular piece of card. Good for you, Adam. It is marked with grid lines. He makes 2 straight cuts along the grid lines. The 2 cuts divide the rectangle into 3 shapes. 2 squares of different size and 1 rectangle.
Wow.
So, I guess if we do big old square and then the rest becomes square and rectangle. Wow, yeah, if I had not spotted that, is there another option for that? Or is that the only option? I think that might be the only option, you know.
Yeah. With 2 cuts. Yeah.
Use a ruler. I'm not interested. So, yeah. What a weird question. That's like an IQ test kind of question, you know.
Yeah, I don't love that, to be honest.
Yeah. The graph shows the maximum temperature for 5 days. For what fraction of the 5 days was the maximum temperature below 10? 2/5 of them. What was the mean maximum temperature? Okay. A mean question. Oh, so it wants us to add them all together, does it? Oh boy. 11.9, 11.8, 12.4. Can't really think of a quick way to do this, so we're just going to have to do it the old-fashioned way. So that is going to be 4 plus 8 is 12, plus 9 is 21, plus 3 is 4, so that's 2.5. Now it ends in 0.5, that's good, because we're going to have to divide by 5 in the end. So fine. So we've got a 10, 20, 23, and 5. So 53.5. So let's go for the old bus stop. Decimal points at the ready. We've got 1, we've got 0, remainder 3, and we've got 7. 10.7. So where's 10.7 on here? It's about there, isn't it? Which I could say that's about the mean. That looks right to me.
Yep.
Okay, Amina, she's back. Not asking questions about jelly, but with a cuboid of centimeter cubes. Stefan makes a cuboid that is 5 centimeters longer, 5 centimeters taller, 5 centimeters wider. What is the difference between the number of cubes? Ooh,
Nice.
lovely, lovely. So, Amina, how many cubes you got? You got 3 times 6 times 4. Now I'm trying to just think. Is there a trick? I'm trying to picture it in my mind because I just don't think there's a neat way of actually getting at the answer because it's not been scaled up nicely, has it? 5 centimeters longer. You're going from 6 to 11, which is just, it's not a nice scaling. So I think the only way to do this is to just actually work out what these are. I'm sure there'll be some way of some trick to this. So
I don't think there's a trick, honestly.
8 times 11 times. No, you don't think so?
No, I don't think there's a trick.
No, there's no real relationship between any of these numbers. So let's just do it. 3 times 6 is 18, times 4 is 72. 8 times 11 is, oh, jeez. Okay, let's do it that way. Let's do the 8 times 9, that's 72. Times 11 is 792. So there is something here, isn't there? So there's 720 more cubes. So that answer seems so coincidentally nice that I feel as though there must have been a nicer way to do that. Nope, can't see it.
No, I can't see it. You know, it's not as though they've scaled it up or anything. It's just
Yeah. No, I think they've actually just deliberately chosen the numbers to be quite nice
yeah, I think so too.
because basically three times 6 times 4 is the same as 8 times 9. That's the only because you've got 3 times 2 times 3 times 4. 6 is the same as 2 times 3, and then when you do it like now you've got 2 times 4 is 8, 3 times 3 is 9. So you're basically doing the old thing times 11. That's where that 11 is coming from. But I think those numbers have been deliberately chosen in such a way. Anyway, and that's the end. And that's the end. So, last few questions. They're your differentiators, really, aren't they? You have to do quite a lot of multiplication in order to do that. And you have to do quite a lot of... Again, it's all arithmetic, but, quite hard to do in the time frame as well. Let's not forget, I think at Key Stage 2 they get less than an hour for this. So it's what questions can you ask that only the really bright kids are going to be able to get time to do, and answer well, to differentiate them. And then this was just bizarre, wasn't it? This kind of spatial reasoning question.
But we didn't get the algebra, did we?
No, we didn't. This is only paper 1. This is paper 2 of a total of 3 papers.
Okay.
So on the other, so paper 1 is usually like the number arithmetic paper. Paper 2 is like the reasoning paper, and paper 3 is another reasoning paper. So it could have been the case that the algebra was on the other paper. I don't like seeing algebra in the sets because they gloss over it so quickly and it's in such little detail that I think it's easier to teach kids who've never seen algebra before than to try and unpick the primary school stuff and say, actually, what we want to do is this, I think teaching a blank slate is sometimes easier than,
Yeah, definitely.
than a half-built slate. My metaphor has died a sorry death there, but moving on. So, Key Stage 3. So, this is an exam that Year 9 students used to take. So, these are students aged 13 and 14. So, halfway between what we call high school. Or this is like towards the end of middle school, I think, what the Americans would call it. So it's at that age, and we don't do this exam anymore, for better or for worse. I think most schools, they're going to do some kind of exam at end of year 9, but it's not one that's kind of formally assessed externally. So this is a kind of obsolete exam, but I think it's a nice middle ground between what we've just learned is at Key Stage 2, which is just very heavy on the arithmetic, and what we are going to see on the GCSE paper. So I expect we are going to see a boatload of algebra in this. We're going to see ratio. We're going to see the start of some trigonometry and some Pythagoras and that sort of thing. It's interesting that this isn't an exam anymore because there used to be, a specification for this. So you'd need all of your students by year 9 to be able to attack this paper. Whereas now, the freedom afforded by removing this exam means that different schools will have completely different schemes of work. They'll teach different things at different times. So, what we might teach at our school up to and including year 9 might be completely different to what a different school, we might introduce surds early, while some schools might introduce surds only much later on, and similarly with other topics as well. But so it was an interesting shift in the sphere. Well, that wasn't the only implication of removing this paper, but anyway, I've prattled on enough about that. So, anything else you predict might come up on here, James?
No, but the only thing I say about this, I think these papers are sadly missed, or at least by me, because I think they reward you actually thinking, whereas the GCSE papers often it's techniques.
Right.
Whereas with this stuff, they ask these papers are a lot less drillable, I think, than the GCSEs are, and I think there's quite a they stand in quite a contrast, really, particularly at that time. The other thing I would say about this, I just posted this in the chat. I think this is the paper that I sat in 2005 because I think I was 14 in 2005. And so the other thing I would say about this is that these are tiered. So this not everybody would have sat this. This is the most difficult one that we're looking at here.
Yeah, so just about to make that point. So, yeah, I agree with you. When we did our GCSEs on the drillableness of them, the GCSEs were so drillable and they were so boring and they were so bad and they were so easy. But since the GCSE overhaul, I think the GCSE tends to be a lot harder now. I mean, the papers that I did just before, the first two papers that I did today, you wouldn't tell that they'd become any harder because they were some like surprisingly easy papers, especially for EdXL, which is the exam board I'm using. Usually harder questions, but yeah, the GCSE now usually a bit harder. But yeah, I deliberately chose this. So last year when I did this marathon, 2005, this is the year that I sat. Are we the same age? I thought you were
No,
1 year older than me.
I am 1 year older than you.
So I think I sat this in. When would I have sat my year 9? Oh no.
2006. Right?
Yes.
So if you should have left secondary school in 2008.
Yeah, you're absolutely right. Wow,
Yeah.
that's some terrible maths from me. I thought I'd chosen this to be the paper that actually I sat, but yeah, I think this is the paper that you actually sat. So
That
yeah,
I would have done, yeah.
and you are right. There used to be 3 tiers. There used to be a higher, an intermediate, and a foundation. We used to use this leveling system. So level 5 is the highest level you could get coming out of Key Stage 2, and then the tiers for this, they were kind of leveled from level up to 5, level 5, 6, and then level 6 to 8. So this is the highest one, because it's the most interesting, the most challenging. Okay, so we may use calculators. So here we go, and we're given some formula there that we all know. So fine, let's do it. So each year there is a tennis competition in Australia and another one in France. So again, I'm going to try and get as far as I can without using the calculator. Although looking at this, I'm definitely going to need to use a calculator on this one, so forget that. So, in pounds then, we're going to do 1 million divided by 2.7. So over 2.7, so that's 370,370. That's a nice number. And we've got 780,000 divided by 1.54. Ugh. Already bored. I've got another 19 hours of how long? Oh, no, 20, 23, 22 hours or whatever it is. 506,493. So France paid more. Alright, a bit tedious to kick us off with, but okay. Okay, now I'm panicking every time I see some kind of scale drawing because I don't have an angle measurer, so... But it's an enlargement question, so that's fine. So, in fact, you could do this without a ruler, because that's going to expand out to there. It's going to be 4 across. It's going to be 8 down. So it's going to look something like that. I'll do. Okay, so here we come with the hefty algebra. About 2,000 years ago, a Greek mathematician worked out this formula to find the area of any triangle. Oh, love this.
I know, this is the kind of thing that they used to do. These are good questions,
So good. A triangle has these sides. Right. So it's just a substitution question, but it's got some flavour to it, hasn't it?
Yeah.
So let's do it. So 3 plus 5 plus 6 is what? 14. So S is going to be 7 in this case. So the area is going to be equal to 7 times 7 minus 3 times 7 minus 5 times 7 minus 6. So it's not going to be a nice number, is it? We've got 7 times 4 times 2 is 56. Whatever that is. 7.48. Yes. Do you know the Greek mathematician who worked that out?
Heron of Alexandria.
Was it?
It's what it says in the top right-hand corner of the page.
Of course. Nice. I thought that was Archimedes, actually. I thought that was an Archimedean thing, but maybe I'm thinking of... I think he did a triangle in a circle rule theorem.
Right, yes.
I think there's something like that. Could be totally wrong about that, so please correct me in the comments if you happen to know.
Thank you, Will Home, for your donation.
Thanks, Will. Really appreciate it. Thank you. Hope you are feeling okay. I think you were a little bit worse for wear last night, weren't you? Here is some information about all the pupils in class 9A. I love that they've nicknamed these questions, actually, now that you've pointed that out. This is the hands question. Okay, so teacher is going to choose a pupil at random. Probability of girl is 14 out of the total. What is the total? 14, 30? I'm not going to simplify, because usually probability don't want to simplify. What is the probability that the pupil chosen will be left-handed? That's 3 out of 30, or 10%. The teacher chooses a pupil at random. She tells the class the pupil is left-handed. The probability that the pupil is a boy will be 2/3. The screens of widescreen and standard televisions look different. Totally agree there. They have different proportions. Yes, they do. Oh, and they've actually used the actual aspect ratios common to widescreen and standard definition. Although I will say, in the opposite order, usually 4:3 is what you would call the aspect ratio of that. You would do the width to the height, actually. Kerry starts to draw scale drawings of the televisions. Oh, scale drawings? Are you joking? I've never seen so many scale drawings in my life. I mean, I've seen like 2 of them, but that's more than I've ever seen. So for each, the height is 4.5. Okay, so we need to do 6 for that. And okay, 4.5 divided by 9 is 0.5, so that one's going to be 8. Okay, a spinner. Okay, so there's more probability so far than what I would have expected, and not as much algebra as I would have expected. We've only really seen one algebra question. Wow, this is almost the same question that I answered on that GCSE paper before, isn't it? So they must be the same. So it's 0.3 for each of them, 0.15 each. I think of a number. I multiply this number by 8 and subtract 66. The result is twice the number of what I was thinking of. So 6n is equal to 66, n is equal to 11. Does that make sense? 88, yeah, 22, yeah, it's fine. Here is some information about A-levels. I'm sure there's usually a hyphen there, isn't there?
I don't know.
I don't know.
You tell me.
How many more students gain grade A in mathematics than in English? Right, so we need the actual 0.19 times 72,000. That's 13680. 0.37 times 54,000 is 19980. So the difference between them looks like it's going to be 63,000. But let me check. 19980 subtract 13680. 6300. Fine. The same caveat as last year, by the way, to anyone watching this. If you happen to be a student, please do not answer these papers in the way that I'm answering them. Show all of your working out. Listen to your teachers when they tell you that it's important. It's important for two reasons. You might get marks for your method. Sometimes you don't get marks for the answer, even if it's correct if you've shown no working. And if you've made a mistake, if you've shown your working, you can go back and correct. Much easier if you've shown all of your working out. I'm doing this for speed. You are doing it for your future, so please make sure you answer the questions properly. Just thought I'd add that caveat in there. Okay, is 17 a solution to the equation? Now, I like this question because I think sometimes students get far too wrapped up in playing the equation game that you forget that what you're actually trying to do is find a number that you can put in there and there that balances this whole thing. So I'm going to do it the substitution way. Oh, no, I'm not. I'm not, actually. Because, actually, it's clearly not going to be a solution because that's equal to 238. So, no. Right? The substitution way would be to do 14 17s, take 51, and that side is equal to 187. And then that is equal to 187 plus some stuff. So, no, it clearly cannot be a solution. Right, what about 3 of 17 squared then? What's 17 squared? Oh, I should know what 17 squared is. I think it's 289, but I need to check it. 117 squared, 289. And then times it by 3, so we are way off. What's the actual solution going to be to that? 17 root 3. Yeah.
They really wanted 17 to be a solution, but
no, 17 it's just not happening.
you're gonna have to continue their quest for an equation to which 17 is the solution.
Yeah.
Oh dear.
Like x plus 1 equals 18, I don't know. K squared plus 6k, 6k squared, 3k. Alright, there's the algebra that I was looking for. Oh, yeah. My days. Okay, here are 4 charts drawn by a computer. Go on then, James. Does R spit out milk bottle themed bar charts on command?
No.
It doesn't. Charts to show the average amount of milk produced by different breeds of cow. This is going to be a misleading data question, isn't it?
Yeah.
Because look at that. This is hideous. I feel sick just looking at that. So only one of these charts is a good way of showing the data. For each of the other 3 charts, explain why the type of chart is not a good way of showing the data. Okay, interesting question.
What a great question.
Kind of boring though, right?
No, I don't know. I don't think so.
Okay, chart 2 is bad. This is the milk bottles. This absolutely monstrosity of a graph here. Because, you know, the area of milk shapes increases disproportionately.
Yeah, I would say the area of the milk bottles is not proportional to the data.
Yeah.
It's interesting. You know, about 15 years ago, there's a guy called Kaiser Fung, and he's got a website called Chart Junk. And if you go all the way back to the beginning of that blog, it's many years ago now, it was filled with this kind of chart, really, in 3D charts, which is the other really criminal thing that you can do. But actually, in more recent times, the amount of that stuff has really dropped off. And even on TV news, which was always the worst culprit for these things, you see really sensible looking bar charts and stuff.
Yeah, it's funny that you say that actually, because when I taught a lesson on misleading statistics, I went for a bit of a Google around like the latest news. I actually couldn't find any bad graphs. I was like,
no, it's improved massively in recent years.
Yeah. But also on the GCSE, there's fewer questions like this now. They sometimes ask. I don't think they would ask a misleading graphs question, and they wouldn't ask. What is the other one? You know that God, it used to be like survey design.
Yes, survey design. Yes,
They don't ask that anymore. Which, if anything, has actually got worse as time. Maybe I'm just filling out more surveys nowadays than what I used to. But I find so often some like horrendous mistakes. I've got a friend who works in marketing, and we've got a running joke where we send each other these like badly designed surveys because. There's some like real, like it's terribly written and terribly designed ones. Anyway,
yes.
26
Don't
hours.
let me distract you.
He watched TV for the same length of time on those 4 days, and watched twice as long. Okay, so we've got 4x from Monday to Thursday. Each of those is worth 2x, so that's 6x, that's 26. So 1 unit of watching is 2.6, which means 2 units of watching is 5.2, which is 5 hours, and 0.2 of an hour, so a fifth of an hour, which is like 12 minutes, right? So 5 hours and 12 minutes. You need to take a break from that TV, Jamal. I'm going to be honest with you there.
Do some maths papers and stuff.
Do some maths papers for 20... Yeah, well, at least I'm not doing it for 26 hours. The nth term of a sequence is 3n plus 1. What is the 8th term of the sequence? 28. Yep, 28. The nth term of a different sequence is that. The first 3 terms... Okay, so when n is 1, we get minus 1 over 1, so minus 1. When n is 2, it dies. When n is 3, we get 1/9. A weird sequence, but there it is. Multiply out. That's very American, that, isn't it? Expand, we would say. And then k squared plus 5k plus 6. That's the worst looking 5 I've ever seen. That looks like a 6. That'll do. Finally some geometry. So the sizes of angles of H and J, where this is a parallelogram. Okay, so J, I'll do that one first. That's 120, because J and angle CBA are co-interior, therefore sum to 180. And H is 80 is alternate to there's no, let's put X there, angle BX. Come on, give me some letters to work with if you're going to ask me to explain my reasoning. A newspaper printed this information about the world's population. If the world was a village of 100 people, 6 people would have 59% of the total wealth. Boy,
those were the days.
I bet that's Jason's.
Yeah.
Oh, wow. The other 94 people would have the rest. On average, how many times as wealthy as one of the other 94 people would be one of these 6 people? Okay. So.
See, this is it, the heyday of the Blair era, 2005. Injecting propaganda right into the exams.
So that's 59 on 6. So this is I don't know if this is a good way of doing it actually. This is like 8.3. So a wealthy person has 9.83% of the total wealth, whereas the rest, I mean, we literally call them the 1%, and here we are with the 6% of them. The rest, 41 out of 94. That is 0.436%. So 9.83 over that will give us the answer. So they are 22.5 times more wealthy. Seems low. Seems low. I think that's right though.
Yeah.
I don't see anything wrong with that. Ooh, this looks tasty. So the diagram shows two circles and a square. Calculate the area of the shaded part of the square. Lovely stuff. So the area of the square will be, it's side length 10, isn't it? So 100. And then we need pi r squared over 4 times 2, which is going to be 25 pi on 2. So 100 minus that equals 60.7. I can believe that. I can reckon that's about 40% of the space in there.
Yep.
Units, I guess.
That would be nice.
The graph shows the heights of 150 fir trees. Okay, the price at different heights. Use this information to calculate the total price of the 150 fir trees. Oh, you know what this is? This is... Oh, no, it's not. It's fine.
No, yeah.
It's a cumulative frequency, so yeah. You know where I was going with that, don't you?
Yeah.
So,
something that you would never do in the 21st century.
So here, that's 25. They're in that bracket, and then we have awful graph paper. We've not included like the thick lines on certain increments. So I am actually going to have to bust out the ruler here. 1, 2, 3, 4, 5. Ish. There. Which, oh, I can't even see it now that I've marked it. That's, okay, so 5th of 25 and one below that, so it's 120. Subtract 25, so there's 100 in that bracket. So the remaining trees must be another 25 of them in there, right?
Yeah, Ollie's wanting you to check. I think he's like disputing your very first number, that 1.5. He's saying he thinks it's
Completely
20, not
correct.
20.
Yeah, thanks for that, Ollie. Yeah, it's that one there, isn't it? I thought it was, yeah. So, and that would actually change all of them. So we are going from 120. Oh no, that's still going to be. Oh god, what was it? That was 120 there, wasn't it? So minus 20. That is still weirdly 100. So I must have even made another mistake there. And now we've got 120. So there must be 30 here, right? And does that make sense? Yeah, of course it does. Okay, so 20 18s plus 100 22s plus 30 26s. So that's 360 plus 2200 plus 5278 780. So we've got 2980 plus 360 is 340. Don't trust myself at all. I'm going to do it all on the calculator. I'm really not in a... Weirdly, I am not in the mood to do 24 maths exams because usually I would just trust my instincts on that and just go with it. It was right. So, see, this is the kind of this is a good question, isn't it? So if it goes up,
oh, nice, yeah.
If it goes up by it's going to be, I reckon it's going to be 21%, but we'll see. So
Yeah, I think so.
yeah, and then we go to 1.1x. So it's x squared versus 1.1 squared x squared, which is 1.21, so a 21% increase. Yep. The length of a rectangle is increased by 20%. The width is decreased by 20%. By what percentage has the area changed? Let's do xy. Let's increase the width out to 1.2x, and let's decrease the width by 20% for 0.8y. So it's xy versus 0.8 times 1.2 xy. What is that? Like 0.96. So it's a 4% decrease. So minus 4%, I guess. By what percentage has the area changed? It's changed by 4%. So I'm happy with that. Yeah. Oh, so good.
Nice.
Yeah, because this is something that's missed. Like, you know, if you increase the radius, the radius and the circumference of a circle are directly proportional. So if you double one, you double the other, which is a counterintuitive result to many. You know, if you take a circle and you double the radius, if that's the diameter there, take two diameters, somehow that looks more than twice as long as that to me. But it is that. I don't know. Maybe to some people it does look more natural, but I don't know. So it's these kind
I agree with you.
These linear relationships. So the circumference plotted against diameter is d. It's a linear relationship. The area of the circle plotted against the radius, so that's a quadratic. So c. And the length of a rectangle of area 30 plotted against its width. So if you, that must be E, right? Yeah. If you increase the width.
Yeah, you double one, you got to half the other.
Yeah. Well, no. No. It's not going to be that. It's not going to be doubling and halving, is it?
Yeah, sure.
Or is it? Maybe you're right, because if you're right, it's B. So this is xy. This is always 30. If I increase to... yeah, of course you're right. If I increase to 2x, but I still need 30. And then I need ky here. Yeah, then I need...
0.51.
Yeah, exactly. Yeah, so it is actually B, isn't it?
Yeah.
Yeah.
Right. Yeah, because E... yeah, I mean, the other way of seeing that is with E is you've got the intercepts, which are clearly...
yeah.
Don't make sense.
Yeah, that's true. Yeah, because you can always have a 30 area rectangle, can't you?
Yeah.
All right. Yeah. Good catch. Okay.
No worries.
So, cos 52 is equal to adjacent over height. So 28 cos 52 into the calculator is 17.2 centimeters. The angle x looks like tan is opposite over adjacent. So arctan of 52 over 60 is 35 degrees. Let's do it to the nearest integer. It's fine. Okay. Again, the formula to find out. There's not enough of this kind of thing. So I saw a few years ago, there was a good science GCSE question, and it basically said, you know, student Dave is reading an A-level textbook and finds a formula about a pendulum, and it gives you the formula and then asks you questions about it. And I don't think there's enough of that. You know, we're here so this is like volume of a frustum, I guess. Which
Yes.
you can do as a compound shape anyway. And if
Yeah.
you, but like I don't know, there's not enough of like just give you something slightly new, and then seeing what they can do with it. But anyway, when so again, it's just another substitution question like that Heron of Alexandria, or in this case, bowl question. So give your answer to
Yeah.
three significant figures. So it's 13 times, sorry, a third of the height times pi times 10 cubed minus 7 cubed over 10 minus 7. Okay, I'm just going to go straight into the calculator here. 1/3 times 5 times pi times 10 cubed minus 7 cubed over 10 minus 7 is 1150 to three significant figures. When b equals 0, the bowl is a cone. So this is going to degenerate into that, which is the formula for a cone, because it's a third of the cylinder.
Really nice question.
Yeah, love it. Okay, this also looks like a fun question. 2 circles. The diagram shows 2 circles with a point of intersection at A. The center circle is B. The radius of the big circle is 6. BC is the diameter of the smaller circle, so the radius here is 5. Okay, what's the question? Explain why BAC must be a right angle. Now, that to come up on the SATs paper. So this is Thales' theorem, or you might say it's angles in a semicircle are 90 degrees. Or I suppose you could say, do we know that AC is a tangent? Because tangent means radius at 90. Suppose we don't. Yeah, I suppose it must be a tangent, right? I mean, it is, because it is 90, but what is the length of AC? Okay, so we know, what do we know? We know that that's 6, we know that that's 10, so, and that's a nice little 8 centimeters, because it's a Pythagorean triple. And that's the end of the test. So, some good questions in there. Love that. Thanks for your comment there, Emily. Hope you enjoy getting drunk. I shall hope to see you later. Yeah, some good questions. Yeah, I like the whole back half of that. Once we get away from some of that.
Yeah, I do think these papers are a real loss. I mean, it's part of this tradition of maths education that is like influenced by, I guess, industry really. Like it's got something in common with the Maths Teachers Association stuff, UK Maths Challenge, that kind of thing, and it's kind of been lost. Catherine's saying, wouldn't we have used Pythagoras or used Pythagoras on part A rather than Thales' theorem?
Well, that's an interesting point. I don't know if we can do that. BAC. Well, at that stage, but we need to know that it's a right angle in order to use Pythagoras here, right? I suppose. No, I don't know if we can do that. Because the converse of Pythagoras' theorem says that if you have a Pythagorean triple, then you have a right angle triangle. But I think you had to assume. I can't quite. I might be wrong, but I can't quite see that from the information that we've got. We can jump in and use Pythagoras without first establishing that right angle. Ollie's saying it's a 3, 4, 5 triangle. Yeah, but we don't know that without first working out this, right? So all we know is that it's a 6, 10, and mystery side here. If we knew that that was 8, then yes, I agree. By the converse of Pythagoras' theorem, that would be a right angle. But there's no reason why it couldn't be like, you know, some kind of 6, 10, 9 or something. Okay, anyway, let's move on. I might have missed something there. I'm happy to be overruled. Let's move on. So we have we're partway through our journey from infancy to degree level, and just after the mathematically speaking, this is far from the halfway point, but age-wise, we're way after the halfway point, I guess. This is the GCSE paper, the old standard. This is the paper 3. So I did a couple of GCSE papers to warm up. They weren't particularly hard. Like, I don't know. I expected to see some more challenging questions on there. I was still surprised by that. But we have got paper 3 here, so maybe they've saved some tricky questions for this third part. So now we have this is exam 6 of 24, and
Yep.
let's do it. And then I think I'll stretch my legs.
Sounds good.
So we've not even been going for 3 hours, and we're approaching the quarter-way point. But let's not forget that I haven't done any of the A-level papers yet, which are much more time-consuming, particularly the further maths, which took me, I think, longer than 2 hours last time, because boy, are they fiddly. So, GCSE, paper 3, here we go. Before we start, what should we say we expect the jump between Key Stage 3 and Key Stage 4, which is sometimes what we call this stage in the education, the Key Stage 4. More algebra, we've seen how much they love ratio. My God, they love ratio. And we didn't see any quadratics, did we? We saw an expansion of a double bracket in the Key Stage 3 paper, but
Yeah, no solving quadratics.
I think just more of the same, but harder. You know, any particularly new content? We might get trigonometry like the sine rule and the cosine rule. We haven't seen any of that yet, and we might
get that dumb thing of mean from a grouped frequency table.
Oh yeah, all of that good stuff. But we are starting with a nice Venn diagram. That's nice, isn't it?
Wow.
I love this kind of stuff. So a bit of set theory. So this creeped into the GCSE a few years ago, and I don't know how I feel about it. You know, I think this is. So if you don't know, set theory is. I mean, it's not an understatement to say that it's the underpinning of all of mathematics. You know, apart from logic, like the maths wise. Set theory is really the at the foundation of everything. Depends on your philosophical position, I guess. But you know, most of us subscribe to ZFC and or different foundation. But I think any found the piano or the I think any axiomatic system is reliant somewhat on set theory. So to introduce it here is an interesting choice. I don't really see the point, because you don't go into anywhere near enough detail to start talking about why it's so powerful, why it's so useful. It's just kind of there.
Yeah, it's interesting. It's a circle of life. Back in the 1960s, of course, we had the new maths movement.
Yeah, the new maths, yeah.
And part of that was that was the first time this stuff arrived at this level, and then it went away again for 30 years, and now it's back.
And here it is.
Yeah.
So
So the pendulum has swung back in that direction once again.
yeah, it's odd how those things happen. But anyway, so we've got a Venn diagram here. So um, we have 6 and 9 members of both sets. So 2 lives out here. We've got the 8, the 5, and the 1. And this universal set, which they've gone with a kind of a calligraphic symbol here, whereas I usually use, the one that often gets used is this Xi, everybody's favourite Greek letter.
Uh-huh.
1, 2, 3, 4, 5, 6, 7, 8, 9. Find the probability that the set lives in there. 2 nines, because there's 2 in the intersection and 9 in total. So, moving on. Katie invests £200,000. Good for her. In a savings account for 4 years. Compound interest. Again, such an easy, straightforward. This is the kind of thing you're on about. This drillable sort of question, isn't
Yeah.
it? Like,
Yeah.
I'm surprised by this. I really am. Power of 4. 2, 1, 2, 2, 7, 2 pounds. Okay. Oh, here you go. Grouped frequency. Although it is a frequency polygon. When was this? 2019. Interesting. Now, I at my school teach the AQA exam board, and I'm fairly sure frequency polygons aren't on there anymore. Interesting. Because they took that and they took stem and leaf diagrams off as well. That's something that we might see in the old spec when I come to do those papers. But anyway, so the class interval that contains the median, so it's going to be the 40th value, so it's going to be there. 40 is less than h is less than or equal to 50. And frequency polygon. Now, do you draw these at the midpoint? Actually, can't remember how you draw a frequency polygon. Or do you draw it at the upper bound? What do you think here, James? Am I plotting 15 against 7?
Yeah.
That's what my gut is telling me. And then
Yeah, I think so.
25 against 13. 35 against 14. This is so tedious, isn't it? At GCSE level, we're still doing plotting questions. 50...
People are corrupt it though, people mess this stuff up,
I know, but it forces you to kind of just kind of stop in your tracks. It grinds you to a halt because it's so easy to make mistakes. It's so easy to make mistakes. 5 minutes on each side. It's so easy to make mistakes that you have to slow down and do it. Anyway, it's a polygon, so it wants us to join these up, doesn't it? Something like that.
You know what, as well, I've led you wrong. I think we should have done it onto the upper bound. It doesn't really matter, but I think we should have done it onto the upper bound because I think what it wanted us to do was put 0 at 10.
Yeah.
But it doesn't really matter.
I think
yeah.
I was thinking about that because it's like cumulative frequency, isn't it?
Yeah.
So maybe this.
Yeah, I think that's what it wanted us to do, to be honest. Sorry about that.
That's all right. I mean, I'm the one doing these papers. I should really know. So ignore that one. There we go. We fixed it. It's you wouldn't be able to tell that we'd even made a mistake there. Okay, what on earth is that? Sean has drawn a time series graph to show the numbers in thousands of visitors to a fun park. Not a theme park, a fun park. Don't tell me whether it's fun. I'll be the judge of that. So the number of visitors in the thousands. Write down 2 things that are wrong or could be misleading from the graph. So it is not smooth by any stretch of the imagination. So that the reason that's a problem is it's really hard to pick out any kind of. You got this kind of kink in the graph here, which could imply that at this point of the graph, which, you know, what even is that? So, Sean, I think that's something else we should talk about. You know, that is implying a big surge in interest at this specific point here. But there isn't a specific surge there, because actually when you draw it, it should be drawn more smoothly. Or, in fact, a time series should be drawn with straight lines.
Yeah, definitely.
It should actually be straight lines. Be straight lines, if anything.
Yeah, should be straight lines. 100% it should be straight lines.
Yeah. In fact, yeah, because even if you're drawing it with a curve, there's some degree of choice over how you draw it as well. So let's change that to just that. Okay, now what is going on with the x-axis? It looks like he's tried to do this in quarters. So that's quarter one of those years. So I'll just put not fully labeled, because that's a catch-all thing, isn't it? I suppose you could say y-axis doesn't start from 0.
I think there's something interesting going on the y-axis between 9 and 10 as well. Look at 8.5 and then straight 9, 10.
From 0. So we got, 9 to 10 is a bad increment, or inconsistent increment, I should say.
Yeah.
So, Sean, mate, you've had a nightmare. This is just a shambles, isn't it?
Dreadful.
I mean, yeah. Okay, I think Sean's fairly embarrassed about that now. So, hexagon. The hexagon has one line of symmetry. Sure. Okay. Angle BCD is twice the angle CDE. Okay. Work out the size of the angle AFE. Okay, well, its only line of symmetry must be there. So as long as we can work that out, we can, we're happy. So that's x, that's 2x, and we know that x plus 2x plus 117 must equal the sum of the interior angles of a hexagon divided by 2. Now, what is 400? It's 720, so that's 360. So that's 3x is equal to 360 subtract 117 is 243. So x is equal to 81. Okay, and the question actually asks for that one, so 162. Fine. Jeremy has to cover 3 tanks completely with paint. Each tank is the shape of a cylinder with a top and a bottom. I wonder if he's going to use that dark paint from earlier.
Probably.
Dark paint. It's bizarre how some of these are written. Each tank is in the shape. Oh, I've read that part. So that's the diameter, that's the height. 7 tins of paint. Okay, so surface area of a cylinder then is going to be 2 pi r squared for each of the end caps, and then if we unfold, we've essentially got a rectangle of length 1.8, and that is 2 pi r. So plus 1.8 times pi 1.6. Okay, so let's do it. That's 2 pi times 0.8 squared plus 1.8, 1.6 pi. So 2 pi times 0.8 squared plus 1.8 times 1.6 pi is 13. So he has got loads of paint. That makes me think I've done something wrong here.
Three tanks.
Ah. Sneaky that, innit? So surface area of all 3 is like 39. the rounding thing is 39. So his paint is 5/7 is 35. So no, not enough paint. Okay, work out.
No.
What?
It's the way you wrote no.
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 No, it doesn't. I thought you'd say no to this question, which is
No.
basically, can you put numbers into the calculator?
Harder than it looks.
Back in the old days, maybe you'd have to think about it, but now we've got these calculators that can literally just show what the actual display is. You know what I mean?
Are you in degrees or radians?
I'm in degrees.
Okay.
319. Guaranteed.
Just keeping you honest.
Yeah, I'm guaranteed to make some kind of mistake later when we go to the A level. Okay. Here is Sarah's method to find the length of BC, but she has added when actually, oh, I can't spell. Actually should be BC squared is equal to 8 squared minus 6 squared. Fine. Okay. Roy is going to enlarge a triangle. Oh. Scale factor 1.5. He's used scale factor 2.5. Hasn't he? Because 2 has become 5. Yep. So, Roy, what are you like? A company has to make a large number of boxes. The company has 6 machines. All machines work at the same rate. When all the machines are working, they can make all the boxes in 9 days.
Like the Simpsons episode, it's the visit to the box factory.
It actually is. The table gives the number of machines working each day. Work out the total number of days taken to make all the boxes. Oh, these are awkward, these proportionality questions. So, right. So one machine can do... if we had one machine that's doing I always right, just let me think about this. So what do they get done in a day? So 6 machines, they do in one day 6 machines do a 1/9 of the work, which means one machine in one day does 1/54 of the work. So on day 1 we're doing 3/54. On day 2 we're doing 4/54, and on day 5 we're doing 5/54. So we've done 12/54 of the work up to here. We need a further 42/54 of the work. So it's going to take another 7 days, I think, because 6 machines working times by 6. So we need 7 of those, don't we? 6 times 7 is 42, right? Yeah. So
yep.
So 7 days. Yeah. Final answer.
Not 7 days total, right? 7 plus 3. 10 days.
Total number of days. Yeah. So it's all other is 7. So it's 10 days overall.
Yeah.
Which is quite surprising. So it only needs an extra day. I would have expected longer than that. Because you're underpowered for 3 days, but not that underpowered.
Well, you're underpowered by six machine days total.
Yeah, that's right. Yeah.
So actually, yeah.
Yeah, I suppose it makes sense. How would you have done that? I'm interested. How would you have done this question?
Yeah, I probably would have put some notation in. I probably would have done like a big capital B for the total number of boxes and something. But yeah, pretty much the way you did it.
Yeah, because obviously the trap here is in terms of, well, one machine is somehow related to 1.5 because you divided that by 6.
Yeah.
But because it feels like it's direct proportion, but it is actually inverse proportion. So yeah, those questions are hard. That is hard. Okay, Marie invests 8,000 in an account for 1 year. Well, I tell you what, in 2005, we had people rich enough that they could just invest 200,000, no problem. Now we're a little bit more modest at £8,000.
Yeah.
At the end of the year, or was that at the start of the G6? I don't even know. I think I might have just got that wrong. At the end of the year, interest is added to her account. Marie pays tax on this interest at a rate of 20%. She pays 28.8 tax. So work out the percentage interest. So the amount of interest she earned must be that 144. So as a percentage of 8,000 is 1.8%. Yeah.
Yep. Someone's been on Money Saving Expert and got a decent account. Hattie says hi, by the way.
Hi, Hattie.
And thank you to one Ellie Gill for her donation as well.
Oh, Ellie, thanks so much. She's a star. So,
Cheers.
The distance between Earth and Mars was that. The signal was sent from Earth to Mars, assuming the signal sent traveled at that speed. How long? Okay, so the time taken is the distance over the speed. That's 130. Now, are we going to get... So that's 130 seconds. Wow, that is very fast. That's 2 minutes. That's not right, is it?
Yeah, I think so.
2 minutes? I thought it took like 15 minutes. I suppose it depends where Mars is, doesn't it, in relation to us. But a 2-minute signal... I thought it took longer than that. But okay, I might be wrong. The speed of the signal sent from Earth to Mars was actually less. So if it was actually less, bigger time. Patrick has to work out the exact value of that. Okay. Patrick says a quarter of 64 is 6. Oh dear. No. 64 to the power of a quarter is in fact the fourth root of 64, which is not a nice answer actually. It's 2 root 2, I think.
Mm-hmm.
Fourth root of 64. Oh, it's not even giving it to me. Well,
Square root of 8, right?
If we subtract 2 root 2, this should be 0 if I've got it right. Yeah. So, good. The density of ethanol is that. The density of propylene is that. 60 litres mixed with 128 to make 188 litres of antifreeze. Work out the density of the antifreeze. Right, okay. So, I think there is actually a shortcut to this with I think you use something like the harmonic mean or something. It's a bit like when you do average speed and stuff like that. But I'm not going to do that. I'm going to do it the old-fashioned way. So density is equal to mass on volume. Now, 60 litres is actually how many... that's 60,000 cubic centimetres, isn't it? It's 1,000 cubic. Yeah, because it's 10 by 10 by 10. That's a liter. Yes, that's actually 188,000. Okay, fine. So we've got 1.09 times 60,000. That will give us the mass of the ethanol. And then we've got 0.97 times 188,000. That will give us the mass of the propylene. I think I'm saying that right. Times 60,000. And then 0.97 times 188. That gives us 182,360. So the total mass is that. So the total mass divided by the total volume will give us the density of the antifreeze. So the total volume is 1.8. Well, let's just do it. Okay, so 247,760 over 60,000 plus 188,000 is 0.999. Correct to do decimal places is just 1. So it has the same density as water then, pretty much. Is that an intentional feature of antifreeze?
I have no idea. You know, it says correct to 2 decimal places. Do you have to write 1.00?
I was just about to do that because I don't know. They're not going to deduct marks if you write 1.00, so sure. Right, we've got another weirdly symmetrical hexagon type question here. So I love this sort of thing. Okay, so the area of ABDE is equal to the area of the triangles. Definitely not drawn to scale, is it? There's no way that they fit inside there. I mean, there'll be loads of space left over, I mean. And then AB to AE is 1 to 3. Yeah, definitely not to scale. So if AB is x, this is 3x. Okay, work out the length of AE. Ah, yes, lovely question. Right, so how do we get our hands on these areas then? So we've got 3x squared is the area of the rectangle, and that is equal to half 24 3x sine 30 times 2. So 3x squared. Now sine 30, I should know this. Is this half? It's half. Of course it is. So that cancels with that. That cancels with that to make 12. Times by 3 is 36x. And then that means x squared, take 12x is equal to 0. So x is equal to, well, let's go through the whole motion here. X is going to be 12, isn't it? X equals 12. So the length of AE is 36 centimeters. Boom. X could be 0, of course, but that would be a degenerate shape, just a point. So yeah. I guess we don't want that. The graph of the curve C with equation is transformed to give that equation. Okay, so it's been reflected and shifted. Okay, a point on C with coordinates is mapped. Okay, so fine. We've gone from 7 to... We reflect in the y-axis first, isn't it? And then so that becomes minus 7, 2. And then we go down by 3 here, so it's going to finish minus 7, minus 1. Ooh, nth term of a quadratic sequence. Always a bit of a meal. So 6, 10, this should be 14. Yes, it is. and then we go 4, 4. So we've got 2n squared. Now I teach this in a way that I think I'm thinking of completely reconsidering how I teach this, because it's just one of these things where I think the way I do it is intuitive. So the way I'll show you how I do it, and then I'll ask how you do it. So the way I do this is a quadratic sequence is of the form something n squared plus a linear thing. Once
Yeah.
we know what the linear thing is, once we know what the an squared is, we know it's the quadratic sequence minus the linear thing. Sorry, the linear thing is the quadratic bit, subtract the an squared bit. So I write the quadratic sequence that we've got up here, and then I write out the 2n squared sequence, which is just the doubles of the squares, and then I subtract them, and that gives me my linear bit. And then once I find the nth term of the linear bit, we're home and dry. So if we do this, subtract this, I get that, I get that, I get that, I get that. Oh, right, so the linear is actually just a constant sequence. So it is just 2n squared minus 3. So that's the answer. But usually this turns out to be a more interesting linear sequence. You find the nth term of that, add it onto your 2n squared.
Yeah. Yeah.
You don't have a better approach?
I'm trying to remember how because I used to teach this. I'm trying to remember how I used to teach it, to be honest. There's a thing. There's a method. There's a method where you write. You wrote the differences sequences there.
Yeah.
I've seen a version of this where there's like a more systematic way of like just using those difference sequences.
Yeah.
I can't quite remember how it goes down actually, but
So
I believe that's how I used to teach it. I don't think I made them do this. Write the table out that you've just written.
yeah, so I know the thing that you're talking about here. So if we've got a general an squared plus bn plus c, then when n is 1, we get a plus b plus c. When n is 2, we get 4a plus 2b plus c, and then we get 9a plus 3b plus c. And then when we find the differences, we get 3a plus b, we get 5a plus b, and then when we find the second difference, we get 2a here. That's why we divide that by 2 to get the a. And then I think you then do 3a plus b is equal to 6 with the value of a that you've worked out. So this is 6 plus b equals 6, therefore b equals 0. And then your a plus b plus c adds up to minus 1. So 6 plus 0 plus c is minus 1. So c is minus 7. Okay, well, when you do it right, this is what happens. I don't know what I've done wrong there. I'm expecting. Oh, a is 2. Sorry, isn't it? Not 6. So we get minus 3 here, which is what we get here. The minus 3 with the linear term dissolving. But
so you want to change the way you're teaching it then? Which one?
Well, I've got a colleague who swears by this method, which is fine. But my problem was always getting them to memorize that you half to find a is all fine, but then there's 3a plus b and a plus b plus c. They seem to just come out of nowhere. So it's 3 packets to memorize.
Yeah.
Whereas this,
no, I don't like this.
But my students really struggle with this.
Yeah.
I've noticed. Well, they can do it, but can they remember it?
Yeah, it's hard. Those questions are hard. I always found them hard as a kid as well.
So, the graphs... Yeah, when I was a student, I actually don't know how I used to do that. I don't know. Okay, so 4 types of function. Okay, so we've got inverse proportion. We've got a trigonometrical function. I would have just said trigonometric, but okay. And then, root x. It's that kind of logarithmic curve there, isn't it? That's fine. Show that that's okay. So big bracket expansion. Let's do the first 2 brackets first. Times 3x plus 7. So let me just double check that. Yeah, fine. And then we get 6x cubed, and then the quadratic pieces we're going to get 14 plus 21 is 35x squared. The linear bits will get 49 plus 9 is 58x plus 21. Okay, now solve that. Okay, now there's a trap here, isn't there? Because this is telling us this, but also we've got that it could be the case that it is greater than minus 3/5, because then it would still square to something that's less than 9/25.
Yep.
So that's the trap that we've avoided. And then there's another trap in here, actually, because we've got this awkward minus x in here. So where we subtract 1 from each of these, and then we'll times through by minus 1. So we get 2/5 is... oh, God, I'm awkwardly swapping them around. I think this is correct. So if x takes any value between 2/5 and 8/5, yeah. Let's just pick a random number between 2/5, which is 0.4, and 8/5, which is 1.6. So if we pick 0.9, say, and then we do 1 minus that squared, we get that, which is less than. Usually, you pick a number and check it, you're fine. Fine, whatever. So that's correct. So this is going to be a bounds question. Calculate an upper bound for the value of d. Now, upper bound means we want to maximize this one and we want to minimize this one. So the maximum, the upper bound for that is 26.25. Lower bound for that is 4.25. So 26.25 squared all over 2 times 4.25. Okay, and then 26.25 squared over 2 times 4.25. 81, and it wants it to 6 significant figures, bizarrely. So that's 3, 4, 5, 6. The lower
that is
bound,
weird.
Yeah, no, why?
I mean, why would you write an upper bound to 6 significant figures? It doesn't make any sense. Anyway.
No, not at all. The lower bound for D is that, correct to 6 significant figures. By considering bounds, write down the value of D to a suitable degree of accuracy.
Good question.
Okay, 78.6003. We know as much. I don't really know what this is asking me. So I would say 80.
Yeah, agreed.
Because that's, excuse me, that is the, to 1 significant figure, it's going to be 80.
Yeah.
Seems to be a suitable degree of accuracy.
Yeah.
Moving on.
And I guess it's saying give a reason, and the reason I would give is the upper and lower bounds are different at 2 significant figures.
Yeah. That's what was going through my head, because if you try to do 2 sig figs, you get 81 and 79.
Yeah.
So let's go with that reason.
Yeah.
Okay, so simultaneous equations.
Nice.
Yeah. Okay.
It tells you to do it algebraically, so you can't draw an accurate diagram of the circle and the line.
Yeah,
Sad.
as if you could draw an accurate. I think that's an ellipse, actually, that one. But
Oh yes.
you know, which is even harder. So, wonder if there's a cheeky way of doing this, because this is a sticky sort of question, isn't it? I wonder if. So 4y squared is equal to 2y squared. I wonder if it's easy. I don't know if this is actually easier. That's 7 minus 3x. And then that means 2y is equal to 7 minus 3x on 2. So if I substitute in for 2y, rather than trying to rearrange the whole thing, let's go with that. Sure, we still have to do a double bracket, but this avoids the fractions, I think, because what it usually wants you to do is, if you do x, for example, is 4y minus, sorry, 7 minus 4y over 3. Oh, actually, no, it's just as awkward either way. Fine, whatever. I'm trying to be clever, but forget it. Minus 42x plus 9x squared all over 4 is equal to 9. Okay, so we get 30. No, we don't. Let's slow down. 4x squared. Subtract all of this. Plus 9x squared. I remember last year when I did this live stream, I did a simultaneous. It's two linear equations, and I just couldn't do it. It was about 4 a.m. and I was getting really stressed out because the answer just wouldn't fall out. So minus 5x squared plus 42x minus 49, which I'm going to add over to the other side, is 85. Now,
jeez,
this is bad, isn't it? I really wanted that to be a multiple of 5. Have I done this right? So 3 times 7 is... Yeah, that seems right. Seems right.
Yeah, I think it's right.
Might be a quad formula question then. Well, let's sort it out. We've got 5x squared minus 42x plus 85 is equal to 0. At this stage, I'm thinking quad formula. The only thing I can think of is...
Yeah, I think quad formula. I really do. It's miserable. I mean, this is pretty much the last question, right?
No, we've got some charts. Yeah, let's go with the quad formula. X equals, so 42 plus or minus the square root of 42 squared minus 4 of 5 of 85 all over 10. Okay, and let's just go straight into the calculator because why not? 42 squared.
Yeah, why not?
4 of 5 of 85 all over 10. Oh, it does factorize. You know, I was thinking about 5 because I've got... This smells like 5 times... what is it? That's 5 times 13, is it?
Is it?
No, it's not. Not at all. 5 times 17. Okay, so it's 5, and changing that to a subtract is, yeah, 3.4 or 17 on 5. So we could have factorized this. 5x minus 17x minus 5. I should have gone with my gut there because something was telling
you let
me,
you let me fool you.
Yeah, something was telling me about that. But whatever, it's fine. Okay, and I guess we need the y values now as well. So y is equal to 7 minus 3x on 4. So we put these values in. So when x, I'm going to write these as ordered pairs. So we've got 7 minus 3 divided by 4 minus 4 fifths. And the other one we've got is 7 minus 3 fives over 4 is minus 2. Okay. Done. Okay, a histogram gives information about the distribution of the weights of some onions grown by a farmer. I mean, honestly. Onions less than 60 grams in weight are used for pickling. So that's these ones. Onions greater than 120 grams are sold at the market. Okay, we've still not actually arrived at a question. A pie chart is drawn, is drawn using the information opposite to show what the farmer does with the onions he grows. The angle of the sector for the onions sent to the processing factory is X degrees. Ugh. Honestly.
This is a question and a half, isn't it?
I mean, I thought it was a joke when it turned over and there was a pie chart there. I mean, this is so awkward. So that's 120 there, isn't it? That's 120 onions. 30 times 5 is 150. 30 times 9 is 270. Now, what on earth is that? 15 times 6, which is 90. And 15 plus 45, that's 90. 90. Okay, so in total, we've got 120, 150, 270, 90, and 90. So that's 720 onions. Oh, that's a nice number at least. So that means each onion is half a degree. Half degrees, if you will. So 720 in total. How many of them are processed at the processing factory? So these are the picked ones. Greater than 120 is these ones. They are sold at the market. So 150 plus 270, that's 420. So that means it should be 210 degrees there. Because now we've got 420 onions. That's 210 degrees because each onion is half a degree. Yeah, fairly happy with that. Jeez. That was a meal, that one.
At least they didn't make you draw the histogram, so small blessings.
Yeah, I guess so. I mean, it's kind of interesting. You don't really get pie charts in the higher paper anymore. Yeah, honestly. This farmer really knows his onions, I guess.
Jeez.
Sorry, yeah, that was worse than my Pentagon joke. I'm embarrassed, actually. Okay, here we go. Oh, they love this question. This tangent to circle question. This comes up all the time these days. So, AB is a tangent, such that we've got a 30-degree angle there. Part B is 16,0. And point P is 3P. Find the value of P.
God.
Okay, that's fine. So we're going to right angle triangle here with 30, and we know its hypotenuse to be 16. So therefore, we can calculate that, which is the radius. Okay, so sine 30 is r on 16, so r is 8. That's our old friend sine 30 is a half from earlier. So we've got 8 here. So x squared plus y squared equals 64. So 3p squared plus p squared equals 64. So 10p squared is equal to 64. So p is equal to root 6.4, 2.52. 2.5 to one decimal place.
Blimey.
You like that?
I mean, it's a great question. My God.
It's actually not the question I thought it was going to be. So quite often you get circle, always center at the origin in GCSE, and then you get a tangent there, and it'll just be find the equation of the tangent to the circle. So you have to go around, you have to find the radius. Well, you don't need to find the radius, but you have to find the gradient of that line. So it'll give you these coordinates here. Use that to find the gradient of that line, and then the negative reciprocal for the gradient of that line. Put those points in, and that gives you the love that equation of tangent question. I've seen it so many times over the last few years. If you're a student watching this, make sure you're pretty hot on that before you enter the exam, which I believe is in about 40 days, which is terrifying. The diagram shows the positions. Now, what do you think about bearings? Because I remember in my training year arguing with somebody about this. I was like, what on earth are bearings doing in this GCSE? And the best anyone seems to come up with is, well, it's useful for navigation. I'm like, well, is it?
Well, I mean, so to me, I think it sets you up for mechanics, right? I think the only I don't think these kind of I don't think it's that interesting or useful, but I think it does set you up for the kind of mechanics questions about, you've got tugboats pulling stuff and how many newtons is it going to be? It's the same kind of setup.
Okay, I agree with that because quite a lot of the times you get those vectors, don't you, where it's like your unit vectors are I and j. So it's getting used to the idea of having one direction as your, canonical
Yeah,
direction. I suppose I can agree with that. Yeah,
yeah.
it's just, it's just
I would say as well that a lot of so my understanding is if you're somebody who does things like makes robots that go in a 2D plane, you probably have some concepts like this.
really.
Yeah,
You don't think it
you
would
know,
just travel along a vector?
well, still, I think simple robots like Roombas use dead reckoning,
Right. Okay.
and if you have a device that uses dead reckoning, then I think this is the maths of it.
Yeah. Okay. I think I can go along with that. Uh, okay. Fine. I just find it odd. I think military there's probably still some kind of bearings. It's always just around boats, isn't it? And I'm like, how many people are we sending out to go sail some boats? After the GCSEs. That's all I think.
Yeah,
But
yeah,
I,
I
but
know.
I do agree. I take the point about the mechanics introduction. Yeah, I think
Yeah,
that's. I think
I mean
that's.
it's fairly weak. I mean, if someone said to me, "Oh, we're going to take these out," I wouldn't be losing any sleep over it.
No, no, I don't think so. It's just a weird extension of some of the geometry, and the fact that we still give it as like this weird 037, which I actually don't know why bearings always have to be 3 digits. The guess that when my students asked me, I said I actually don't know, but I'm guessing it's got to be something to do with when you transmit a bearing. There's reliability in the fact that it's always a 3-digit number. It's always 3 packets of information. You know, I don't know if that actually, in like a coding theory sort of way, if you know that you're going to deliver 3 packets of information,
Yeah.
it's usually. Anyway, should we actually answer this question?
Yes. Let's get this over with.
So, we've got some towns: Acton, Barston, and Chorlton, just down the road. Find the bearing of Chorlton from Acton. So, we want this theta here, and then the bearing will be 37 plus theta. So, how are we going to do that? So, we've got a lot of information here. I suppose we know that is 143 because it's co-interior with this one, and therefore we know that. This is going to be a cosine rule question or something of that ilk. So this is going to be what? It's going to be 143 plus 150, and then deduct from, I think 77, isn't it? 67. 67. Okay, that's good. Is it easier to find this angle here, I wonder? We know what that angle is. That's 30, because it's co-interior with that one. We have enough information to find that with the cosine rule, and we have enough information to do 8 on that, 9 on that. Oh, yeah. I think this has to be a cosine and sine rule. Don't see a quick way of doing it. Because with the sine rule, you need sides opposing the angles. So we don't know that side, so we can't use that information. Okay, let's just do the cosine rule then. So x squared is equal to 8 squared plus 9 squared minus 2, 8, 9 cos 67. So x is the root of 8 squared plus 9 squared minus 2, lots of 8, lots of 9 cos 67. That is 9.4. Yeah, I think I agree with that because looks like could be. This is almost an equilateral triangle. I would have expected it. I would have expected that to be between 8 and 9. Actually, thinking about it, I suppose. So what I'm thinking about here is this is an unknown feature of triangles, unknown to many people, is that we have the longest side is always opposite the biggest angle, and the shortest side is always opposite the smallest angle, which makes sense if you think about it, but it's not an obvious fact. So I'm thinking, I thought this angle maybe was bigger than that, so I expected this side to be bigger than this, but the point is it doesn't really matter. So we know that 9.4 under, let's do it under sine 67 now, is equal to sine theta on 9. So sine theta is equal to 9 sine 67 over 9.4. Now, given what I've just said, theta has to come out to be less than 67, and it has to come out to be bigger than whatever that is. So, into the calculator we go. 9 sine 67 over 9.4 equals, shift sine equals 61.8. To one decimal place. Now, let's, out of curiosity, 180 subtract. This has to be smaller than all of them. 51. Yep, and it is. So it makes sense.
Yep.
Could you
5
see
marks.
Could you see a 5 marks for cosine
Nah,
rule and sine rule?
Yeah, but
we haven't been asked about that on any. This is paper 3 of 3, and there hasn't been a cosine rule or a sine rule question, and that's the end of the test. So done.
So we should say thank you to Liz Gill, donation.
Oh, Mother Gill.
Mother Gill, yes.
Thanks very much. Thank you.
And also a massive thank you to Preston for a £100 donation that he has put through in 4 separate chunks.
Oh, just because he wants to dominate that whole corner of the screen there with Preston.
Well, he's written us some very interesting messages, which I will now read. You have a task. To release yourself from this web of numbers, this knotted maze of functions, you must complete the papers of the Maths Charity Challenge. There are 24 papers of the flesh, chosen from different eras, ancient and modern. The trivia of your workings is important to me. Indeed, some may score marks. Read through, but linger not. Where the questions lead, you will follow. Answer these papers well. Ignite my anger with your delay, and more questions will come your way. Welcome. You have entered the cranial vistas of Magoo-genesis. This is a place of no time and no space. Do not be afraid, for I am merely the vocal manifestation of your mathematical dreams. I am as addition, as subtraction, like maths itself. Do not be afraid.
Amazing. I love that. And thanks so much for your donation. I imagine I'm probably the only person who will ever listen to that or get the full meaning of that and what it is in reference to. But amazing. You really had done yourself there. So good.
Yes, thank you, Preston. We are enjoying ourselves.
That is exactly what I expect from Preston. So good.
Well, we both loved it, Preston, so I don't think it was too much time spent. I think we both needed that after 6 papers.
Oh my god, that is so good. Right, thanks very much, Preston, and thanks for your donation as well. That is outstanding. So, I hate to say it, James, but he's knocked you off the top there, hasn't he? With
he has,
pounds.
yeah.
Although maybe not, because he's done it as 4 separate donations. So maybe Tiltify thinks that he's only donated £25. So,
indeed, it does. So it's still showing me as top donor. So.
All right. Well, there you go then. But if you could write me some kind of rhyming couplets based around some niche musical interests that me and Preston share, that would be great. But until then, I'm going to consider Preston to be my biggest contributor. Okay,
Yeah.
so I'm gonna get a drink and stretch my legs for a second. I'll be back in 2 minutes, and then we will crack on with an A-level paper. So getting to the tricky stuff.
Yep.
Um, but should be fine. Should be fine. Quite nervous about it, to be honest. I've done nowhere near enough prep for this, so this might be where we start to struggle, but not to fear. All right, I'll be back. I'll be back in a minute.
All right. See you in a bit. Okay, folks. So who we got with us? We got Preston with us. Hi, Preston. Feel like I haven't seen you for ages. If you're here watching, say hi. We like to see you. It's still worth it. Yes, I think it was worth it. So yeah, so we're 6 out of 24 exams done, which is 1/4 of the way through. Making good time. We've been going for nearly 4 hours. And yeah, so making good progress, but we haven't done any A-level papers yet, and that's what's coming up now. So we did a Key Stage 1 paper, we did a Key Stage 2 paper, we did a Key Stage 3 paper, we just did some GCSEs, and now we are going to do some A-levels. And yeah, this is where we're going to use some of that time that we've saved up on those GCSE papers and so on this morning. Not this morning, but early this afternoon. So yeah, editing synth. My goodness. Yeah, and the A level, but I mean, it is interesting to go back to these A level papers. I think what we're going to do is we're going to do the sort of core maths, which is kind of the pure maths stuff, which kind of contains. It's got a lot of calculus, so differentiation and integration, and then there's some other sort of bits and bobs. Oh, hello, Kit. How are you? Welcome. Painful memories. Well, nothing worthwhile to do is easy, right? Um, um, so yeah, so we're going to be doing some calculus. We're going to have some integration and differentiation. There's also some bits of geometry in there, but not too much, I think. And we also have some little bits of what's called numerical analysis. So Alex was talking about the trapezium rule earlier, and that's where you're doing something like you've got a integral, and rather than exactly calculating the value of that integral, which is what you normally do, you want to estimate it for some reason. And we have a couple of the most basic techniques for that included in the A-level, the Trapezium Rule, and I'm sure Alex is going to thoroughly grumble about the Trapezium Rule when we get to that, because it is a lot of adding and timesing. Not too much fun with a hand calculator, but there we go. But yeah, so there we have it. And just as a reminder to people, this whole event today is all in aid of Refuge, which is a really important charity which kind of supports victims of domestic violence and abuse. So, it's all in a good cause. He's not just putting himself through this because he loves maths exams so much. It is all for a good cause. Yeah. Just a reminder, folks, with the culmination of this series of papers that we're doing at the moment, we're going to do some A-level papers, and then we've got a sets, numbers, and functions first-year undergraduate paper. So we saw a little bit of set theory in the GCSE paper, and we discussed that a little bit, how that's a new thing. New thing that's also an old thing. As far as we're aware, he doesn't do this for fun. Yeah. But yeah, so we saw a bit of that set theory, but then we're gonna get into the undergraduate set theory where it all starts to really take off. So if you're curious about what degree level mathematics looks like. We're going to be getting there early evening to see that. Yeah, but well on track so far, doing well. Feeling fairly confident. I'm sure that's not true, Kit. Sure that's not. You did maths A level, right? I'll be saying the some things from maths A level that I'm sure we'll recognise. But I want to ask Alex when he sits down, does this have factor theorem in it and remainder theorem? Something I always liked in the core one. I was just wondering, Alex, does this have like the factor theorem in it? Is that part of this?
Yeah, that's introduced at the A level. Yep.
Okay, and remainder theorem as well.
Yeah. Not really used as much as the factor theorem because it's not as useful, is it? But
no.
You know, it's. I'm actually just gonna stick a comment on Reddit. Someone responded to my post asking when I'm doing the A level papers because they're taking their A levels soon, so they wanted to watch along. So
right now. And we also have a colleague, former colleague of mine from UCH with us. So
excellent.
Some
Welcome.
Yeah, we got some NHS folks around.
Okay then. Excellent work. Thanks for using your NHS influence to promote the event. Always appreciated.
The NHS massive.
The NHS massive. Okay, so paper 7 of 24. This is A level. It is, where are we? Paper 2 of June 2019. So let me update the screen here. And that is paper 7. Okay, so. And another donation from Jacob, it looks like. Thanks very much. Someone's got to knock Preston off that off that table there. Okay, so what are we? What's the big change between the GCSE and the A level? For me, is calculus. This is where we finally introduce calculus to the young people of the UK. Now, we actually disagree on this, I know, but I think calculus should be introduced just that little bit earlier. You know, if we've got room for bearings in GCSE, we should have room for just the kernels of calculus. You know, it's really, really hard to overstate just how impressive of a theory calculus is. It really is the closest thing that we've got to magic. You know, as much as I understand it, and no matter how much I understand it, it is still something that I think is just incredible that it actually works. You are shuffling some numbers and functions around, and you are able to deduce some really extraordinary things that I don't know. It's just it's extraordinary. And so useful. You all modern physics and engineering is impossible without it. It's just that important and just that useful. And I think we all educated people. You know, you speak to some 40-year-old person who did their GCSEs ages ago, and they still remember Pythagoras. They still remember SOHCAHTOA. They should also remember. Oh yeah, and I remember a bit of what calculus was, even if it's only in the context of quadratics, you know, because you do everything else about quadratics at GCSE level. Why not just learn how to differentiate them or something like that, you know? But anyway, that's my pitch for why we should have at least a little bit of calculus at the GCSE rather than just dumping it all on the A level. What do you think?
What you're saying is it's the Shakespeare of maths. So you're basically saying we have Shakespeare in English and we should have calculus in maths for the same reason.
Yeah, I mean, I'm a group theorist, but I would never say that we should have group that'd GCSE level because that'd just be pointless. But like, I think calculus deserves a spot in the compulsory mathematical education of all young people. That's what I think. That's what I think.
Yeah, I mean, well, you know me. I would cut a lot of, even from how the GCSE is now, I would reduce the level of content and increase the depth of the questions. And I think that's I don't have anything against calculus in particular, but I would just rather have a GCSE that had about a third less content in it, but had required much more extended argument in the questions.
Yeah, I mean, I think broadly I agree with that. So it's also so it's hard for me to make the case that we should be adding more to the GCSE.
Yeah.
The equally important question is what do you remove? I think there's room to remove lots of stuff.
Oh, there's lots of junk. There's lots of junk
Uh,
in there. Yeah.
yeah, so plenty that we could go at. I would increase the relevance of certain things. Like I would do more with prime numbers at GCSE. I would do more with. I don't think I would add any more geometry actually, but I would do more with it. I don't know. I just think so. Calculus is going to be in here. You've mentioned factor theorem, remainder theorem. The other big shifts, so there's not actually that much new geometry at A level, but because you kind of deal with all of that Euclidean stuff at GCSE, but you are introduced to radians. There's a lot more trigonometric function stuff. So yeah, I think where previously we could sort of see everything build upon each other, this is probably the bigger step where we're now going to take to quite a large step. Even though it's only a 2-year course, we're going to see quite significant changes in the kind of maths that we're being asked to deal with here. So, shall we get on with it?
Do it.
Okay, so let's go.
Just while you're starting this one off, I'm going to step away for a couple of minutes, but I will be back.
Okay, that's fine. So, wow, okay, so after having said all of that, we still get what could... I mean, there's no real reason why this could not be a question on the GCSE paper. There's nothing really going on here. So it's basically saying that's 2 squared times y, so this is x plus 2y, and that is 2 to the power minus 3 on 2, I think, because it's 2 times 2 to the power half, so 1 plus a half, 3 on 2, and then negative because it's the reciprocal. So x plus 2y, therefore, is equal to minus 3 halves. We want y as a function of x, so y is equal to minus 3 over 2 minus x, and then divide the whole thing by 2. And if we want to, we can sort that out to something like that. So, quite an easy... Oh boy, they give you a lot of paper to work with. Quite a lot of... Quite a lot of... I don't know, maybe that is an extension of a GCSE topic, but fine. Okay, the speed of a small jet aircraft is measured every 5 seconds, starting from the time it turned onto a runway until when it left the ground. Okay, estimate the length of runway. Okay, so we want the distance, which is the area underneath this curve. So does it want me to... Let's look something like this. So we want the area under... Oh no! James, you're not here to see the disappointment in my eyes. This is a Trapezium Rule question. And it's disguised because it's got all this context around it. So, God, I hate the Trapezium Rule so much. I can't even begin to tell you. So I think it's this. 5 plus 10 plus 18 plus 28. So let's just whack it in the calculator. What's the height of each of these strips? 5, isn't it? So I've got 2.5 times 2 plus 42 plus 2 of all of this. 5 plus 10 plus 18 plus 28. 415. Explain whether your answer to... Given that the jet accelerated smoothly in these 25 seconds, explain whether your answer... Okay, so for those unaware, the Trapezium Rule is what we use, one of the things that we used before the miracle of calculus, which I've just prattled on about. Say you have a curve here, and you want to find the area of this space. So with other geometrical objects like trapezia or rectangles or triangles, we know how to find the area of those shapes. It's pretty rudimentary. But we don't know how to find the area of curved things unless it's something like a circle, you know, a special sort of shape like that. But we can estimate the area under this by basically splitting it up into trapezia and finding the area of each of these. And because it's a smooth acceleration we see, we're actually overestimating the area slightly. But I hate the trapezium rule because we know how to do stuff like this. We've got calculus now. We've got this magic that we can appeal to. So don't make me do this boring number thing with the trapezium rule. Okay. Wow. A lot of spare paper here. I really wish I had looked at this before printing them, because I really wouldn't have printed off so much paper. Apologies for that. So, area of the sector is given by half r squared theta. That's right. Half times 40. Okay. So 40 degrees needs to be in radians, the grown-up angle measurement. So 40 degrees if you want the correct solution. So it is going to be half r squared times theta. Theta in radians is going to be, well, it's going to be 40 on 360 in degrees is the same as that on, sorry, 360 over 9 is 40, which in radian world is 2 pi on 9. So it's 2/9 of pi. Okay, so it's going to be half times 5 squared times 2/9 of pi. So half times 25 times 2/9 times pi. Now, what do I think the area is going to be here? I would expect this to be something around 5 times, around 12-ish, or 8, lower than I thought, but I think that's fine. So that's 25 pi on 9, which is 8.73 if you prefer, which I do not, but sometimes they do. So that'll do. Oh, so much paper. Ooh, this is nice. Look at that. So a curve C1 with parametric equations. Okay, parametric question. Meets that circle. Okay, so that is a circle. So they meet at 4 points. One of them lies in the 4th quadrant. Okay, that's fine then. So we're finding solutions to this system of simultaneous equations. So interestingly then, in the last GCSE paper, we saw an equation that looked like that with another linear equation, and we solved it simultaneously. This is exactly the same thing. It is the same. The only difference is we've got this parameter involved. But we're basically going to find out what x squared is, find out what y squared is, shove them in, solve it for t, and that's going to give us the x and y coordinates. So we know that x squared is 100 cos squared t, and we know that y squared is equal to, so 4 root 2 squared is going to be 32 sine squared t, and they sum to 66. So 100 cos squared t plus 32 sine squared t is equal to 66. Okay, now we just need to solve that. And we are going to solve that by, let's pick one of them. So we're going to use the identity sine squared theta plus cos squared theta equals 1. In other words, sine squared theta is equal to 1 minus cos squared theta. So that's 32 1 minus cos squared theta equal to 66. So we've got 100 of them, and we're going to subtract, well, this is going to result in 132 cos squared, sorry, that should be a t there, shouldn't it? Subtract 32, so it's equal to 96 plus, 66 plus 32, which is 98. So cos squared t is equal to 98 over 132. Okay, now this is where we get our 4 solutions, because remember, these curves meet at 4 distinct places. So when we root both sides, we get plus or minus the square root of 98 on 132. Now we want the s where x is positive. So we want to take positive values here, which means we're only going to, thinking about the cos graph, we're only going to take positive, well, what is root? Am I right in saying that? Yep, we want positive, and we want the principal angle there. Yeah, so we want the positive one, yeah. So, sorry, inverse cos of the square root of 98, 98 on 132 is 30. Now, we are in radians here, so we should change our calculators to radians. So that's, so t equals 0.532, etc. So x is 10 cos 0.532. So 10 cos of that is 8.616. Y is 4 root 2 sine 0.532, which is, so 4 root 2 times sine 0.532. Okay, now we want this to be negative, don't we? So if I take the sine of that, I'm now pondering whether I should have pulled more solutions out of this, because I don't think it's going to be as simple as making that negative, or maybe it is. So that's 2.869. So what I've actually done is I've found that one there. So if I make it negative, it must be fine. So xy is 8.6 minus 2.9.
Yeah, it looks good to me.
It doesn't look good to me.
No?
No. This is wrong, because there's no way that if you square them and add them, you get 66.
Oh god, no, you're quite right.
So what have we done wrong here? Oh god, I was dreading this. This is all right. So don't panic. Let's just go back. 1, 3, 2. Shift cos equals 0.532. So that is correct based on that, which means that I feel like I've made a mistake earlier. What is 4 root 2 squared? 32. Sine squared t. 100 cos squared t. This looks good. It's definitely 1 minus sine squared. 100 cos squared minus 32 plus 32 cos squared equals 66. Definitely in radians. Huh. What's gone wrong here then, James?
So all the stuff on the left looks right to me. So I'm looking at the range of t. The range of t, it says, is t is between 0 and 2 pi, right?
Yeah.
I don't think that helps.
No, because it's just like it's going around, you know, the parameter is going around once, isn't it?
Yeah.
Sine 0.532. But this has all come out based on these values come from this, so the mistake must be on this side. Oh, what have I done wrong here?
100 cos squared t. 2 sine squared t. That's right. Ah. So your two lines, 100 cos squared t plus 32 sine squared t equals 66. Between that line and the next line, you go from plus 32 to minus 32. Why is that?
For no reason whatsoever
Aha,
is the answer to that. So, honestly, I need to.
Sorry.
Yeah.
Should have spotted that one sooner. Sorry about that.
No, it's all right. You know, I've actually got a. I'm gonna make a cup of tea here because even though they don't recommend caffeine to get you through these things, I mentioned before, I feel terrible. I did not sleep very well last night. I've basically gone in with the worst possible setup to one of these things. So, come on, I need to waken up. I need to wake up here. Right.
Yeah.
So,
cup of tea.
Plus, minus. So that's 68 cos squared t is equal to 66 subtract, which is 34. So this is 34 over 68. Now we need inverse cos of the square root of 34 over 68. And that's a quarter pi. Of course it is. You know, of course it's going to be something nice. Yeah, of course, because 34 on 68 is a half. So,
Yeah.
So t is equal to pi by 4. Okay, fine.
Now we're back on track.
Now we are back on track. So 10 cos pi by 4 should be 5, right? 5 root 2. So 5 root 2 and 4 root 2 sine pi by 4 is 4. So I'm going to go with 5 root 2 minus 4. Okay. So, okay then. Ooh, this is interesting. This looks like a first principles question. But integration, which so figure 3 shows a sketch of the curve y equals root x. Okay, the rectangle with width delta x. Okay, calculate the limit as delta x tends to 0 of that. So it isn't an integration by first principles question. This is a weird. Because this is when x is 4, we've got this strip When x is 5, we've got this strip. When x is... What on earth is that? This is going to be root 4 plus root 5 plus...
What? Yeah.
This is going to tend to 0 because we're just adding... Unless this sigma notation, they're using it in an unconventional way, and they're not. It is actually an integration from first principles question, and it does want me to add all these strips together. That's the only thing I can think of.
Because you're right. I mean, I also read it as it's going to tend to 0.
Yeah,
But why would they go to the trouble of drawing the picture and everything?
yeah, I think because so if you're unfamiliar with this notation, usually this means the integer values between 4 and 9. So you have your expression where x is 4, you have your expression when x is 5, all the way up to 9, and you add all those together. But I think what this wants, it wants us to sum across x from 4 to 9 continuously. And as delta x tends to 0, it becomes, like an infinitesimal. So you are basically doing integration. So it's the integral from 4 to 9 of root x dx. But
yeah,
it's not a first principles question because this doesn't in any way prove that this is what it is. This is just saying that's what it is. Like it is true that when you sum an infinite thing across a continuum, then it becomes integration. By magic, as far as the A level student is concerned, because integration from first principles is really hard compared to differentiation from first principles, which sometimes you get a differentiation from first principles question, but it wasn't until I did real analysis that I learned actually what integration is and where it comes from. I'm just gonna go with this.
yeah. Be interested to see the mark scheme at some point.
Yeah, so that's 2 to the power 9 to the 3 over 2 plus, subtract. So this is between 9 and 4, right? 2 times 4 to the 3 on 2 over 3. So 9 to the power of 3 over 2 is 27 divided by 3 is 9 times 2 is 18. 4 to the power of 3 over 2 is 8 times 2 is 16, so it's 16 on 3. If we wanted to simplify that, it would be 54 minus 16 on 3, which is 38 on 3. Weird question. Not entirely comfortable with that. If it turned out that I got that totally wrong, I would be unsurprised. Anyway, some functions here. Okay, find the value of GG of 0 on this, the day of the Grand National, a GG. So GG of 0, well, that's going to be G of 0, that's when x is less than 2, so that's minus 2 squared plus minus 5. And then when x is greater than 2, we use this part of the function, so 4 times 5 is 20, so it's 13. Find all values of x for which g of x is greater than 28. Ooh, okay. Alrighty then, so we want these and these, don't we? So we want, okay, so let's do part B here. Actually going to need to make use of this paper. So 4x minus 7 is greater than 28. That implies that x is greater than 21 on 4. Or if we prefer, 5 1/4, just to help us visualize where that is. So that's that part. And then we also need to consider x minus 2 all squared plus 1 being greater than 28. In other words, x minus 2 is less than the negative root 27. Because when we root it, we're going to go bang. And then we need to consider it's when x is less than. So it's this end of the graph. So x less than 2 minus root 27. I think that'll do it. So the range of values, therefore, is as follows. Sorry. Needs to be less than that. Oh no, you can't bundle those together, can you? Can you? We want it to be bigger than... Yeah, it's just... no. Don't like it. So let's just treat it as two separate inequalities.
Yeah.
Yeah. Because you can bunch them together, but then they don't hold in simultaneity, which is what that implies. Okay, so done that one. The function h is defined to be that. Explain why h has an inverse, but g does not. Well, g doesn't because it's not an injective function, but neither is h. So it doesn't have an inverse. H does not have an inverse. That is a... Oh, it's only defined for that part. So yeah, H in injective. Sorry, that was a slow moment, wasn't it?
Oh, no, but I mean, that is exactly what they're getting at, right?
Yeah,
Is that you know, it's one of those really dumb, annoying functions questions that smart asses like to write, isn't it?
yeah. H is a bijective function. I suppose you want to say 1-to-1 and onto, is that the word that they use for surjective?
I don't know.
Whereas
Surjective, we all know what surjective means on this stream, so I'll say subjective.
So and G is not. So only bijections are invertible. So D. So awkwardly kind of going back to, I'm going to make a bit of room over there so I can spread these papers out a bit near my cup of tea. So my janky setup has become even jankier. So question D is to solve that equation. H inverse of x is equal to minus 1/2. So we know h of x is equal to x minus 2 all squared plus 1. Now I'm going to cheat here because I think the natural way to do this is to find the inverse function and then solve. But actually, we know h inverse of x is equal to x, which is h inverse of minus 1/2. So if we just put minus 1/2 into there, we'll get the answer. So minus 1/2 subtract 2 all squared plus 1. That is 4 on 2, so minus 5 on 2 all squared plus 1, which is 25 on 4 plus 4 on 4 is 29 on 4.
That's a good trick. I like that.
That's the group theorist's way of doing it, isn't it?
Yes.
So I suppose we could check the answer, but let's not. So let's... so much paper, honestly. A small factory. It's just a small factory, you know. It's just a small one. It makes bars of soap. On any day, this is going to be a modelling question. I hate these. I'm so bad at them. So bad. Okay, on any day, the total cost to the factory Y pounds of making X bars is modelled to be the sum of two separate elements. A fixed cost, there's your fixed cost again, James, and a cost that is proportional to the number of bars of soap that are made that day. Okay, so that means the cost is so something fixed plus some amount of x, I guess. So I suppose it's a linear. I suppose the more natural way to write this would be like this, because this is like a linear straight line sort of thing.
Yeah.
Okay, the bars are sold at £2 each on a day when okay, so this is going to be put the numbers in and solve simultaneously. So on a day when the bars of soap are made and sold, the factory makes a profit of £800. Okay, so 500 is 800k plus A, and a loss of £80 minus 80 is equal to 300k plus A. Let's do a subtraction here. 580 is equal to 500k, so k is equal to 580 on 500, which is 580 divided by 500 is 1.16. Oh, that's not what we've got there.
Yeah, I think the devil is in. Sorry to backseat drive, but it's the total cost is what you've modelled in A.
Oh, yeah. All right. Okay. Let's slow down then. So,
Yeah,
why would you do it like that?
to
Usually,
make it really annoying.
to make it awkward. Well, at least it's to
Yeah,
show that question. So I know I've goofed. I would have spotted that eventually. I think. So
yeah,
okay. Yeah, you are right. Okay. So this is actually a little bit more sophisticated then. So the cost to the company on the 800 bar day. I love it. It's made and sold as well. So this factory is cranking out and selling 800 bars. That's so
yeah.
the
Literally as fast as they can make the
just
soap.
yeah.
Flies off the shelves.
And they've not oversold. They've not like under manufactured. They've just got 800 made and sold. Done. So they are making 600 quid because it's £2 each, isn't it? We forgot to use that. So, but they only actually make a profit of 500, which means the cost is 1100. That's the cost. And why is the cost? So 1100 is equal, in fact, to A plus. Now it's 800 bars, but they're sold for £2 each. But X is the number of bars, so 800k. Right. Okay. And on the 300 bar day, we're making £600, but that's resulted in a loss of minus 80. So the cost in this case is 680, and that's A plus 300k. All right. I'm more happy about this. Although I'm not happy with the question because it's annoying. So that's 420. And that's equal to 500k. Yes, that's good because 42 times 2 is 84. So this is going to come out nicely. Yeah, this is going to be it. So 420 divided by 500 is 0.84. Okay, and now to substitute back in 0.84. Let's do the bottom one times 300. 252, 680, subtract that is 428. Yes. So A is 680 minus 300 of 0.84 is 428 as required. Okay, awkward. With reference to the model, interpret the significance of the value 0.84 in the equation. Well, it's positive. That means that the more bars we make, the more money we make. Oh no, the higher the cost is, because this is the cost and not the profit. Is the fact that it's less than 1 relevant? No.
Sorry.
Just The significance of the value 0.84, you know,
I
that's
think it just means like it's the per bar cost, right?
yeah. So 84 pence per bar,
Yeah, 84 pence per bar.
I guess.
Really, I think I was looking at this thinking that's silly. I don't know why they're asking us that.
Well, they probably reached the end of the paper and added it up to 79 marks. So they were like, "Well, let's do another mark here." Find the least. Okay, assuming that each bar of soap is sold on the day that it's made, which apparently they are. Find the least number of bars of soap that must be made on any given day for the factory to make a profit on that day. Okay, so the income, let's call it, is 2x. That's what we did here, isn't it?
Mm-hmm.
So, and the cost is kx plus a. Now, the income will equal the cost at the cusp of making profit. I think that's right. So 2x is equal to 0.84x plus 428. Solve. We get 428 divided by 1.16. Which is what we got there, isn't it? Because we didn't take into account that 2x thing. Yeah, that makes sense. Divided by 1.16. So 368.97. So 369 bars at a minimum to make a profit. All right, need to wash my hands of that.
But
Oh, I didn't even enter. God, you get so much paper. You know, I'm quite glad about that because I remember, particularly at university, it used to be like, okay, your time starts now. And then I always used to raise my hand and go, can I have some more paper, please? Rather than waiting for me to fill up the answer book of only about 8 pages. Just like, I used to
yeah,
ask for paper at the start. I always needed it. And one of those stupid treasury tags.
yeah, I remember that when I came to Manchester. Suddenly, oh, everybody loves treasury tags in Manchester.
What did they do in Cambridge?
I don't remember. I feel like maybe we had treasury tags in Cambridge as well. I don't remember. I think we had stapled booklets actually.
Stapled booklets.
Yeah, I don't remember, but I think we had
Well,
stapled booklets.
with Cambridge's endowment, they can afford some staplers, can't they? But it's just measly treasury tags at the University of Manchester.
Well, and also I used to love in Manchester like they were still using the booklets from UMist days. That
Oh
was
yeah,
like
yeah. They've obviously like they printed off tens of thousands of them way back in the. Well, it must be. Yeah,
it was a really long time. I mean, it was like more than a decade before we were there. So
yeah. When did it dissolve? Well, not dissolve. It kind of became in 2003, was it?
yeah, it's the early thousands. So,
Yeah. My colleague would know because he's proud of the fact that he went to that university as you missed. So
ah,
uh,
yeah.
showing his age a little bit. But anyway,
Anyway,
so it's an infinite sum. So
oh,
it's the old a over 1 minus r, isn't it? So that's the formula to sum to infinity, provided r is less than 1. Well, mod r less than 1, isn't it? So whatever. The first term of this is 20 times 1 over 16, which is 5 quarters. And r, in this case, well, my notations become quite confused here because they've used r
yes.
as the dummy variable. Let's change that. R is a half. So the sum to infinity is 5 quarters divided by 1 minus 1 half, which is 10 quarters or 5 halves. So show that that sum is 2. Okay. Okay. I'm going to write out the first few terms just to get a feel for this because I'm not entirely sure because it's not arithmetic, geometric. The only thing I can think of is it's going to involve some laws of logs there might be a trick in this one. What am I doing? Log 5 of so when n is 1, it's 3 on 2, and then we're adding log 5 of 4 on yes, I know exactly what this is going to be. This is going to be a telescopic thing, isn't it? So
Oh, yeah.
so
Oh, man.
log 5
Takes me right back.
50 on 49, and now through our wonderful logarithmic laws, this is 3 over 2 times 4 over 3 times 5 over 4 times blah 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 times 49 on 48. I always like to do 2 terms at the end. 49 on 50 on 49. And now let's get a different coloured pen for this, shall we? Because it's exciting. Oh no, I dropped it. I got too excited. So 3 cancels with the 3, the 4 cancels with the 4, the 5 will cancel with the 5 down there, the 48 will cancel with the 48 up here, 49 with the 49. So all in all, we are left with log 5 of 50 divided by 2, which is log 5 of 25, which is 2. Alright, nice. Love that.
That is a nice question. I like that a lot.
Got all the time in the world for that. Okay. Ugh. This looks interesting. A researcher is testing the effectiveness of a braking system of a car when it is driven in wet conditions. The engineer measures and records the braking distance d meters when the brakes are applied from a speed of v. The graphs of d against v and log d against log v were plotted. The results are shown below together with a data point from each graph. Okay. Explain how figure 6 would lead the engineer to believe that the braking distance should be modeled by that formula. Well, it's linear in a log-log graph, so it is an exponential relationship. So it is going to be modeled in that way, isn't it? So that's fine. And now we need to know that. Okay. So how are we going to work that out? So let's do this as... So we know y equals mx plus c. But y in this case is log d. So that equals some gradient m times log v plus... Now, should I write this as log c or should I write this as c? I haven't made my mind up yet. But actually, we know what it is. It's minus 1.17. No, it's not. It's 1.77. Okay. So, now, if we try to... Okay, so now d is equal to 10 to the power of all of that. M log v minus 1.77. Okay. Now, whip that up there. So we've got 10 to the power of log v to the power m times, or divided by 10 to the power of 1.77. Let's keep that up there, because that's going to be our k, isn't it? I'm hoping that that's what it pops out to be. So 10 to the power of minus 1.77. 0.017, yeah. And of course, 10 to the power of log v to the m is just v to the m. So I've got 0.017 times v to the power of m. where m is equal to n, because they've used n and I've used n. I think that's all fine.
Yeah.
Yeah, I should say let log x equal log 10 of x, because it's not always assumed that log base blank is log base 10. Okay, I'll try to keep the question on there. Use the information from figure 5 with k equals 0.017 to find a complete equation for the model giving the value of n to 3 significant figures. Okay, so figure 5 tells us, it gives us this data point vd is equal to 30, 20. We know from the first part of the question we've got 0.017 v to the power of n, and it just wants us to find n. So we know that d is 20, so 0.017 times 30 to the power of n. Now we just need to solve. So 20 divided by 0.017 is that, horrible, 20,000 over 17 equals 30 to the power of n. So now log base 30 of that is equal to n, which is log base 30 of that 2.07. 2.08, let's say. What does it want? 3 significant figures? 2.08. Sean. No, I thought we already had Sean. Well, we had Sean. Wasn't Sean the guy who made an absolute mess of that that time series graph?
Yes.
So now he's driving his car 60 kilometers an hour in wet conditions. So he's driving away from his former mistakes at high speed in wet conditions, and he notices a large puddle 100 meters ahead. It takes him 0.8 seconds to react before applying the brakes. Use your formula to find out if Sean will be able to stop before reaching the puddle. Well, Sean, let's find out. We have, so our braking distance is the thinking distance plus the oh no, I think stopping is equal to thinking plus braking, isn't that? Makes more sense. So his thinking distance, I think my pen's running low on ink here. We have got, he's driving 60 kilometers an hour for 0.8 seconds. So 60 kilometers an hour is 1 kilometer a minute, which is that number of kilometers in a second. So 0.8 of those, 0.013. That's the thinking distance. And now the braking distance. So D is equal to 0.017 times V to the power of, what do we get? 2.08. Okay. Oh, and V is 60, isn't it? All right, so we just do it. So 0.017 times 60 to the power of 2.08 equals 84. 84.9 plus 0.013 is 84.5. My pen has well and truly died there. I need to top that up in a second. Where did my other pen go? So that's 84.93. So I think he actually stops with quite ample. He notices it 100 meters away, so he does manage to stop. Usually it's a lot closer than that, isn't it? James?
Sorry about that. Well, I mean, I've not got my calculator out here, and I so I cannot assess. But yeah, I mean, I don't know. It's reasonably close, right? Same order of magnitude.
Yeah, sure. Let's go with that. Okay, where is my? I'll be back in one moment.
Just a brief break here. Hello to everybody from the NHS who's watching. So it seems like our entire audience this afternoon is largely consisting of NHS colleagues. You know, thanks, welcome. Um, Now we get to see the ritual of the refilling of the pen here. Now, what a privilege this is.
I'll tell you what, my students absolutely love it when I do this.
I bet they do.
Yeah, they find it fascinating.
Like you like Professor Snape.
Yeah, they'd probably agree with that as well. Sadly. Oh well. He was good in the end, right?
I don't know.
It's ambiguously good.
Yeah, yeah, something like that.
And if you ask any of my students if I'm a good teacher, they'll say ambiguously good. So. Okay. Put that in there. And do we have ink? We have ink. All right. Apologies for that. You know, I thought I topped this pen up yesterday, but it can only take so much. Okay then. Looks like a bloody rag. Anyway, where were we? Oh, we did that question, haven't we? So
Yeah.
let's move on. I feel awful about the amount of paper that I've used on these. I really did not expect. Because I thought at the A level you used to get like a separate answer book. I'm sure you used to get a separate answer book.
Yeah, I think you did.
Not anymore. Okay. So, sketch of a triangle. OC is 2OA. So C is like here. Okay, M is the midpoint of AB. Usually it gives you all this like on the diagram and then it just gives it to you. You know, you don't usually have to build the diagram yourself. The straight line through C and M cuts through OB at the point N. So let's draw that in there. This seems very familiar, I have to say. OA is A, and OB is B. Find CM, and we also know that that's A because it's the same. It's twice. So let's find CM in terms of A and B. Well, if we're at C and we want to get to M, we are going to go from C to A, and then we're going to go halfway from A to B. That's how I like to do these questions anyway. So minus A plus half of, now how do we get from A to B? It's minus A plus B. So that's half of B minus 3/2 of A. Does that make sense? Can you imagine going A and a half and then half of B? Yeah, that seems close enough, doesn't it? Okay.
Yeah, looks good to me.
All right. So ON. So from O to N. Okay, so we're scaling up somehow. So I think ON should be written OC plus a scalar multiple, which they're using lambda here, as we tend to, of CM, because it's on a straight line. OC is 2A, so plus lambda, which we found in the first question, CM, so half minus 3 on 2a. Okay, now I think it just wants me to tidy this up. So now, how much a have we got? We've got 2 minus 3 over 2 lambda. And how much b have we got? Oh, I think I've forgotten my b in there. We've got half lambda of b. Right, what form does it actually want? No, exactly that form. Hence, prove that ON equals NB. Sorry, ON NB equals 2 to 1. So it wants us to show that. Okay, well, this is very much like that GCSE question from before, except I think it's easier because it's ON is some multiple of B. Yeah? So that means the A component of ON must be 0. So in other words, 2 minus 3 over 2 lambda must be 0. So when we solve for lambda, we'll get 4/3. So what does that tell us? Well, half of 4/3 of B is now what ON is, which is 4 on 6b, which is 2/3 of b. So if we break this up into 3 parts, 2 of them are here, 1 of them is there. So therefore ON to NB is 2 to 1. All right, that was okay actually. I took a look at this with all the vectors and I thought I was getting that GCSE question that I did a couple of hours ago was way harder than that.
Agreed.
Okay.
And thank you to Kit Baxter Darrington for your donation. Much appreciated.
Thank you very much, Kit. Very much appreciated. Thank you. How are we doing on those? 705. Not bad. Not bad.
Yeah, not bad. Less than halfway through. So
it all helps. It all helps. You know, I've not actually done any calculus yet, but this looks like it might be some calculus. So, after my whole song and dance with calculus earlier, I don't think we did any. Oh, we did that weird integration question, didn't we? But yeah, that was just a bit strange. X to the power of x. Oh, I'm not going to like this. This is where my calculus gets really stretched here, if it is indeed a calculus question. First, by taking logarithms, find the x coordinate at the turning point of C. Okay, so we are going to find dy by dx. But it is telling us to use logs, which is really helpful actually, because I don't think I would have remembered to do that. Okay, so we've got log y is equal to x log x. So if we differentiate implicitly, we'll get 1 over y dy by dx is equal to x over x plus log x. Sure. So okay. Dy by dx is equal to x to the power x plus x to the power x log x. Substituting back in for y. Okay. Now if that equals 0, then that implies x to the power x 1 plus log x is equal to 0. So that means x to the power x equals 0, which it doesn't, or 1 plus log x is equal to 0. Therefore, log x is equal to minus 1. Therefore, x is equal to e to the power minus 1. I think that's it. Solutions based entirely on graphical or numerical methods are not acceptable. I mean, if you want to use the graph to try and work that out, be my guest. And you wouldn't catch me dead using a numerical method. Fine. Okay.
Nor me.
So, yeah, I mean, what would you even... Newton-Raphson, would that converge? I don't know.
Probably. I don't think it would be much fun.
No, it wouldn't be much fun. It'd be about as much fun as doing the Trapezium Rule. Which, by the way, there was a Trapezium Rule question at the start of the paper. I don't know if you saw that.
Oh no, I didn't. Oh
Yeah.
dear. Oh, sorry, I missed that.
I'm not. So, alpha 2... Okay, so 2 equals alpha to the power alpha. Lies on C... show that 1.5. So this is actually in the GCSE spec these days. So we're saying that alpha to the power alpha minus 2 is equal to 0. This is question B, by the way. So 1.5 to the power of 1.5 minus 2, and then we'll do 1.6 to the power of 1.6 minus 2. One of them will be positive, the bottom one presumably, and then the top one will be negative. So we get minus 0.16, and we get 1.6 to the power 1.6 minus 2 is positive. So usually we write change in sign. Oh, I can't write today, honestly. Change in sign implies yeah, the answer. So, a possible iteration formula that could be used in an attempt to find alpha is that. Okay. Ugh, 1 point iteration, honestly.
Oh, tell me about it.
2 times that to the power of 1 minus that. So, x2. x3, x4. So x4 is equal to 1.673. And the long-term behavior of xn, it's going to converge, right? Ooh, no. It does not look, it looks quite bouncy actually. It's going to oscillate between two values, I think. It looks like it's going to oscillate between 1 and 2. Yeah, 1 and 2. So divergent, I guess. So I'll write oscillates between 1 and 2. I suppose that makes sense, doesn't it? 2 times... So if xn is 1, then we get 2. And if xn is 2, we get 2 times 2 to the power of minus 1, which is 2 over 2, which is 1. So go back to 1. So it's just going to oscillate between them. So, fine. A message from Kit there. Is anyone marking these to see how well we've done? No. I'm kind of hoping that James spots any of the mistakes as we go along. It's funny, isn't it? What I could be writing here is total nonsense, and I think a lot of viewers might just watch along and say, "Oh yeah, looks right to me." We could bust out some mark schemes if we have time at the end, and I have enough patience. But
yeah, we'll see about that.
We will see about that. Yeah.
I mean, so I will say we have a number of highly qualified individuals watching. We had some nice corrections from Catherine earlier, and I think Ollie McDonald is still here as well. So
yeah, and Dan if he's viewing. So
Dan will jump on anything that looks dubious. So you know, I don't think we're going to be letting him get away with too much. Don't worry about it, Kit.
No, not with too much. Okay, so we've got a meaty looking trig question here.
Oof.
Yeah, oof, indeed. So, right. So, cos 3 theta. Now, the trick here is that is 2 theta plus theta, because I never memorized my triple angle. I only ever, because I think you can memorize, because they do turn out to be alright, but if you use a double angle with that, which actually I think is the way to go because we've got that 2 theta in there. So we want all the theta bits to cancel out.
Yeah.
So which way around is it? Cos A plus B, I'm pretty sure is cos A, cos B minus sine A, sine B. And sine A plus B is sine A cos B plus sine B cos A. Pretty sure that's right. I guess we'll find out because if it doesn't work, it won't be right. So cos 2 theta plus theta, first of all, is going to be cos 2 theta cos theta minus sine 2 theta sine theta over sine theta plus sine 2 theta cos theta plus sine theta cos 2 theta over cos theta. Woo! All right, so messy. So we've got cos 2 theta cot theta, that's the reciprocal of the tangent function, minus sine 2 theta, so that does cancel, plus more cancellation here. Ah, nice, they cancel out. Plus tan theta cos 2 theta. Okay, so cancellation happens here. Always good to cancel. So now we have cos 2 theta times cot theta plus tan theta. And somehow that is equal to cot 2 theta. Right, so I'm actually trying to arrive at this. So to get there, I have to show that this is 2 upon sine 2 theta. Okay. Let's do this. Let's break it down into sine again plus sine theta over cos theta. I mean, the only thing we could reasonably do is just try and add them. So let's do that. Cos 2 theta.
I think so.
I think it is going to work because we're going to get the squared. The squared's involved now. We're going to get cos squared theta plus sine squared theta over sine theta cos theta. Now there is something we can do with that. Yes, this is it. Because I do know that sine 2 theta is equal to 2 sine theta cos theta. So over 2 is that. And that, so cos squared plus sine squared is 1. Pythagorean trigonometric identity. So this is 1 over sine 2 theta over 2, which is 2 cos 2 theta over sine 2 theta, which, wouldn't you know it, is 2 cot 2 theta. Ooh, that was a meal, wasn't it?
Well, I will say these trig questions are always like this, aren't they? They're very satisfying.
Yeah, they are. Yeah, they are satisfying when you know what you're doing, but sometimes there's something that you just don't spot. So, like, if I hadn't noticed that could be put in with this one, for example, it's hard.
Yes.
Because it's easy to break sine 2 theta. Whoops, that's completely gone. It's easy to break sine 2 theta into the double angle, but then to go the other way, that's always what I used to struggle with. You know, starting with something that looks like a double angle, and then putting your double angle back in.
Yeah.
I think if I was a student taking this, I might not have got the answer to this question. What I would have done is I would have started with this and worked down and then married them up, you know.
Yeah.
And if worse comes to worse, proof by turning the page, you know. Okay.
Yeah.
So let me get that on there. We have got.
They're not making it easy with that range, are they?
Between 90 and 180. All right. So before I do anything, I'm going to put the calculator back into degrees because that's the sort of boob that I would make. So 2 cot 2 theta is equal to 4. We've just done a lot of hard work here. So I guess that means tan 2 theta is equal to a half. And now 2 theta, so inverse tan of half, one that I probably should know. Oh no, it's one that doesn't, no, because it's inverse. So it's 26.57. Now that range is a bit awkward. So what I'm going to do, I'm going to add 180 to this because it's tan. It's periodic every 180 degrees. And I'm going to go again. Because, in fact, I think only that middle value. Yeah, so now when we half them, this is 13 and change, which is outside the range. This is 190 and something. So that goes out the range. So actually, we only need that one. So divide it by 2. 103.28 is the only solution. Oh, and it wants it to 1 decimal place. So fine. Good old solution of trigonometric equations. Fine. Here we are again. So we had a cone connected to a hemisphere before. Now it's a cylinder. This kind of not an ice cream cone, but it looks like a 9mm bullet. A
Or an observatory.
A conservatory.
Observatory.
Oh, an observatory. I was just going to say that's a funny conservatory. You know. Yeah, observatory. Let's go with that. Yes. Or a storage tank, which I think is the least interesting of all the options that we've suggested, but that's what the question has gone with. So, the tank is modelled in the shape of a hollow circular cylinder. That's interesting. A circular cylinder. Is there another kind? Can you have an elliptical cylinder?
I have no idea.
I don't think I've ever seen one where you know, if it's like an oblong ellipse kind of thing.
Yeah.
Is that still a cylinder?
Not according to Wikipedia. According to Wikipedia, a cylinder is a prism with a circle as its base.
Well, yeah, I object to prism though, because prism is usually defined as a polygon. You know, a polygon that's been, and a circle isn't a polygon.
Mm-hmm.
So sort yourselves out, Wikipedia. Or maybe I'm wrong, I don't know. Anyway, so we've got the circular cylinder with the hemispherical shell. The walls are negligible in thickness, it's fine. And the volume is 6. Show that according to the model, the surface area of the tank. Okay, so fine. The surface area of this then, we've got the circle at the bottom, we've got the rectangle forming the wall of the cylinder, and we've got the hemisphere lid. And we don't want anything in between. So we're not going to have that circle in the middle there. So pi r squared for the circle at the bottom plus 2 pi r h for the rectangle here, and it's 4 pi r squared divided by 2, so 2 pi r squared. So, and that is equal to 6. Okay, and what form does it want it in? Ooh, it wants it in a form where we don't have... Oh, what am I doing? The volume is equal to 6. that's the surface area. But we need to use, because this doesn't involve h, so we need to find the volume of the whole thing, set it equal to 6, find h, bang it in there, and sort it out. So the volume then is pi r squared h plus 4/6 pi r cubed, because it's a hemisphere, we need to half it, and that is equal to 6. So that means that h is equal to 6 minus 2/3 pi r cubed, all divided by pi r squared. Yeesh, it's getting messier and messier. So we've got 3 pi r squared plus 2 pi r multiplied by this monstrosity over pi r squared. Now, should get a bit of cancellation here. So the pi's cancel, that r cancels. So we've got, I'm actually going to write this as 3 pi, no, let's just keep it like that. Let's not jump ahead. So plus 12 minus 4/3 pi r cubed over r. Now, what form does it want it in? Oof, where's that 5/3 coming from? That is weird. Well, we've got the 12 over r. So let's break that up. So we've got the cancellation there. We've got the 3 pi r squared minus 4/3 pi r squared plus 12 over r. So now we just need to check that 3 subtract 4/3 is actually 5/3. And it is, because 9/3 is 3. So that's 9 over 3. So 5/3 pi r squared plus 12 over r. Is that the form it wants it in? Yes, it is. Alright, that was actually meatier than I thought it would be.
Yep.
But again, you know, I reckon you could do a 6-mark GCSE question and ask that. I don't think there's anything there. You know, there's some algebraic sophistication that a GCSE student would struggle with, but it's nothing crazy.
No, I agree.
So use calculus to find the radius of the tank for which the surface area is a minimum. Oh,
Now we're talking.
right, here we go. Right, let's just write this down again. So we've worked out that the area is 5/3 pi r squared. So that means dA by dr. So the variance in the area as r changes, minus 12 over r squared plus 10/3 pi r, and we'll get extremes when that is equal to 0. So again, just for a bit of an explanation as to what's going on here, we've got the area, and if we were to graph this, so as the radius changes, the area is also going to change. Maybe it looks like that. I've got absolutely no idea. It's not going to look anything like that. But you know, imagine the graph as the area changes as the radius changes. Then this is telling us how steep this is on any given radius, and we want that minimum point there, which is when the gradient goes to 0. That's why we set it equal to 0 to solve. And so we get pi r cubed is equal to, oh, I had it in my head for a second there, 3.6, I believe. Should I do that the long way? Just to, yeah, add 12 times it by 3 is 36 divided by 10. So that means r is the cube root of 3.6 on pi. Close to 1 this is going to be actually, isn't it? So cube root of 3.6 on pi is 1.046. Okay, and I'm presuming we don't want to establish that that is in fact a minimum. I mean, it's an increasing function, isn't it? As r increases, the surface area must increase. So that must be a minimum. You're not going to suddenly achieve a maximum surface area of some value of r, at which the area starts to go down again by increasing r. That doesn't make sense. So I'm not going to go with the d2 by dr squared. Calculate the minimum surface area of the tank. Oh, right. So isn't that just 12 over 1.046 plus 5/3 pi 1.046? Just the area with that substituted in. 12 over that plus 5/3 times pi times that squared is 17 because it wants it to the nearest integer, meters squared. Yeah? Alright, so got to some good stuff there. I like that. Okay, right, here we go. Here we go indeed. Oh, you know, my weakness with calculus is substitution. I've never liked it. And this...
Right, I'll watch carefully then.
This looks horrendous. Yeah, let me struggle through it. Because I can usually bodge it out, but I'm never at my most comfortable during a substitution. Right. Okay. So let's just take our time here. So this is h to the power of a half. That means du by dh is equal to minus half h to the minus half. Oh. Okay. So, don't like where this is going. This is why I don't like substitution. I've got a bad intuition about what actually happens 3 steps in it. Someone who's good at substitution can pick out a good substitution and know in advance how it's all going to turn out. And I am not good at that. So dh as we call it, is minus 2 root h times du. So
yes, inverted commas.
well, because it's not quite right, is it? You know, it's just
correct.
It's just
For convenience.
Yeah, minus 2 root h du over u. Now root h is 4, so root h is 4 minus u if we rearrange this thing. So we can put that back in, and this is equal to minus 2 4 minus u over u du. And this is minus 8 plus 2u, and at this stage we'll split it because that just goes to nothing. So all in all, we've got minus 8 times the integral of 1 over u du,
yeah,
plus 2 times the integral of du. Okay, so that's minus 8 log u plus 2u, and we might have a constant on here. Are we given any initial conditions or no? Oh, it's got that plus k there, so it does want me to leave the constant in. Okay, so this is looking good actually, isn't it? Oh yeah, this is looking fine, because now we've got minus 8. Let's put the h back in. Instead of u, we've got 4 minus root h plus 2 4 minus root h plus a constant, and this is minus 8 log 4 minus root h. Okay, minus 2 root h plus 8 plus the constant. So let's just compile that all together into a constant k.
Yep, looks good to me.
Wow.
Do you want to explain the absolute value signs?
So you can't take the so what the logarithm means. So for example, log 5, it's asking you. So log 5 is some magic number, and the point is it's the magic number that if you do e to the power of that magic number, you get 5. If you tried to do something like log minus 5, so you're looking for the magic number that when you raise e to the power of that magic number, you get minus 5. And that's actually impossible because e to the power of anything is always positive. Like the graph of e to the power of something, it looks like that. It never goes below the axis. So through some quirk of integration, it works out that you can just take the absolute value of your expression here, and absolute value just means the positive of whatever's in the bars. So it's saying whatever this is, take the positive of it if it's negative, and take the positive of it if it's positive, and then log it.
Cool.
That's
good stuff.
That's how I would say it. Okay, well that was actually all right. Now the reason I could do that question is because it's telling me what the substitution is. If the question was that, then I would really struggle here because I am bad. I wouldn't have thought. I probably would have used this substitution. I would have used u equals root h, and I would have gone from there. That's how I would have done this. Because again, this is just where my intuition flops a bit, because it's clearly better to do this, because when you do du by dh, the 4 vanishes anyway. So by making this whole denominator become that one u term, it becomes so much cleaner over here. Whereas in my case, I would have ended up having to integrate something along these lines, with some other stuff. And that, you can still integrate that. You can still integrate that because that becomes log, that would become minus log 4 minus u. And then when you put that back in, you still get the 4 minus root h there. But you see what I mean? Like, my gut on substitutions is just a little bit... It's not what I would like it to be.
Yeah, and I think I think it's one of these things, isn't it? It's like it's almost you go back to the Victorian era. You look at Victorian textbooks, and they're teaching you, well, probably not Victorian in the case of integration, but maybe 1930s, and they're teaching you like classes of integral, right?
Yeah, well, yeah,
and it is just a matter of like having a systematic understanding of everything that's in the zoo, and I'm just not sure how useful that is these days.
Yeah. What was the book that I had? Was it the book that you got me, where it was like, that kind of
Oh yes,
that catalogue of mathematical techniques.
Yeah.
What was it? A synopsis
Oh,
of mathematical
let
methods
me.
or something. Yeah, like I
Yeah.
think maybe I saw that in there. But yeah, I've seen a lot of like those kind of diagrams where it's like, if you get something that looks like that, then that's what your substitution is. And I think it would improve my calculus considerably if I just went ahead and memorized those. There's so much that I've got memorized that there's room for a bit of substitution in there as well, I think. And I think that would be a low cost, high gains thing to do, to just quickly, improve my confidence with that kind of question. But anyway, we are completely changing gears from the looks of it, although looks like an ODE here actually. So a team of scientists is studying a species of slow-growing tree. Wow. Come on, exam writers. You might as well say a team of scientists is watching paint dry. The rate of change in height of a tree in this species is modeled by the differential equation that... I suppose what they want to do is like add the real world context. I suppose there are scientists who would need to use a bit of calculus to study slow growing trees and model it and stuff like that. So I do get it. It wants it to be realistic, but let's just get on with it anyway. So it's modeled by this. So we've got an ODE here. But it looks like the easy kind of ODE, which is fine. The height in meters and the T is the time measured in years after the tree is planted. Find, according to the model, the range in heights of trees in this species. Okay. So, all right. So again, we've got some kind of how the tree changes height. I imagine a tree changes height kind of like an S curve where you get slow start and then a big growth. It's something like this. But it wants us to find like any maxima and minima. That's the range of the heights of the trees. Well, surely the shortest a tree could be is 0. Maybe I'm thinking about this too hard. So the height, I'm going to say h bigger than 0. Surely the you can't have a tree that grows that has a minimum height greater than 0. Surely.
Does it not want you to integrate it?
I don't think so. Not yet.
But isn't it the same? Isn't it basically the same integral from part A? Is that why it's only 2 marks? I can't see part A anymore. So, but it's got that 4 minus root h there.
It isn't. It doesn't have the 4 minus root h. I think we're going to need to use this at some stage.
Okay.
But yeah, because if you were to solve this ODE, that 4 minus root h should come down. So we are going to be using this, but I don't think it wants us to do that yet. Not for 2 marks. I think it is just a case of, if we look at this, by common sense, the minimum height for the tree must be 0. But we do have a cap on that when this whole thing is 0. And that is when 4 minus root
right.
h
Yeah,
is
I
0.
understand.
So 16 is the top. So I'm gonna go with that. I think.
No, you're absolutely right. Sorry, I was thinking about it way too hard.
No, it's fine. Well, I think we all know what question C is going to be, don't we? It's going to be to solve this thing. So does it give us some initial conditions? One of the trees is 1 meter high at t equals 0. According to the model, calculate the time this tree would take to reach... Okay, so now the question is, how do you solve an ODE? Well, here's a class of equations that do form those distinct families, don't they? So, you know, this one is just one of your bog standard, you know, the integral of dh over 4 minus root h is equal to 1 over 20 times the integral of t to the power 0.25 dt. Now, fortunately, we did a lot of the work in question A, and we know that this comes out to be minus 8 log, and do tell me if I disappear off the bottom of the screen here, because I'm trying to show the question as well. Minus 8 log 4 minus root h minus 2 root h plus our constant k, and that is equal to 1 on 20 times 0.25 t. Oh, what am I doing? I'm differentiating it. 1.25 over 1.25 plus c, and we'll just assume that all the constants have dissolved into this k. Okay, I said fortunately we'd done a lot of the work. Unfortunately, the work resulted in this horrible mess, but never fear. Let's just do k is equal to t to the 1.25. In fact, that's 0 at the initial condition. So it's equal to 8 log 4 minus 1 minus 2 root 1. So that's 8 log 3 minus 2. That's our k. And now we want the height of 12 meters. So now we have minus 8 log 4 minus root 12 minus 2 root 12 plus 8 log 3 minus 2. And what is 20 times 1.25? It's 25.
Yeah.
So that whole thing times 25, and we are going to take the 1.25th power of it, root of it.
Oof.
Bizarre. So t is equal to. Okay, let's do it all in one go. That's exciting, isn't it? 1.25 times. Okay, so minus 8. It's not going to come out to be negative. This is it. Oh, well, let's just do it. Log 4 minus root 12 minus 2 root 12 plus 8 log 3 minus 2. Oh, this whole thing needs to be multiplied by 25. So, but inside the root. So that was foolish of me. Hopefully the syntax error will take me to the end. No, it doesn't. So all of this times by 25. So the t is 53.96. Okay.
Calculator had to think about it, didn't it?
It really did. Yeah.
"53 years? My goodness.
Yeah,
It is a slow-growing tree."
That's what I've got questions about.
Well, I mean, they did specifically tell us it was slow-growing.
Yeah,
right?
but there's slow growing and there's slow growing. And I completely, if this is the answer, I completely take back what I said about this being a realistic scenario. No one would fund this. No one would fund a 54-year experiment.
Well, you say that, but I mean, there's that really slow dripping bit of tar.
Yeah, that pitch.
Yeah, that pitch. That's what it's called.
The pitch drip experiment. Yeah. And
There's that.
There is one where they've basically taken clones of bacteria again and again and again for generations. But they're kind of the exceptions that prove the rule, aren't they?
Probably, yeah.
Yeah. Is it really 54 years? Something is off about this, and I can't. I don't know if I'm just overthinking it. I just didn't expect it to come out to be that. This is where I wish I had a mark scheme to double check my answer.
Integration on the right is correct.
Did not expect it to be so big.
No.
So we do get all of that. And then it's the fact that we're timesing by this 25 here. But it definitely does need the 1 over 20. And we definitely do divide by 1.25. So times that by 25. And then we take this bizarre 1.25th root. So 1.25 of that. Oh, 61 I'm getting now. Oh, jeez. I've lost all confidence in my answer now. Still it's even bigger. we'll just leave that there then.
Yeah.
I mean, this must be right because that was given in the question. Convinced that this is correct. There's not something fishy about the fact that it starts at 1 meter high? No, because this is giving us the time according to yeah. So we are substituting in 12 here. I think it's fine. If I've made a slight error here, I apologize, but did not expect it to be 61.2 years. That is one slow tree. 12 meters. I suppose 12 meters is quite tall, isn't it? But is it that tall?
Yeah.
You know, for a tree? 60 years. Oh well, whatever. So, after that, yeah. This is where I do. Should we look up the mark scheme?
We can, yeah. I have no idea how to do that.
Just this once. I'm not going to make a habit of this. I'm very surprised that this is as high as it is. I'm very curious. So, at Excel.
I think Dan is going to step in for me while I eat something, if that's okay.
Eat? No, there's no time for eating, James.
Maybe not for you.
No, that's fine.
All right, Dan. Yeah, do you wanna hop in and you can. Hey.
Hello, everyone.
Thanks. We're just having a crisis of confidence about slow-growing trees, so I'll leave you guys to figure that out, and I'll see you later on.
See. Slow-growing trees. So I've just joined now.
Yeah, just this differential equations question, and so the answer that I got was 61.2 years for a tree to reach 12 meters. Now the question does say that the trees grow slowly. They are slow growing trees. But I did not expect the answer to be 60 odd years, and I cannot for the life of me see any mistake that I've made. So I'm just interested in this. I'm not going to make a habit of doing this. I want to double check this one because I am convinced that I must have made a mistake somewhere. So, question 14. Oh, so I've not got the right answer, but the right answer is actually even higher than that. Wow.
Wow.
So my gut was right in telling me that it's telling me that it's wrong, but
Just the wrong way around.
yeah.
Oh, gosh.
So where have I gone wrong then? Where have I gone wrong? Very curious about this.
Looking at this for the first time, so I'll try to catch up.
Yeah, it's all right. I'm going to move on in a second. I don't want to.
Oh, yeah. Don't dwell. Yeah.
If I dwelled on every question.
Well, you'd still be on that. You'd still be in the Key Stage 1
Yeah.
exams. Oh,
Some tough stuff there.
yeah, there were some tough ones there.
So. can't even follow this mark scheme. They've done something really weird here. Instead of writing 2 root h, they've written 2 4 minus root h. And I don't even know where that comes from. Like, why would that be there? Starting to feel like maybe they've made a mistake. Sure they haven't, but
that'd be something.
right. Let's just move on. Let's just move on because I could spend all day on this, rethinking it, but whatever. Can't see it. I might come back to it now that I know that it's not right. If you are watching and you see my mistake, please put me out of my misery and tell me where it is.
Is there a tally for the people that that have pointed out mistakes? I reckon James Gill is probably winning.
But if he loses a point every time he corrects one that isn't right, then you know,
he's probably he might be below par.
Yeah. Nah, he's all right. So that's 7 papers down. So what is that? That's just short of a third, and we're coming up on a quarter of the way through.
Yep, so, 6 hours.
Yep. Not bad. So I've got a few of I have done a lot of the easy papers though. So you know, I've kind of banked some time there. I think we'll conclude our journey through our mathematics. Sorry, I can't even get the words out now. Only 6 hours in. We'll conclude our mathematical journey with a degree level paper. That's what the one that we'll do next. And I actually want to spend a little bit more time on this than I did last time, because I think a lot of people switched off at this stage and were like, I just don't know what's going on. So I want to use that time that I've got banked just to discuss it in a bit more detail and why there is such a sudden shift in the content between the A level and the degree level, because we've seen the mathematics like slowly progress. You know, we've introduced a few things here and there. We've introduced calculus. At A level we introduced trigonometry at GCSE. We introduced ratio at Key Stage 3. And you know, these kind of incremental things. The degree paper is going to look completely different. It's going to look not even like the same subject, and there's a good reason for that. So I do want to spend a bit of time and try and explain why we take such a different approach at that level, and just explain some of the questions a bit more. So I've got a comment from Catherine Wellsford just saying that 61 years feels about right for a redwood. It might be. I know nothing about trees. I just didn't expect. Maybe some trees do grow so slowly. But
I think 61, because I mean, how long do redwoods even live? I mean, they can live hundreds of years, right?
Yeah, but so can, I mean, a lot of trees can live a while.
Sorry, they can live up to 1,000 years on average.
Wow.
Right, so 61 years old. I mean, maybe it's a little bit like Baby Yoda, you know, where the dude can be 150 before he's even adolescent, you know.
That's a good point. But that's only to get to 12 meters, which just seems like quite an unimpressive height, you know. So anyway, okay.
Yeah.
I will be back in just 1 minute, and then we'll do this degree paper.
Excellent. Oh, I didn't realize that the Grand National was on for that time of year already. Did anyone win any money? For those just joining, Alex just popped out. He'll be back in a moment.
Okay, so I'm back. I don't suppose you know who the Grand National winner was, because I did have a sweepstakes with my group. Do you know?
So let's have a look. Google. Okay. Noble Yeats.
Noble Yeats.
Noble Yeats, traditional spelling.
And I had Death Duty, and I had Noble Yeats. Yes. Oh, incredible.
Well done.
Oh, why did nobody tell me? Oh, I muted all of this this chat. Oh my god, I think that's the first time I've ever won that thing. I've got a friend who, whenever we do anything like this, he will win every single time without fail, which probabilistically is anomalous, but right, okay, so good stuff. I don't know how much I'm going to win there, but I will put all of that towards Refuge, the charity that we are supporting today with this live stream. So thanks to all of those who are still with us. Here is a degree level paper. Oh, and I actually need some paper to answer this on. So, first thing is about truth tables. Okay, so this is the paper that you would sit at the end of your first semester of first year. So this is a very kind of basic, it's about logic, it's about, it'll be some set theory in there, and there will be some number theory in there as well, because set theory, as I mentioned before, it is, I cannot understate how important it is. It is the underpinning of all of mathematics, so it's important that you get a good handle on that early. Number theory, I think we do number theory so much in first year because you spend a lot of your first year learning how to prove things. And number theory is just a really nice, accessible way of practicing proving stuff. You know, you want to be able to prove stuff about anything, you know. So I'm a group theorist, so I'm looking at groups, so which is an entirely different mathematical structure. But in order to kind of practice your proof skills, then numbers is something that you're already hopefully pretty familiar with. So that's why we look at a lot of number theory. So truth tables. Okay, so what we've got here? You've got a statement P and a statement Q, and these could be any statements. They're usually mathematical, but P could be something along the lines of, 3 is even. And, you know, the only rule with a statement is it has to have a truth value of true or false. Obviously, the truth value of this is false, but we need to talk about statements in general. So if you imagine the options for P and Q, they could either both be true, the first could be true and the false second, other way around, or they could both be false. And we use truth tables to, like we do with algebra, we combine variables together, like x's and y's and things. We also want to be able to combine statements together using not addition and multiplication, but by logical operators. So things like not P, what that means is not 3 is even, or in other words, 3 is not even. In other words, 3 is odd. So it's the kind of opposite statement there. So what we call it the negation of the statement. So whenever P is true, not P is false, and vice versa. And we have things like, P or Q. Globally, that whole statement there is true if one of them is true or if both of them are true. So, if I say something like 3 is even or 4 is even, then this entire statement here is a true statement because one part of it is true. If I said and, then this is now false because and is only true when both of the statements are true. 3 is even and 4 is even overall is false because we have one of them being false. So that's kind of what we're doing here. I don't know if that makes any sense at all, but yeah. Let's jump in then. So the first one is P implies Q. You've probably seen me write this symbol. It does have a very specific meaning. So implies, it means if, so P implies Q means if P, then Q. And we use that for deductive purposes. So for example, if x is equal to 2, then 2x is equal to 4. That is true. So we could write that mathematically as x equals 2 implies that 2x is equal to 4. Of course, 2x equals 4 also implies that x equals 2. So sometimes we can write it like that. So it is, when is this overall thing true? If x is 2, then 2x equals 4. Well, if they are both true statements, then we have true here. If x is not equal to 2, and then we say that 2x is equal to 4, well, that isn't true overall. So that is false overall. Where it gets a little bit confusing is if x is equal to 2, then 2, I don't know if my example is going to work here, but imagine that x isn't 2. So the first one is false. So x is some number other than 2. Then can we say that 2x is equal to 4? Well, so this would also be false then, wouldn't it? But I don't know if there's a. I know why.
I've honestly never had a very good intuitive answer for the third line. False implies false implies true.
Okay.
Never been able to think of a good one.
Yeah, so this is a bad example, isn't it? So this has got us so far, but I do have so the intuitive approach I try to take. This helped when I taught a class of first year students. I think it clicked for some of them when I did this. Imagine this is imagine I've got a load of statements written down on this piece of paper, and these are all the statements. How did I used to say this? So right, well, because the answer here is that these are true, and this is a really counterintuitive point. There's a few ways of explaining this. So the point being, if P is false, then nothing can be said about Q, is the way that we generally think about this. If P is false, we cannot determine the truth value of Q. So Q could be true or false, and overall it'd still be true to say it.
Yeah, I was thinking about like if you assume that 50 is smaller than 10, then it's also smaller than 100.
Yeah. So you've got something that's clearly false. Then it's smaller.
And it implies that it's smaller than 100.
But does it? Yeah. I don't know. I think this is falling into the same kind of difficulty as this. Let me show you this kind of Euler diagram here. So imagine if you're in this circle, then P is true. So imagine P is making some kind of statement, and you could try different values, and you are in here if P is true, and you are outside of here if P is false. Now, if it is indeed the case that whenever P is true, then Q is true, then Q true must look like this. So a fried egg kind of model, because you cannot possibly be in P and not be in Q then. So whenever P is true, then you're automatically in the space where Q is true. Now, if P is false, you have no idea whether you are in the Q true or Q false part. But you do know that the only completely not valid space here is the space in which P is true and Q is false. You cannot be inside P and outside Q. So that's why it's false overall. So this kind of fried egg diagram that's the kind of how I explain it. But it's, yeah, I do appreciate it's a bit of it's an awkward one.
Really unintuitive. Yeah,
It is.
yeah. There's one in the chat from Catherine, which is could you do x equals 2k? If x equals 2k, then x equals 2k plus 1 for false proofs true.
X equals 2k, then x equals 2k plus 1. So if this is false, then it could be the case that this is true. And it could be the case that this is false. Because we actually don't know what x is. So yeah, I think maybe this is,
But if it's not even, then the number must be odd.
Yeah. I think it's just, I don't know. It's one of those, as our lecturer used to say, you need to sit in a dark room and think about it for a long time before it makes sense.
Yeah. Charles Walkden used to say, if the moon was made of cheese, then I'm a kangaroo, or something.
Yeah, exactly. Yeah, which is
one of them.
Which is only false if the moon is in fact made of cheese and he is not in fact a kangaroo. But yeah, I mean, you never really need to use the idea. It's just about whatever is logically reasonable. Okay, anyway, so we have some more of these. So we need another setup here. T, 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 F, F, T, F, F. Not P, therefore, is like this. So whenever P is true, not P is false. And then not P or Q. So this is true if either of the inputs are true. So only there, because if we're looking at these two columns here, do we get that? Let's do P and Q. So this is going to be true and the rest false. So only true, P and Q is only true if both inputs are true. And now we want to have P if and only if. So that's what we call that double implication. And we're running out of space. I'm going to use that that little hat means and in logic speak. So P if and only if. This is only true when they match. So if they're both true or if they're both false. So true, false, true, true. P if and only if P and Q. Yeah, because most of the time P is going to be whenever P is false, then P and Q is false. So we hit those. But yeah. So that's that one, and the last one let's just draw up another table here. So T, T, F, F, T, F, T, F. Again, our lecturer used to warn us against don't write that, the infamous TF symbol. But if you accidentally draw a T, then you kind of want to fix it to an F like that. So we'll do P implies Q. So T, F, T, T. Oh, I've used a single arrow there. Usually in logic, use a single arrow. And then we have another. Oh, we've got R. I should have read through the whole question before starting that. Let's start. Just need to start the whole thing again. So P, Q, and R. So true 4 times, false 4 times. So yeah, just like with numbers in algebra, we can have more than 2 kind of statements involved. But there are now 8 possibilities for the truth value of each of these. So true, 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 false, true, etc. So P implies Q. So this is only bad if it's TF. So that's bad, and the rest are good. And P implies Q does not imply R. So this is what we would do in the implies case, but negate it. So let's do only the TFs are good this time. Reading backwards, so TF is good, TF is good, TF is good, so the rest are false. So it's the first time you've seen anything like this. You know, maybe you don't fully get it straight away. I'm just trying to give a kind of broad, what are we actually doing here and why? Because maths, you might think is all about numbers, but the way I think about maths is numbers are just a special case of what maths is about. Maths is about anything in which you can have, you can assign truth value. So you can talk about numbers, you can talk about matrices, you can talk about groups, you can talk about basically anything that has any kind of, I even hesitate to say pattern to it. You know, mathematicians, we generally we're drawn to things in which we can seek patterns, but it's much more broad than that. And numbers are just like, they just happen to be the easiest example of things that are worth working with. So that's why we spend 18 years learning about numbers, and then we try to say, okay, what about in generality? Would you kind of agree with that, Dan?
Yeah, I always understood it as like, this really is setting out what rules are there, like what can you do, what can't you do to make a series of logical deductions to keep you on the right path. Once you, and I think when previously we were just talking about how if you assume that something is true, then if you assume that something that is clearly wrong is true, then you can prove anything that you want.
Yes.
Right? If your initial set of assumptions are bogus, you can piece it together however you want to prove anything. And I think that's where that's what this is really trying to set out. It's like, okay, you have to, if you can only follow a certain set of rules to continue on like a logical path.
Yeah, I totally agree. And again, this first year stuff, it's really just trying to introduce you to the idea of proof, because with mathematics, proof is the objective. We want to make true statements about mathematical structures. First year philosopher, they would study, I'm sure, day 1, lecture 1 would be logic, and it would be, it would be about, it'd be a very similar sort of thing. what is deduction, because people use the word deduction colloquially, even though it means something very specific. You know, what is modus ponens? What is modus tollens? What is, you know, what is abductive reasoning? All that kind of thing. So they would be doing the same sort of thing, which is why, you know, a degree in maths with philosophy still remains a bit of a classic choice in some institutions. What on earth is going on here? So let me break this.
Looks a lot of Greek.
Yeah. It looks.
Some of it is.
Looks good though, doesn't it? So Z, this big bold Z here. This is referring to the collection of all the integers. So we can have any integer we want as any whole number, positive or negative. To say that something is in Z basically means P is equal to some integer. So if P is a member of this, so for example 2 is a member of the integers, you know, that's what that little E means. It means element of. And these quantifiers, this is saying for all. So for all integers, I've written that down wrong actually. So for all integers Q, so given any integer Q, and then the other quantifier means there exists. So there exists an integer P such that P plus Q is less than 0. So it's saying that. So to choose an easier example, for all integers x, there exists a y such that x equals y. You know, the easiest. So if you give me any integer, I can find an integer that's equal to x, and I just choose
23.
Then I choose 23, and that is actually equal to x. So we win. So this overall is a true statement. If I said, you know, if I said that there exists an x in Z, such that for all y in Z, x equals y, then we've got a problem, because I'm saying I can find one specific integer x such that whatever y you choose, x is equal to y. And that's not true. Whatever I choose as my magical x, if I just choose y to be 1 greater than x, then we don't have equality. So this overall is a false statement. So this is kind of what we're doing here. So if you start with any integer q, can you find some integer that when you add it to q, you'll bring it into the negatives? And this is true, I would say, because imagine you give me q, and then I say, okay, then I give you minus q subtract 1. And then when we add these together, we have minus q plus q minus 1, and that is equal to minus 1, which is guaranteed to be less than 0. So it's just about, you know, getting us used to the idea of proving things and using these quantifiers and things like that. And yeah, I mean, my example here was quite a natural one, because now it's the same sort of question. This is saying that there exists some special p such that for every possible q you could give me from the integers, p plus q is less than 0. And this is false, because, okay, here's your special p. It's not the case that whatever q I add to it, we end up negative. Because I choose to disprove this, I only need to find one specific example in which it breaks down. I will choose minus p plus 1. And then when we add them together, we get p plus minus p plus 1, which is 1, which is not less than 0. So I have found a specific case in which this whole thing breaks down. Okay, question 3. So there exists a p z, so there exists an integer such that for all p in z, I've written this down again, I don't know why my eyesight is failing, so there exists some special q in z such that for all p in z, q is less than 0. Now this is one of these like trick question type things, because you'll notice that p isn't even involved here. So this is overall true because there is some special q such that q is always less than 0. So if I choose q is -1, then -1 is less than 0 for whatever value of p that I choose, because p doesn't even factor into this question here. So a bit of an awkward one, but there it is. We sometimes say it's vacuously. Well, we don't say vacuous. Vacuous means something a bit more specific. But so here there exists.
I always thought of this. I always thought of this like a game. Like player 1 chooses there exists.
Yeah.
And then the player 2 needs to outsmart them somehow.
Yeah, exactly. Or are you confined to the question? You have to do it that way. So there exist p and q in z. So this means there's some special p and there's some special q integers such that 2p plus 4q is equal to 1. Remember that you might think this always has to be positive, but remember we are allowed to have negative integers. So you might say, okay, 2 times 1 plus 4 of minus 2 is equal to 0, which is close to 1. But no matter what you do, you will never actually make this work, because we can factor out p plus 2q is equal to 1. This over here is an even number because it's 2 times something. An even number is a multiple of 2, so it's 2 times something. And this over here is odd, and an odd can never be even. So this is false overall. And question 5. Okay, something a bit meatier for question 5. So this is saying for all p and q integers, if p plus q is less than 0, so if they add up, so it's not saying that all integers will add up to something negative, it's saying given any integers that add up to something negative, is it always then the case that p plus 2q is negative? So how many examples of this do we need to find in order to prove this statement false? 1. We just need one example. We need p and q such that they add to something negative, but when I do this, we get something positive, and that will disprove the statement. Usually you jump in trying to disprove it, and if you can't disprove it, that's when you might prove it true, but this is definitely going to be false. So let's choose q equals, so we want it so that when we make q bigger, we dip into the negatives. We dip into the positives, don't we? So we definitely want, if we do p, so q's got to be the positive thing. We'll do p is minus 2. See if this works. And q is equal to 1. Then p plus q is equal to minus 2 plus 1 is minus 1, which is less than 0. Now this does not imply that p plus 2q, which is minus 2 plus 2 of 1, which is 0. This is not less than, that's not strictly less than 0. If you wanted that to be a bit neater, this is the mathematician's answer, isn't it? But if you wanted, if we do something like p equals minus 3 and q equals 2, then p plus q equals minus 1, but p plus 2q will be 1, which is definitely positive, so it's not less than 0. So, a whole variety of examples there, so that disproves that statement here. So, hopefully we're making a bit of sense. Okay.
I agree.
Say again?
I agree.
Do you agree with all my answers?
Yep.
Okay, that's good.
Thus far.
So, find a solution in the integers to this. So, this, I suppose, is a kind of extension to what you might have already done at A-level or at GCSE. So, we do a lot a lot of solving equations at GCSE and A-level. But now, to make things harder, we add restrictions to the solutions and we say, okay, solve it, but actually you're only allowed to have a solution where x and y are integers. And this makes it quite a hard question, because if you remove that restriction, then you could say, okay, x equals 1, and then I could just solve, divide, y will be something like a fraction, but it will still be a solution. But if we want x and y to be integers, it becomes a more challenging question. And this is something called a Diophantine equation, named after Diophantus, ancient Greek mathematician who was, I guess, interested in this sort of thing. And we have a technique to do this, which is Euclid's algorithm. So we are looking at 9131 and 8648, and it is a fact about numbers. I think it has a name. Oh, geez. Who was it? I reckon James might know this. Who was it? Basically, you can find integers p and q such that this holds. That is just a true thing. So the greatest common divisor, you might see that known as highest common factor. It means the same thing. So it's the highest number that divides nicely into both of these numbers. So that is true. And the point is, if we get the greatest common divisor of these two as a factor of 63, then we can multiply up to 63 to do that. And Euclid, our favorite, one of our favorite Greek mathematicians, had a algorithm in order to find this greatest common divisor. So let's do it. We have got, not to find the greatest common divisor, but to find these p and q. It might actually be Diophantus, this theorem here, but I can't remember. Anyway, so the algorithm goes like this. It goes like this. It says, try to divide 9,131 by 8,648, and you'll get 1, and you'll get a remainder. And your remainder, where is my calculator? Because even at degree level, we need the calculator. So 9131 subtract 8648 is 483. And now, I mean, when you do the proof of this, there's kind of nice reasons for this, but now we do 8648, and then we divide that by 483. So 8648 divided by 483, that is equal to 17. Remainder... Oh, it's not going to give me the remainder in a nice sort of way there. So 8648 subtract 483, lots of 17. Remainder 437. And now we play the same game. 483 is equal to 437 times 1. And the remainder, I can do that one in my head at least, 46. And 46, now this looks good. I think we're going to get... Yeah, no, maybe not. Maybe getting ahead of myself here. So 46 times something divided by 46. The reason I thought that looked good was because of the 69 here. The 69 is 3 times 23, and 2 23s is 46. So maybe we're getting to the end of it. Anyway, that's 9, and then 437 subtract 9 of 46 is 23, and there's our 23. Okay, so we're done with that. We've got our 23, because now if we try to do the Euclid's algorithm again, we get 46 is equal to 23 times 2 plus 0. So the algorithm terminates when we get a remainder of 0, and it will always terminate. But anyway, we get that the greatest common divisor is 23, and then what we do is we rewrite this in terms of what we've already written, and we keep substituting back in until we write it in terms of our original numbers. So this is 23 is equal to 437 minus 9 lots of 46, which is 437 minus 9 lots of rearranging here, 483 minus one lot of 437, which is in fact 2 times 400. Whoa. Sorry. 10 times 437 minus 9 times 483. And then we can write 437. So this is 10. 437 is 8648 subtract 17 lots of 483. And we're still subtracting 9 lots of 483. So this is 10 times 8648 minus 170 minus 179 lots of 483. And that's 10, 8648 minus 179 lots of 483 is 9131. Subtract 8648. So this is, if we do 189 times 8648, take 179 lots of 9131. Definitely going to check that on the old calculator before we carry on. 8648 subtract 179 lots of 9131. 23. Okay, good. Now, what was the point in all of that? Well, we know that 9131 multiplied by minus 179 plus 8648 multiplied by 189 is equal to 23. So in order to get to 69, we're going to multiply through by 3. 179 times 3. So 9131 times minus 537 plus 8648 times, well, we've got an extra 10, so an extra 30, so 567, I reckon, times 3, 567. So x is equal to, sorry, 587. Yeah, 567. X is equal to minus 537, and y is equal to 567. Should we check it? 9131 minus 537 plus 8648 times 567 is 69. Okay, so that is how you might solve a simple Diophantine equation using Euclid's algorithm. I'm sure there are plenty of other techniques, but that's the one that's adequate for our purposes here. Do you remember doing that, Dan?
I sucked at them. I was awful. I could never do them. And whenever I would do it, I would always feel really, really, really scared about doing that final check, because it would always be something different.
Yeah,
it would come out to be like 83 or something like that. And I'd go, oh, darn it.
Yeah, or it'd come out to be like minus 2000 and something, and it's like, oh god.
Yeah.
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 So there's nothing particularly hard about it. It's just one of those really fiddly procedures that's it's easy to get wrong.
It's one of the best exercises in learning how to not drop a minus sign.
Yeah, exactly. Yeah.
It happens a lot.
Yeah, absolutely. Okay, so we've got some permutations here. So this is, I guess, when I talked about in mathematics, we like studying numbers, but we also like to study other mathematical objects as well. Functions are the big one that we like to study, and a specific type of function is the permutation. A permutation is just a shuffling. So if we start with the numbers 1, 2, 3, 4, 5, 6, 7, 8, we can shuffle them up and finish with 5, 6, 7, 2, 8, 3, 4, 1. That is a permutation. So it is a mixing up of the numbers. But there's interesting things that we can do with them. So what are the orders of these permutations? So basically, the order of a permutation is the number of times you need to repeat the shuffling until you get back to where you started. And there's some notation that we use to help us work this out. So sigma 1 instead of writing it in this big clunky bracket notation, we're going to write it in what we call cycle notation. So 1 goes to 5, 5 goes to 8, and 8 goes to 1. 2 goes to 6, goes to 3, goes to 7, goes to 4, goes to 2. So if you want to see where the number 6 goes, you just see 6 goes to 3, and there you go. So that's just a shorthand way of representing that entire shuffling there. Okay, now sigma 2 is a composite here. So we need to find the inverse of sigma 1. So that's what that notation there means, the inverse. And this is just the same permutation but in reverse. So instead of 1 going to 5, 5 is going to go to 1. And instead of 8 going to 1, 1 is going to go to 8. So you're basically just writing them in the opposite order. 7, 3, 6. And now sigma 2 is the composition. That means we do the permutations one after another. 5, 1, 8, 2, 4, 7, 3, 6. And now let's just write this one in the cycle notation. So 1 is fixed by that permutation, doesn't go anywhere. 2 goes to 7, goes to 4. And 3 is fixed, and 4 goes to... Oh, we've already dealt with 4, actually. 5 goes to 8, goes to 6, goes to 5. 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's everything dealt with. So now we have cycles that are what we call not disjoint. We have the same number appearing multiple times. So what we do here is to find out the net result of all of these permutations. We start from this side. We ask, where does 1 go? Well, 1 at the moment doesn't change. It does finish on 8, so 1 goes to 8. Now where does 8 go? 8 goes to 6, and then 6 goes to 2. Where does 2 go? 2 goes to 7, and then goes to 3. Where does 3 go? It's fixed by this one, and then goes to 6. 6 goes to 5, and then 5 goes to 1. Okay, let's pick a different number. 1, 2, 3, let's choose 4. So 4 goes to 2, and then 2 goes to 4. So 4 is now fixed. 5 goes to 8, and then 8 goes to 5. So 5 is fixed. 6 we've already dealt with. Let's look at 7. Now, we know 7 must be fixed by this, because it can't possibly go anywhere else. There's no more numbers to deal with, so it's a nice little check. We should have that 7 is fixed. 7 goes to 4, 4 goes to 7, it's fixed. So instead of writing the fixed numbers, sometimes we just write the permutation like this. But don't be upset by the notation. We are just in full. This shuffling would look like this. 1 is going to 8, 8 is going to 2, 2 is going to 3, 3 is going to 6, and 6 is going to 1. All other numbers are fixed. We're taking a list of numbers, we're just shuffling them. That's all it is. Okay, and I'm not going to get into the argument of whether we go from right to left or left to right. It's different depending on whether you ask a group theorist or whether you ask anybody else, basically, because group theorists think we're still a little bit old school and we like to go left to right. I know my supervisor did, but I go from right to left. I think that's what's being asked here. Anyway, let's do this one. So this one's already given to us in the cycle notation. I'm not going to write the commas because usually you don't. So 1 goes to, it goes to 2. Sorry, 1 goes to 2 goes to, let's start again. 6, 6 goes to 3, 3 goes to 2, 2 goes to 8, 8 goes to 1. And then the other numbers don't feature. So it must be, 4 is just going to stay at 4, for instance. And now sigma 4 is sigma 1 squared. So 1, 5, 8, 2, 6, 3, 7, 4. 1, 5, 8, 2, 6, 3, 7, 4. And then sigma 3, which we just worked out. 1, 6, 3, 2, 8. Oh, this is a lot more work than I remember it being. 1 goes to 6, goes to 3, goes to 7. 7 goes to 4, goes to 2. 2 goes to 8. 8 goes to 1. 1 goes to 5. 5 goes to 8. 8 goes to 1. Okay, let's see where 3 goes. 3 goes to 2. 2 goes to 6. 6 goes to 3. Let's see where 4 goes. 4 goes to 2. Goes to 6. What was I doing then? I've lost my place here. Was I doing 4? 4 goes to 2. 2 goes to 6, sorry. And then 6 goes to 3. 3 goes to 7. 7 goes to 4. Like that. So we've got 1, 2, 3, 4, 5, 6, 7. If we've done it right, we should have 8 as 6th. 8 goes to 1. 1 goes to 5. 5 goes to 8. Yes. Okay, so this overall is 4, 6, 1, 7, 2, 5. I can change the order of these because they're disjoint. Okay, so what was the actual question? What are the orders of these permutations? So, let's call that question A. So, the orders of these permutations. Imagine you're shuffling these numbers around. Every 3 shufflings, this is going to repeat itself. So you do this permutation, you shuffle 1 to 5, then you shuffle it to 8, and then you shuffle it to 3. So every 3 shufflings, this one gets back to where it started. Every 5 shufflings, that one gets back to where it started. So, you know, it's a bit like music, I guess, how I think about this. You know, every 3 beats, one of them goes back to the start, but then the other one only goes back on 5 beats. So it takes 15 beats. So the order of sigma 1, well, usually I write it like this actually. So I did in my thesis anyway. Order of sigma 2 is just 5. The order of sigma 3 is also 5. And this one, so every 2 beats, that gets back to where it started, and every 4 beats. So it's going to, after 4 shufflings, 4. Okay. And the next question asks us, which 2 permutations are the inverses of each other? Well, to be inverses, they have to have the same order. So it's between these 2, and yeah, we can see 1, 8, 2, 3, 6 going backwards, 1, 8, 2, 3, 6. So sigma 2 and sigma 3 are inverses of each other. Whew. Okay, right then. Anything to add on that one, Dan?
No, I think that was fairly straightforward for those people that have just tuned in and thinking that your GCSE papers were a lot harder than this, were a lot easier than this, sorry. We are doing a first degree level paper. I think this is Manchester University sets, numbers and functions.
Yeah.
What year of paper is this? I didn't quite get.
I think it's 2012 actually. So
2012, so that's year after us?
Year after us, yeah. So yeah, January. So yeah, we did the 2011 paper, yeah. Again, I just saw it was publicly available and then got one. Okay, so prove that 7 does not divide that for any integer a. So we're getting into the number theory now. But we're asking the sorts of questions that we might not have considered about numbers before now. So this is in a branch modular arithmetic. So we're basically this area of number theory is just interested in divisibility. When are numbers factors of another, and what kind of remainders can we expect when we do our divisions and things like that. So for a question like this, we are going to reduce modulo 7. So imagine we are dividing this by 7, and the only options, once we, you know, if we reduce this whole thing, we reduce a mod 7, then we only have 7 possibilities for what a could be. So what I'm doing here is, for example, 14 is the same as 4 modulo 5. We take off chunks of 5 until we get our remainder. Or this is the other way of saying 14 divided by 5 has remainder 4. And it turns out that some nice things happen. So for example, 14 times, let's do another number, 6. The remainder when we divide this by 5 is the remainder of this when we divide by 5 times the remainder of this when we divide by 5. So 14 times 6 mod 5 happens to be 14 mod 5 times 6 mod 5. And that makes our life a lot easier. So it's 4, 1, so it's 4 mod 5. And if we were to actually do that calculation, so that is 60, what is 6 times 14? My head's gone, 84. So 84 mod 5, when we divide that by 5, we do indeed get 4 mod 5. Yeah, so it works. And the advantage of that is if we have something like 14 squared mod 5, then that is 14 mod 5 times 14 mod 5. So we can kind of dissolve this mod 7 into all of these variables here and only consider a mod 5. And a mod 5, a mod 7, whatever number a is, its remainder after dividing by 7, it could only be 0, 1, or 2, all the way up to 6. They're the only options for what it could be. So let's have a little table here, shall we? We'll do what are the possible options for a mod 7? As our lecturer used to say, in the universe modulo 7, there are only 7 possibilities. So, and then that's 2 plus a squared plus a cubed. So when a is 0 mod 7, then this whole thing mod 7 is 2. When a is 1 mod 7, then this whole thing is 5. Okay, it gets more difficult when we actually have to do something. So 2 plus 2 squared plus 2 plus 2 plus 2 squared plus 2 cubed. That's 16, which is 2 mod 7, because it's 16 divided by 7 is 2 remainder 2. 2 plus 3 squared plus 3 cubed is 41, which is 6 mod 7. And we're wanting none of these to be 0. Because if you get 0 as a remainder, well then you must be divisible by 7. Like if I did something like 49 mod 7, 49 is a multiple of 7. So it divides perfectly by 7. So that's 0 mod 7. It has 0 remainder. We don't want any zeros here because the question is asking us to prove that this is never divisible by 7. So 2 plus 4 squared plus 4 cubed. That's 86, which is 2 modulo 7. 2 plus 5 squared plus 5 cubed is 157. And what is that mod 7? Well, it's the same as 17, which is the same as 3. And 6. 2 plus 6 squared plus 6 cubed equals 260, which is the same as 120, which is the same as 50, which is the same as 1. So if you're wondering how I'm doing that in my head, 260, I know if I take off a multiple of 7, I'm going to still end up with the same remainder. So I'm taking off 140 to get 120, because I know that I know that 140 is a multiple of 7, so I can reduce by that. 120, reduce it by 70, and I get 50, which is 49 plus 1, so that's where the 1 comes from. So never 0, so it's never a multiple of 7. Okay, and that takes us to the end of the compulsory part of the paper. So this is quite common in university level exams or in things like sixth form plus exams. So for example, like the STEP paper and things like that, questions do tend to be optional. If you do like the Olympiad, or if you do any the Puckman or anything like that, generally speaking, you generally get a bunch of questions and you're asked to answer just a few of them. So it's more common at the university stage. Quite common, we found, is that you have a compulsory question where it's attacking you on all of the basic stuff that you just need to know. you're going to have a hard time in your degree if you can't do any of this. So, and then it asks you answer 3 of the 5 questions. So it's giving us 5 questions to have a go at. We can choose to answer any 3 of them. If you were an absolute dork like me, what you tended to do was answer all 5 of the questions, and you get graded on your best 3. So they would mark all 5 of your answers and choose the best 3 marks, and that would contribute to your score. So
was enough time. There certainly was enough time to do at least 4 of them when we were going through it.
Yeah, in fact, I don't know if I did all 5 of these. I think you're right. I probably would have done 3 or 4. A lot of the papers that we did was just like the whole thing was answer 3 out of the 4 questions. So quite a lot of the time, that depends on the course. I would try and answer all 4 of them. But this is a 3-hour paper. You've got time to do this. Why wouldn't you try and have a go at more of them?
See, that's really interesting. I never did that. I would always just answer 3 really well.
Right. Okay. Yeah. So that's your step training there, isn't it? Where like in the step paper and things like that, you get graded for completing a question, don't you? So
you get a big bonus. You get bonus points.
So if you actually get to the end of a step question, you get a lot of marks. Whereas here it's just 15 straight, and they're probably distributed according to some scheme. So, which questions shall we have a go at? Looks like some set theory with some inclusion-exclusion principle. State the equation that determines when 2 fractions represent... Okay, some weird number theoretic stuff. Okay. Some binomial stuff. Prove there are infinitely many primes. Looks like some Fermat's little theorem. And a group theory question. Well, it'd be rude not to do the group theory question, wouldn't it? I might just do all of them. I don't think they look particularly hard. So, let's go for it. Yeah, I might speed up a little bit. But let's just do them. Or until I get bored. But a minimum of 3, I would say. So this is the set theory. So I've kind of bigged up set theory as the be all and end all. It really is the foundation of all of mathematics. And the reason it's important is because we talked a lot about truth. We talked a lot about how to prove things are true. So you start with some basic assumptions as to what is true, and then you use those assumptions to then prove other things. How do you know whether those starting things are true? So in the world of mathematics, we call them the axioms. So how do you know if your axioms are true? So you don't. You just assume them to be true. But you better be pretty confident in them. You want to develop a theory from a sturdy foundation. You don't want to develop a theory from some axioms that create true statements within that framework that are not useful. So if you start with some dodgy axioms, you can prove true things that are true with respect to those axioms. So if you start with the assumption that 2 is bigger than 3, then you can prove that 4 is bigger than 2. It's just not very useful because the way we use numbers is not like that. So you want to start from things that your axiomatic system needs to be a kind of something that makes sense. In the world of philosophy, we call those the presuppositions. So I don't know why that shift took place between the vocabulary there, but your presuppositions, they are the things that you take to be true without proof or without evidence. So, for example, I think most philosophers would take the 3 foundational laws of logic. That is the law of identity, the law of what are the other ones? Non-contradiction, and the law of excluded middle. So they're basically saying that whenever you have something X, then X is always equal to X. That's the law of identity. And the law of non-contradiction says that any statement P must it cannot be simultaneously true or false. So you are assuming that every statement is true or false, and the law is excluded middle that says that every statement must be true or false. You know, it must have some associated truth value. Paradoxes are not considered statements, so I know some of you listening might think, well, what about paradoxes? Well, we just don't consider them to be statements. So so you start with those things because they seem to be self-evident. You know, that when we make a statement, it's either true or false, and that's the theory that we want to develop. Where set theory comes in is it helps us to establish the axioms that we use in order to derive all of mathematics. So like you can define the numbers in terms of sets. You can define everything in terms of sets. So everything comes from sets. So that's why somebody listening is probably saying, all right, just shut up and get on with it. But that's why we want to, to make sure our grasp of sets is tight. So we have 3 sets. Now, so this is a bit of set theory notation. Now, we've already seen a bit of this notation in that GCSE Venn diagram paper. So A union B. So we have numbers and we do operations to them, like addition and multiplication. We have sets and we do operations to them, like union. So this is the set of elements x such that x is in A or x is in B. So imagine your Venn diagram. This would, if this is A, this is B. A union B is all of that stuff there. It's in both sets. So in one set or both. And A less C, that's the like subtraction, if you will. It's x such that x is in A and x is not in C. So if you wanted your Venn diagram A, C, you want to be in A, but you don't want to be in C. So it's actually this little, what I think of a crescent moon sort of shape there. Show that. So we're going to show that if we union A and B together and take C away, then that is this symbol means it's a subset. So it means that everything in here is in here. So a subset is something that looks like the fried egg. So if we've got sets X and Y, X is a subset of Y. Everything that is in X is in Y. Is a subset of A less C union B. Okay, now the way we do this is we choose an element in here and show that it must in fact be in here. So let X be a member of this horrible thing over here. So that implies X is in A union B and X is not a member of C. Now, either X is in A or X is in B, because it's in the union. If X is in A, then X certainly lives in X less C. Therefore, X lives in A less C or B. But if X is in B, then automatically X belongs to A less C union B. So, proof. Describe how this formula simplifies when A is equal to the empty set. So the empty set is just the set of all, the set containing nothing. It's the zero of the set theoretic universe, if you will. And if A is the empty set, then the empty set union B is just B. So we get that B less C is a subset of the empty set less C is just the empty set, because you're saying you're in the empty set but not in C, but you can't be in the empty set. This is the empty set. Union B. So it's just saying that B less C is a subset of B, which is true because this is everything in B and takes some stuff away, and this is everything in B. Okay, so given disjoint finite sets D and E, state the addition principle for the cardinality of D union E. I don't know what the addition principle is. I think it's saying that. So what I would say here is that the cardinality, that just means the number of elements in the set. The cardinality of D union C is less than or equal to D plus C. Either of you want to weigh in on that?
I think it's the fact that it's emphasising their disjoint sets, isn't it?
Oh, they're disjoint. So if they're disjoint, then our Venn diagram looks like this: C and D. So the union literally is the sum of all the elements.
Are we doing B6 part 2? Sorry.
Yeah, we are. Yeah, I've
Yeah.
added.
So it's D, isn't it asking about D union E rather than D union C? It's D and E that are disjoint
Oh
finite
yeah.
sets.
Sorry.
Yeah, that's okay.
E fixed.
Yeah.
I don't know why I did that.
So yeah, I think the addition principle is exactly what you said, which is that if they're disjoint and finite, then the cardinality of the union is the sum of the cardinalities of the sets. Yeah.
That's fine. Explain the modification required when D intersect E is not the empty set. In other words, when now I'm going to go with my original answer here. I'm going with that one because if it's not equal to the empty set, oh well, if we actually explicitly given that it's not the empty set, then it is strictly less than. By substituting D equals A union B and E equals C into your formula, prove that. The inclusion-exclusion principle with 3 sets, isn't it? So, we know... Alright, so A union B union C. That is equal to D union C. I know what that wanted. What it wanted was this. It wanted D union E is equal to D E minus the size of the intersection. That's what it wanted.
Yeah, absolutely.
Because, again, for the uninitiated, if you add up all the elements of D and then add up all the elements of E, you've overcounted the middle. So you've got to take that away, and then you'll have a full count of the whole union. If that makes any sense, I don't know. So
yeah, and I think that's exactly the explanation they're looking for. I think they probably want to see the Venn diagram.
No, I think they categorically do not want to see any Venn diagrams. They have a big bee in their bonnet about that. But
really?
Yeah.
Oh God.
Yeah.
Oh well. Okay.
Can't prove things with pictures.
Yeah.
Oh dear. Okay. Well, so much for my attitude then.
Well, you weren't with us in first year, were you? So
no, I wasn't.
You might have missed the Venn diagram vitriol. So, because and the reason I knew it was going to be that is because we need some more meat in our formula if we're going to start messing about with that. So, we've got A union B union C. So, every time I see a D, I'm going to write an A union B. And every time I see a E, I'm going to write a C. Minus, so this is A union B intersect E. Yeah? Okay, and now I guess we do some set theory here. So A union B we know is that minus A intersect B. We've got the cardinality of C. And now this, I'm assuming that we are allowed to assume this. This is it. This is the same as A, I've written E again there, C. A intersect C union B intersect C. It's easy to prove that intersection distributes across. Again, if you want the Venn diagram proof, which you can't do, but A union B intersect C is that little bit there, isn't it? So A union B, and it's all of that. So if we imagine colouring in A union B, and then taking only the part that's in C, that is the same as A intersect C, and unioning it with A intersect B. So they are the same, you know, proof by Venn diagram, but you can prove it set theoretically as well. So A, B, C minus A intersect B minus, so we've got the cardinality of A intersect C plus the cardinality of B intersect C, subtract A intersect C intersect B intersect C, which is just A intersect B intersect C. So this is A, B, C, A and B, take A and C, take B and C, plus A intersect B intersect C, as required. And the reason this works is because if you want to count everything in here, you need to do A plus B plus C, but now you need to get rid of A intersect B, and then you need to get rid of A intersect C, and you need to get rid of B intersect C. So you've kind of made, you know, imagine you've got one count of each of those, you've got two counts of those, and you've got three counts of those. By taking away all these intersections, you've reduced those to one, but then you've actually reduced that to 0. So you need to add in the plectrum, I call it, in the middle. You know, the you know, that Rolo rotor, whatever it's called, that shape in the middle. So you need to add it back in so you've got one count of everything. That's why the inclusion-exclusion principle on 3 sets works. Oh, I think, you know what? I think I'm gonna hate this question. 3.
Well, this is perhaps one of the only times when you see that. Well, I mean, the real question is, why does someone have 144 scarves? Like, it's a bit excessive. And the thing is, with some of these maths problems, you can have 144 scarves and no one bats an eye.
Yeah.
Like,
yeah.
it's just okay. Yeah, fine. Yeah.
Yeah, I mean, they've tried to add some content. It's probably, see, the thing about these papers is that they're always written by the actual academics. So it it could just be one.
Last year it was probably beads,
Yeah.
right? 144 beads.
It'd be one guy who's just like, what, a really eccentric mathematician in the department who's just really into scarves, and he's like, oh, we'll make it a scarf question. You know, we all love scarves.
Nigel Ray always wore a scarf.
Yeah,
So-
yeah, he did.
And he probably wrote this.
Okay, so how are we going to do this? Well, let A be the set of long scarves, B the set of green, and C woolen. Whoops, woolen. I promise you that's what it says. Because this is exhaustive. We don't need a set of short scarves because we're basically just saying if you're not in A, then you're a short scarf. So then the information given is that mod A is 75. The size of B is 69. And that is 68. Long green is saying long and green, so in A intersect B is 38. Long woolen is A intersect C, which is 40. Green woolen is 36. Long green woolen, so in all 3 sets, is 23. Calculate the number of short black cotton scarves. Okay. So, Now, the annoying thing is, I think it might have been actually easier to set this up the other way.
But wouldn't you do it's 144 minus the cardinality of A or B or C there?
Yeah.
Because you want things that are not like
yeah,
and not.
Yeah, so yeah, that's it, isn't it? So we want not A and not B and not C. That's what we're looking for. And then there's a nice thing called De Morgan's law, which tells us that this is not A or B or C. So that's that's the total minus the cardinality of A union B union C. I just wondered if there was a way to set it up differently that would be a bit. I don't think there is, and
I think the first I think I might have like looking at this I might have done A is short, B is black, and C is cotton. But I think you can get to it with this.
yeah, the problem with that is like, what would A intersect B be in that case? Because it's not the same, is it? Yeah, because I was just thinking, could I do something clever? And I don't think so. So 75 plus 69 plus 68, subtract the intersections, and then add in the big intersection is 121. So 23 is the answer. All right, and that concludes that question. So next we have.
Sorry, can I just have a look at that again?
Yep.
Does that seem intuitively right?
Yeah, I think so. I think it's a coincidence that it's the same as this, but yeah, it's a big intersection.
Oh, sorry. Yeah, yes. Sorry. Yes. No. You're absolutely right. Sorry, I was on a little bit of a delay, and I thought the answer you put was 121. No. 23. Yeah. That seems more reasonable. Yeah.
Yeah, I think. Yeah. How is the delay, by the way? Because I think before it
It's
was quite good, but I know it changes.
it's like 5 or 10 seconds, perhaps.
All right.
Yeah, it seems to have got a bit worse as we've been going.
Well, it's as the day goes on as well, isn't it? So when more people start using the internet and such.
Yeah, true.
Do please remind me at 8 p.m. To make sure we switch over to the next YouTube video.
Sure. Yep. I will set an alarm.
I'll have this paper finished by then, I'm sure, which will be 8 papers in 8 hours. Not the kind of time I would like to make. I don't need to do all these questions. I just want to. Okay, state the equation that determines when two fractions A over B and C over D represent the same rational number. Well, surely A on B is equal to C on D if and only if AD minus BC equals 0. Is that what it was? Describe the set of fractions representing 2/3. So 2/3 equals, let's say, x over y. That's true if and only if 2y minus 3x equals 0. So it's the set of all x over y such that x, y integers and 2y minus 3x equals 0. I think that's what it wants. Under what circumstances is a fraction in lowest terms? So x over y, a rational, is in lowest terms. Something you've known since school, you just plain never formalized it. Lowest terms when the greatest common divisor is 1, or when they are coprime is how we say it. Explain how to express the fractions that and that in lowest terms. What? A over B minus C over D is equal to AD minus BC over BD. And A over B times C over D is equal to AC over BD. But we don't know if they're in lowest terms because we don't have any clue what these numbers actually are. And then I say it says explain how. So from here we just divide numerator and denominator until fraction is in lowest terms.
Can't you just oh wait, no, never mind. Sorry.
Okay.
I was gonna say yeah.
Yeah, because it's not something you can just do in generality, is it? You know, you can't just say that.
Well, I mean, yeah, you keep doing that until well, couldn't you find the greatest common denominator of AD minus BC and BD?
I think it just depends entirely what the numbers are, you know.
But
if I was getting a computer to do it, I would probably just get it to prime factorize the numerator and the denominator.
Yeah, I mean that's yeah, but it's I don't know. It's not like I don't know.
It's not it's not a thing.
Yeah,
it's a weird question.
At this stage of the paper is when I would think I'm not entirely sure what B7 is all about, and I move on to B8 and answer that question. Is honestly what I would do. Now this is just a GCSE question these days. You know, find the rational number represented by a recurring decimal. You know, there's all sorts of these questions now. So we play the game of let x equal 2.375858. But curiously, it's done an iteration of 58, and then it's gone. I'm just going to do that. And then 100x is 237.5858. So the reason I've done that is so that when we do 100x subtract x, the recurring parts cancel, and we get come on, you can do this with a calculator, 0.21532, like that. Don't trust my arithmetic at the moment, so let's just do it. 2.37. Oh wow, that was way off on that. Why was that so wrong? Oh, it's because I typed it in the calculator wrong. I don't even trust. I'm checking my answer on the calculator and checked my answer on the calculator by realizing it couldn't be right because it wasn't what I'd written there. So it defeats the point of the calculator, really. So x is equal to 235.21 on 99 in lowest terms. I should have stated here and xy in the integers. It's implied by this, but you know 21 over 9,900. And is that in lowest terms? Well, Mr. Casio, you can tell me. Looks like it is. Yeah, it's not giving it to me any simpler, so let's assume as such. Define what is meant by a denumerable set, and it's a great word, just not a word that really gets used very often. I know this denumerable, we never say denumerable. I think denumerable means, it doesn't quite mean the same as countable. I think denumerable means finite or countable, whereas countable tends to refer to
yes, you're right,
infinitely.
That's...
Or is it the other way around? Does countable mean?
It's one to one with countably infinite set.
Yeah, so I think countable means finite or countably infinite. I think denumerable means countably infinite. So
Yes.
A is denumerable. I love the word though. If there exists some function f from A to n, f bijection. Usually from n to A actually, but sure. Explain why A is denumerable if and only if it can be given as a list. So if A is denumerable, then f from n to A exists. So 1 maps to A1, 2 maps to A2, and so on. So A can be ordered as A1, A2, etc. Conversely, if A can be written A1, A2, and so on, then define f from the integers to A by f of I equals AI. Then f is bijective as AI equals AJ implies I is equal to J. And it's going to cover A because it can be written in that way. I think that'll do, won't it? Use this fact to give a brief outline of the proof that the set of rational numbers is denumerable. Oh, jeez. So we've got, how do you do it? 1 over 1, 2 over 1, 3 over 1, 4 over 1, and so on. So this is the diagonal, well, it's not the diagonal argument, but it's similar. Over 2, over 3, over 4, and so on in all directions. And then delete equivalence fractions. So I'll do these are all 1, aren't they? So we'll delete all of those. 4 over 2 is the same as 2. That's the same as a half. Something like that. And then what you do is you go like that, scooping up all of the fractions. So your list goes from 1 over 1 to 1 over 2 to 2 over 1, 3 over 1, 1 over 3, and so on. So it's written in the form, you know, which is in that form, isn't it? That we showed. It's denumerable by the previous part of the question.
Yeah, I actually don't think you need to delete the equivalents, to be honest.
Well, I suppose when you compile them in a set, then it's assumed that the duplicates get deleted because it's not a multi-set. But I think in terms of defining a bijection, it's just a bit cleaner, because if, for example, 2 is the same as 1 here, so if our bijection would have f of 1 equals 1 over 1, 2, 3, 4, and f of 5 is equal to 2 over 2.
Ah, gotcha. Yeah,
So
you do need to get rid of them.
It's no
Yeah,
longer
yeah.
injective. So
Gotcha.
yeah.
Gotcha. In order for it not to be a
I know,
multifunctional.
it's just a shame.
Yeah.
It's actually, it's interesting you mentioned that, because it's the part of the proof that I've never liked, because there's something nice and elegant about the idea that you can spread all of the positive rationals at least, in this kind of, you know, grid. It's so nice. And then there's the step of magically delete the duplicates. And it's like, well, how do we do that? We just assume that it can be done. And if it can be done, I'm sure, it's all fine. But you know what I mean? It's just adds a touch of messiness to an otherwise really elegant proof.
Yeah, definitely.
Okay, so pressing on, we've got let A be the set of size n. Explain what is meant by that. Well, I'm going to go out on a limb here. I'm going to say, I actually don't know what this is. I think this is all of the R element subsets of A, because that looks like the power set of A. So the curly P R of A is all of the subsets of A such that they are of size R. And NR is the number of ways to select R objects from N objects. If we want, we can write it like that. Don't know what it wants really. Assume A is not. I think that's supposed to be the empty set, but they've screwed that up because that's a phi, isn't it? I remember there's a bit of a divide among mathematicians. So in LaTeX, which is the kind of word processing system that we use to type out things like this, if you type in \empty, I think it is, it comes up with like the 0 with a line through it. But I and many others prefer the more rounded one like that, and it's something like var empty that you type in or something like that. I don't know what you prefer.
I'd just write a 0 and then draw a line through it.
I prefer that one. Assume A is not the. I'm going to assume that it means the empty set. They've done It's funny that they've done that typo, because to actually type that, it's \phi, and I also do \var phi, which is the nice kind of curly phi and not the boring one like that. Choose A from A and construct a bijection. Okay, so we need a bijection here. So let A1 to AR be a member of this thing. Where does that get mapped to? So if A is in there, it needs to go one place, and if A is not in there, it needs to go another place, is what I'm thinking. So if A is in there, then without loss, assume A is A1. Then map this. Where are we going to map this? Map that to. So we're unioning it. So it's still a size R, isn't it? So we want to map it to this one. We want to map it into there, and we map it into A2. So just delete A1, which is an element of that. It's an R-1 size set taken from the set of A less small a. If A is not a member of this, then this set gets mapped to itself, which is an R element subset of A less the set A, because A isn't in there. R elements. Okay, why on earth are we doing this? We do not need to check that it's a bijection. Clearly is. but glad that we don't need to check it. Assuming that the map given in part B is a bijection, deduce that n choose r is equal to n minus 1 choose r plus n minus 1 choose n minus 1. So it's basically asking us to prove that the sum of the two previous entries in Pascal's triangle, because if you're unfamiliar, Pascal's triangle is like where all this is. So like r choose 2, for example, sorry, 3 choose 2, it means the third row, second entry, which is 3. That's the number of ways of choosing 2 objects from a set of 3 objects. So you can have those 2, you can have those 2, you can have those 2. So there's 3 different ways of doing it. And the Pascal's triangle, it comes from, you add these 2 together to make that, you add these 2 together to make that, and so on. So it's saying from row n, go to the previous row and add up the rth and the previous entry, and you'll get that. So it's asking us to prove that. That's interesting, actually, because it's just kind of by magic, isn't it, that this happens to be the same as this. Like, there's no, for me anyway, there's no good intuitive reason why that is. But anyway, so the size of this is the number of R element subsets, and A is size n, so that is just n choose R. And now since since P R minus 1 A and this one are disjoint is what I want to say, then the cardinality of the union is the sum of the cardinalities. Since it's the empty set, then this union this, oh, this is fiddly, isn't it, is this minus 1 A less which equals, so that's a size n minus 1, choose r minus 1, plus this is a size n minus 1, and we're choosing sets of size r. Okay? And since a bijection exists, then these then they are the same size. So this is the same size as the big union, which we've just shown to be that. I'm going to write it that way around because that's the way it's written in the question. Okay, done. Oh, I thought that question was over. What more do you want? Okay, so use Pascal's triangle. Okay, so here we go with Pascal's triangle. So we need the 7th row of Pascal's triangle. So 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, 1, 2, that's the 6th row, isn't it? So one more, 1, 7, 21, 35, 35, 21, 7, 1. So by the binomial theorem, which we actually didn't meet in the A-level paper, but they love to ask, expand this binomial and give the first 3 terms. They love to ask questions like that, usually with the generalized binomial theorem, but still. X to the power 7 plus 7, I'm just reading off the coefficients here, x to the power 6y plus 21 x to the power 5y squared plus 35 x to the power of 4y cubed plus 35 x to the power of 3y to the power of 4 plus 21 x squared y to the power of 5 plus 7x y to the power of 6 plus y to the power of 7. Show that so this is part A, this is part B. n to the power of 7 subtract n minus 1 to the power of 7 is congruent to 1 mod 7. So, okay. So this is x plus y to the power of 7 when x equals n and y equals minus 1. Let's do it that way. So that means n to the power of 7 subtract n minus 1 to the power of 7 is equal to, the first term is going to die, then we get 7 minus 7x to the power of 6 plus 21, sorry, it's n's now, isn't it? N to the power of 5, subtract 35, and we can already see what's going to happen here. These are all multiples of 7, which is something particular about that 7th row. Is it only on prime rows where it does that? There's something about the primes, isn't it, where on every prime row, they're all multiples of that prime? Is that right? I've just completely made that up. I don't know. Plus 35n cubed plus 21n squared plus 7n, and then a big minus 1 to the power of 7 minus 1. Okay, but we are doing the negative of all of that. So all of these signs actually flip, and we get, so it's congruent to 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 1 mod 7. Because they're all multiples of 7, they all die when we take that congruent mod 7. Okay, state a formula for n choose r in terms of factorials. So obviously it didn't want me to give that before, so I shall give it again. That is n factorial r factorial over n minus r factorial. Okay, to show that. Right. Okay, let me get a new piece of paper. So, just write that down again. N factorial over r factorial n minus r factorial. This is a weird little question. So, n is equal to 3n in our formula. R is equal to 3. So this is 3n factorial over 3 factorial 3n minus 3 factorial. And we've got to somehow show that it's equal to all that. Well, some of those terms are going to die, so let's go for the right-hand side now. The right-hand side, so n choose 1 cubed is just n cubed. How many, if you've got n objects, how many ways are there of choosing one object? There's n, you just n objects. Plus, so 3 choose 1 is 3. 2 choose 1 is 2. N choose 1 is n. N choose 2 is n times n minus 1 over 2. Plus 3 choose 1, which is 3. N choose 3, and I'll sort that out in a minute. So this is giving us n cubed plus 2's there die. 3n squared n minus 1 plus 3 lots of n choose 3. Right, okay then. So let's go back to the left hand side now. I'm just going to get these to marry up, you know, trying to bodge my way to it. So if you think about 3n factorial, what that means is it's 3n multiplied by 3n minus 1 multiplied by 3n minus 2 multiplied by 3n minus 3 and everything below. So we get some nice cancellation there. Minus 3 factorial, they die. So we've got n times 3n minus 1 times 3n minus 2 over 2. I've cancelled out 3 factorial is 3 times 2, so cancel that out. Right then, should I know what n choose 3 is? That's the question. Is as simple as n times n minus 1 times n minus 2 over 6? I feel like it might be, you know. Is that n minus 1, n minus 2 over 3 factorial? I think it might be. Yes, because if you've got n objects, how many different ways are there of choosing 3 of them? Well, you've got n choices for your first one, you've got n minus 1 choices for your second one, and you've got n minus 2 choices for your third one. But you can permute each of those, which is 3 factorial. Also, you could do it like that, couldn't you? You could say it's 3 factorial over n minus 3 factorial. So it's n times n minus 1 times n minus 2, and then all the other terms die. Okay, alright, okay, fine. Yeah, fine. So I'm happy with that. So, it's a lot of work, this, honestly. Let's expand. What's the easiest way of doing this? Okay, so we're trying to show, just to recap, we're trying to show that this is equal to plus n minus 1, n minus 2 over 6 times 3 over 2. So that's what we're trying to show. I think we're just going to have to bite the bullet and expand this whole thing out. I'm worried about all these 3n's though. That's going to make a 9n cubed at the end of all this. That doesn't seem right. That doesn't seem right at all. Let's just do it. So I've got 9n squared. I'm taking away 3n, and then I'm going to take away 6n. So subtract 9n. Plus 2 over 2. And it's equal, so let's start to expand this side now. N cubed plus 3n cubed minus 3n squared. Plus n squared minus 3n plus 2 over 2. They certainly do not look the same to me. Oh, yes they do, because it's not 9n, it's 4.5n. So it's 4.5n cubed, and here we've got 4, and here we've got half. So it's starting to look okay, actually. So let's deal with this one. So let's take the n out. We've got 2n squared plus 6n. I should have just added those. So that's 4n cubed, isn't it? So we've got 8n cubed. Subtract 6n. Oh, but I've taken the n out. I'm trying to do too many steps at once here because I'm bored of this question. Plus n squared minus 3n plus 2. Because I've taken the n out. I've timesed all of these by 2, and it's given me that much. So this is 9n squared. There's our old friend, the 9n squared. We've got minus 9n, and we've got plus 2. Yes! So they are indeed the same. Oh, God, what a mission that was.
Yeah, it's always interesting, these questions, because you do look at that and think that must be something that must be an identity that is useful. But God knows why.
Yeah, I know. I mean, especially with all these like 3 choose 1, 2 choose 1. You know, that must be good for something.
Yeah, or it's a specific version of an famous identity or something. They sometimes do that, don't they?
I don't know, James. It looks like something out of out of the exercises. Out of the problem set to teach you.
Do you think?
That's what it looks like to me. It just looks like can't possibly be useful, can it?
Yeah, I don't know. It could. I think it could be a specific example of a larger identity. Anyway, I've been really looking forward to this one, B9I, that we're going to do now. So.
Oh right, you've been looking forward to this one, have you?
Yeah, let's do that.
I didn't really read it. I saw the proof of the infinitely many primes,
Yeah, that's the bit I want to talk about. 'Cause, I mean, that is like
Oh,
classic bookwork, really good classic book. I mean, this is probably the definition of bookwork.
yeah, this really is. They could say prove that root 2 is irrational, couldn't they?
Yes, yes.
Uh, I'm just reading your comments. These terms are going to die. Those terms are going to cancel out. Yeah, I picked up this kind of language. I think we always say die, don't we? You know, if you do 0 times something, then it dies. I think, it was in 3rd year, was it, where we did the commutative algebra course, where the lecturer was like, and what do we do with this polynomial? We kill it. He used this vulgar like language when he was dealing with it. So good. Right, so this is a really good example of a proof, actually, which I think most of us, with a bit of a stretch of the imagination, can really get our heads around and prove something quite profound. It's so common knowledge among us that we forget how extraordinary it is, I think, that the primes do indeed go on forever. You can keep finding more primes. So the thing about primes is they become more sparse as we go up. So we start with a whole loads of them, 2, 3, 5, 7, and then we've got loads in the tens as well, 13, 17, 19. But then they start to kind of taper out. You know, we've only got 2 in the 20s there. So you know, the further we go, the more sparse it gets, and you know, you can imagine you go so high that you go through thousands of numbers before you even meet another prime. And the reason they're becoming more sparse is there's just more things to divide by. So if I pick the number 27 here, I've got loads of things that I could divide by. And it obviously turns out to be, you can divide it by 3. But if you go up to something like, the example we had before was 91, looks quite primey, but as soon as you start testing for numbers that you can divide by, you do realize you can divide it by 7 and 13, so it's a composite number. So the primes become more and more sparse as they go along. Now, this is, I'm going to give the classic, I think there's many proofs of this, but I'll give the classic, I think it's the Euclidean proof they call it. So we'll talk about that, and I just want to briefly talk about why this actually works. So imagine I look at the number 36, and the number 35 is 5 times 7. That means it's in the 5 times table, it's in the 7 times table. It means that 5 snugly fits inside 35, and it also means that 7 snugly fits inside 35. And when you have a snug fit like that, it's guaranteed that neither 5 nor 7 are going to snugly fit into 35 plus 1. And that's the really important concept about this proof. If 5 snugly fits inside there, the next number it snugly fits into will be 35 plus 5. And same with this, the next snug number for 7 will be 35 plus 7. So there's no way in hell that 5 and 7 are going to fit inside there. And that's the case even if I do 3 times, let's choose 3 different primes. Let's do 3 times 2 times 11, let's say, which is 66. So 3 snugly goes inside there, as does 2, as does 11, because it's in the 2 times table, it's in the 3 times table, it's in the 4 times table. So 66 plus 1, there is no way that these numbers are going to fit nicely inside 66 and then 1. That's the key. That's the key. So what we're going to do now, we are going to prove that the primes go on forever. And to do that, we're going to assume that there are, in fact, there are only a finite number of primes. So, the other thing to say, I guess, is the fact that no matter what number you start with, you can break it down to a point where you can find a prime factor of that number. So whatever number you start with, you can find a prime factor of that number. That's important as well. So put a pin in that. Put a pin in that, because some magic is about to happen. So assuming that there's only a finite number of primes, if there's a finite number of them, we can write them all down, and we'll give them names P1, P2, all the way up to Pn, where n is just some number. There's n primes, and they're the only primes we've got in the entire universe. There aren't any more. That's what we're assuming. Something is going to go wrong here, because we're actually trying to prove that there are an infinite number. So what happens when we times them all together? Okay. Now, P1 fits snugly inside here, as does P2, as do all of the primes. And that means that none of them will fit snugly inside this number here. So, the question is, what is the prime factor of that number? Because P1, P2, P3, none of the primes in our list fit inside this. It doesn't have any of the factors in our list. So, there must be some other number to divide, another prime that will divide this number here, or this number here is prime itself. In any case, if this is prime, then we've got another prime that wasn't in our list, so our assumption is false. If there's another prime that must divide it, then we've got another prime that wasn't in our list. So by assuming that there's only finitely many, we can immediately find a situation in which there must be another one. So, and that happens whenever we try to assume that there's a finite number. So therefore, our assumption was false. So there are infinitely many primes.
Bravo.
I did that in far too much detail, but you know, this is something people should be aware of. It's total magic to me. You know, the fact that we can prove this. Now, just as a brief aside, that turned out to be quite easy, really, and it's been known for thousands of years. Like I said, I think Euclid was the first person to do this, or at least it was named after him. You know, so it might not have been him, but you know. So this is rudimentary, but let's make the question slightly harder. So some of these, so for example, 3 and 5. That's a bad way of writing 3 and 5. These are what we call twin primes, because they've got a difference of only 2. And again, these become more sparse as we go along as well. So we've got loads to begin with, 17 and 19 and so on and so forth. But the more you go on, the less common they are. And then the question to ask is, well, the question to always ask when there are less and less and many of them is, do they go on forever? And while it's easy to prove that there are infinitely many primes, are there infinitely many twin primes? We don't know, is the answer. It's yet to be proven.
I genuinely thought you were about to prove this. Like you were just about to launch into proof, because you said, let's make the question slightly harder. And then you started talking about twin primes, and I thought that you were just going to prove that.
Yeah.
Right here, right now, live.
YouTube.
For
Like,
all of these people to see.
Like what Andrew Wiles did, you know, when he proved Fermat's last theorem. He invited everyone to that conference, and there was rumours going around that that's what he was going to do, but he did like three-hour lectures where, you know, there's all this kind of buzz in the air about, you know, by the end of the second lecture, they all knew what it was going to be, but like, and there it was, the proof of Fermat's last theorem. Yeah, I'll just go ahead and use the remaining 16 hours to prove the twin prime conjecture. Yeah, but it's, I mean, I would love to, because I think there'll be a lot of money in that and a lot of fame. But the fact that this is an open question and this is a rudimentary one is, I find, quite extraordinary. This is a different kind of question because this is all about, the primes are all about multiplication. The reason this question is so hard is because you are asking, given P a prime, when is P plus 2 prime? And as soon as you bring addition into anything, the question becomes so much harder. Multiplication is really the natural way to study numbers in any meaningful way. Addition ruins everything. Addition is just so messy because it's totally unpredictable. when you have a prime and when you don't, and when you start to add things together, it becomes just generally very messy. You know, look at the numbers. 32, that is a nice power of 2. Then we go to 33. That's what we call a square-free number because it's just 2 primes times together. You know, it doesn't have any prime squareds. 34 is also another square-free number. 35, again, it's the product of 2 primes. 36, all of a sudden, loads of factors. And then 37, we've got a prime. So adding numbers creates a lot of unpredictability, and that's why the twin prime conjecture is so hard. And in fact, it's why all those famous conjectures are so hard. The Goldbach conjecture, which says that every even number can be written as the sum of 2 primes. Well, the primes are all about multiplication. What happens when you start adding them, we don't know, and usually we don't care. So that's why that conjecture is so hard. And the the Collatz conjecture, the 3n plus 1 thing, as soon as you start adding, things just get messy and get very difficult. So, but addition is the first operation that we learn about, and through something as trivial as addition, we create such difficult questions. Anyway.
Okay. Yeah, time check.
Okay, so it's 19. Okay, let's try and just finish this question, and then yeah. Okay, so prove by contradiction that if a is an integer and p is prime with p not dividing a, then they have oh wow, okay, let me just pass that. So p doesn't divide a, then greatest common divisor is 1. Okay, so assume GCD of p and a is k for some k greater than 1. Oh, thanks, David. That's really kind to say. Thank you. Just seen his comment there. So that means that k is a divisor of p and k is a divisor of a. But the problem with that is it implies that k is equal to p. So if k is equal to p, then now p divides a, which is a contradiction. It contradicts the fact that p is not supposed to divide a. Question B. Prove that if a and b are integers and p is prime and p divides the product, then either... Okay, yeah, I think I remember how we do this one. So p divides ab. That implies that it's an integer I can times by k to make ab. And... oh no, I think what we're going to do is we're going to... Oh yeah, okay, so we want to show that either p divides a or p divides b. We will assume that p does not divide a, and we will aim to prove that p must therefore divide b. If p does not divide a, then the greatest common divisor of a and p is 1, given to us by part a. And then by this Diophantine thing, I wish I knew the name of the guy. I don't know. So we can... There exists, let's call them x and y in the integers with ax plus py is equal to 1. We want a b to be involved, so we times through by b. And remember this much. This seems right. And we've not used that yet. So let's get that in there. AB is kp x plus p by is equal to b. Yes, p kx plus by is equal to b. Therefore, p divides b because it's p times something equals b. Okay, state Fermat's little theorem. And there's multiple equivalent ways of stating this. The one I tend to like is, so if p is prime, a bit of background on Fermat. So Fermat was not actually a mathematician. He was a judge, actually, but he did maths as a hobby. So he was like a recreational mathematician. and he proved a bunch of theorems, but he famously neglected to prove a theorem which became known as Fermat's last theorem, which took another 200 or so years to actually prove. And he wrote this famous line in the margins of his book that said, I do have a proof for this theorem, but it's too long to include in the margin here. The common kind of consensus is that either he was joking or he was wrong, because it took so long and so much new mathematics to be developed to actually prove that theorem that he can't possibly have had a genuine proof. But anyway, and a is an integer, then a to the power of p is congruent to a modulo p. Now, I think the other way to state this is a to the power of p minus 1 is congruent to 1 mod p. That's the other way of stating it. It kind of depends on what you're trying to do as to which one is easier. Find the least positive residue of that. Okay. Obviously, we need to use Fermat's little theorem. So Fermat's little theorem is what is I don't know why little, actually. Maybe in contrast to the last theorem, but this one is one that he did indeed prove. So what do we want to do here? So we want to get 820 to the power of... I think I'm going to actually go with this version, because... So what's 550? Does it divide by 16? No, it doesn't. So 820... So 550 is equal to 34 times 16 plus 6. And we'll do the same for, I think this is the way to go. Oh, sorry, 279 divided by 16. So 279 is equal to 17 times 16 plus 7. So, in other words, 820 to the power of 550, which is a monstrously huge number. And then we're multiplying it by another monstrously huge number. But we do know things about them. So we know that this is actually going to be 820 to the power of 16 to the power of 34 times 820 to the power of 6 times 549 to the power of 16 to the power of 17 times 549 to the power of 7. And the reason we've done that is because now, appealing to Fermat's little theorem, a to the power of 16 is congruent to 1 modulo 17, where p is 17. That's the prime that we are taking the modulo of here. So that means this is congruent to 1 to the power of 34 times 820 to the 6 times 1 to the power of 17 times 549 to the power of 7. Now we've broken the numbers down into calculator size. So divide that by 7. Yeesh. So that's... so we want to take... no, okay. Oh no, we can take 820 mod 7, can't we? So that's 820 is equal to... sorry, 17. What am I doing? 48 times 17 plus 4. So this reduces to 4 to the power of 6. 549 divided by 17 is 32. So this reduces to 5 to the power of 7 mod 7. So 4 to the power of 6. I keep writing 7, don't I? Sorry, mod 17. times, let's do it all in one go, 5 to the power of 7. Divide that by 17. Okay, so 188,23529 equals 7. Okay. And the next part is going to be something very similar. You know what? Since I've done 3 questions already out of the 5 necessary, I think I'll skip that last bit. It's just going to be more of the same sort of stuff. And then we'll take a look at that next question. But I think that's a good time. So you're not a big fan of this paper, James?
On this paper, I don't like Fermat's little theorem.
Why not?
Because I'm very bad at arithmetic, and I never learned it properly. I never learned modular arithmetic properly. I've never.
But it's just magic, though, isn't it? Like,
you're not going to convince me. I'm sorry. I've been lost to this world long ago. Give me some functions. Give me some continuous stuff, and I'll be happy.
Always with the continuous stuff. Yeah.
Always with the continuous.
You don't think it's just absolutely miraculous that for some reason you take any old number and you raise it to the power of I don't know, 6. You know that when you divide it by 7, it'll have a remainder 1. Like, you know, why do we have any right to expect things to behave so nicely? You know?
Yeah, I know.
You know. Yeah.
Oh dear.
Okay, so if you are watching, we've reached the end of part 1 of this particular stream.
Yes.
That actually tells me that we are a third of the way through, and I've not yet finished this 8th paper because I'm spending so long talking about all of the mathematics involved, which is
having too much fun.
Which is my fault, but I think it is fun. Yeah, you're right. B10. We're going to be carrying on with this group theory question. Now, group theory is, if I do have an area of expertise, it should be group theory. That's what my my PhD was based on. So this should be a fairly straightforward question, but it'd be really good to talk to you about what groups are, why we have them, and what we can do with them, and how they relate to the maths that you might already know. And then after that, we will be powering through. We've got some GCSE papers, we've got some A-level papers, we've got some international GCSE papers, and it's going to be a bit of a sprint. We've also got that further maths paper in there. I'm tempted to get that one done and out of the way while I still can think clearly. So that's the end of part 1. You will find the link to part 2 in the description. You can also get to part 2 using the Tiltify page, which I'm just about to update. Thank you so much to those who've been watching, and to those who are still watching, and especially to those who have made a donation to Refuge. So I'm going to end this stream now, and I will see you in part 2. There'll be a delay of a couple of minutes, but I'll see you then.